My name is Ashwin Ram. I'm a Technical Director of AI in the CTO office at Google Cloud. And we've put this day together for you with one of our leading machine learning practitioners and scientists, Cassie. Cassie has a really interesting background. She has 4 degrees. She has degrees in psychology, economics, mathematical statistics, and cognitive neuroscience. And what she does is look at data using the lenses of statistics and machine learning to bring it together to help people and companies make decisions. Her role is a chief decision scientist at Google Cloud. It just changed from chief data scientist with the office of CTO. So my pleasure to introduce Cassie, and she'll take it from here.
Thanks so much for that introduction. So hello and welcome. My name is Cassie Kozyrkov. I serve as the Chief Decision Scientist for Google Cloud, and it is my pleasure to welcome you today to the wonderful world of machine learning. Now, this course is one of Google's most popular courses, and it is accessible to all of our job roles. So it is specifically designed to be entirely beginner-friendly. So even if you don't know what a computer is, hopefully you should still be fine in this course. Never seen an equation before? Fine as well. So we aim for the big ideas, the flavors of things, because I believe that technical nitty-gritty, those equations and those code things, I really like to do those things, but I don't like it when those things are done to me. So in a class setting, it's excruciatingly boring, at least I think so, to watch somebody copy out a textbook on the board. When you know you can go do that yourself with a cup of coffee, that's much more fun. So I'm aiming to give you all the other stuff so that those textbooks, equations, and code snippets make more sense when you are playing with them yourself later. And the focus here is on application, on process, and on big ideas. So let's dive in, shall we? And see what it looks like when a learning system is learning. So this is an AI system learning to play an Atari slider game, Breakout. And when it begins, it is playing, if you will believe it, worse even than I play. I give it a little while longer, and it's a flawless expert. It's getting some pretty steep angles there. And then, see what we want it to do. We give it controls of a joystick, essentially, and its sensory input is this environment. We don't tell it anything about the rules of the game. Tell it just to figure it out, but figure what out? Figure out how to get the most score velocity. In other words, how to get that score to go up as quickly as possible. And so after it trains some more, this little bundle of math and joy is going to figure out strategy. If you wanted to get that score to go up as quickly as possible, what would you do? How do you play? It tunnels up the left side, and look at that score go up. How many of you do this? Yeah, seriously? Okay, wow. All right, I'm impressed. We've got an expert audience in the room. When I gave this presentation in the Tokyo office, it was like almost all the hands. What am I dealing with here? Anyway, now this looks all exciting, it looks magical, and there's all these marvelous buzzwords in this space. Neural networks, AI, machine learning. You're all excited. So, let me take you down a notch. What is machine learning? It's used often these days as synonymous with magical magic. It's a magic box of magic, and we open it up, we sprinkle magic on the top of our business, and magic happens. Actually, let's just put it bluntly. It's something far less glamorous. Machine learning is a thing labeler, essentially. It's an approach to making lots of small decisions with data. Decisions like, is this email spam, yes or no? Or what should I bid on the next auction? How do I move a joystick? And if you want a computer to make decisions for you, it's got to convert information, input data, into an answer, a label, or a decision via some kind of recipe. And the difference between traditional programming and machine learning simply boils down to where that recipe comes from. So where does it come from in traditional programming? Of course, the human programmer must communicate in some way with the universe, think deeply about the problem, channel divine inspiration, and handcraft that recipe as code that the computer will then use to convert data into outputs. Now, in machine learning, we don't handcraft anything anymore. Now the programmer's task changes to feeding examples into the system, and it is the machine learning algorithm's job to stitch that recipe together out of the examples. So that's the difference. Now, why would you use machine learning? Well, let's take a look at a little example. Here I have a completely made up treatment schedule for a patient. From day 1 through day 60, this is the correct dosage in milligrams. And now the exercise is to see whether you are actually alive and able to make noise. So, it is day 2. How many milligrams do we give the patient? 17. Day 4. 41. Day 2 again. 17. Would you use machine learning to solve this problem? Well, how would you solve this problem? I hope you would do a lookup. Just look the answer right up. Don't do any kind of magical learning. There's the answer, why not just look it up? So you don't need machine learning in this situation. Okay, different question for you. It is day 61. What is the answer now? Aha. Well, if there are no patterns here in these data, then you can't actually solve that. Nothing can help you for day 61. Or if there are patterns, but they just simply don't apply past day 60, they don't generalize beyond that, because maybe the patient is now healthy or, I don't know, dead, then, right, doesn't work either. So the only way that you might be able to make an attempt at day 61 is if there are patterns here that you can find and make a recipe out of, and that are still relevant and useful in this new data situation. In that case, you would want to use machine learning. So I'm going to say over and over today that in machine learning, we have one job: succeed on new stuff. That is the entire focus. Do well in new data situations, because how do you deal with the old ones? Just look it up. All right, so how does this magic thing work? We have some data to learn from, and our task is going to be to predict whether or not I like a bottle of wine. So what we have here is the correct classification for 50 bottles of wine: a red Y for yummy and a blue no for not so yummy. And I have the age of the wine in years and the opinion of some amateur wine critic friend of mine on the y-axis here. And the game here is to find and exploit patterns in data. So look at these data and tell me when you see a pattern that you can exploit. Something to separate the yeses from the nos. That's the game. So can you do it? You come up with a recipe that separates them? Nod when you see it. Nod when you see it. All right, I see some people who are finding it. Very nice. And now I have to own up that it's all a trick. Actually, these data, I made them up, and I made them up completely at random. So I know that there are no patterns here. And if you're finding patterns that are sort of spirally or circular, and you think you've got some story that you can base a recipe on, that's your beautiful human mind finding Elvis's face in a piece of toast. Our brains do that. We find patterns that aren't actually there, and then we think that we've got a strategy that we can exploit, and things go wrong when we try to use it. Now, machine learning can do exactly the same thing: find patterns that are not there. And then if we base our solutions off of those patterns that aren't there, of course things crash and burn. So the approach that we take to protect ourselves, and we'll talk about this a lot today, it's the same approach that we should actually get in the habit of taking with our own human intuitions. Don't take it seriously in the piece of toast where you found Elvis's face. Try it on a new piece of toast and see if the face is still there. So try it in the new data, see if that recipe still works. Whether it comes from a machine or from a human, that's the part that keeps you safe. Okay, enough messing about. I generated these data and I promise you that there is a pattern in here. How would you exploit this pattern to help me classify new bottles of wine? How about you put a line through it, and that line is a wall that separates the red region from the blue region, and off we go. Sounds good? That's pretty much what machine learning does. Now, that boundary does not actually need to be a line. Those gobbledygook algorithm names, which we'll meet later, the main difference between them is the allowable shape of the boundary that the thing is trying to shove through your data. So if you pick this one, it's going to try to put one single line, and that line can have any slope. With this one, now it can use many lines, but the only slope options are thus and thus, vertical and horizontal. Or you can have a real nice flexible squiggly thinger, which we call neural network. And once you have picked the algorithm and the allowable boundary that's represented by it, then what it's going to do is, based on where your data lie, it's going to try to find the most sensible place to put that allowable boundary. So it's going to try to contort itself to your data, subject to the sort of thing it's allowed to be. So say we pick the line, and we run it. Oh, there we go. There's our answer. And what comes out of this is what we've wanted all along, a model. Now, a model is just a fancy word for recipe here. Just a set of instructions to take inputs, turn them into outputs. And our model reads, if we're in the red region, call it red. If we're in the blue region, call it blue. Job done. And so in comes a new bottle of wine. Red or blue? Red. But we could have chosen a different algorithm. There we go. Let's pick the tree and run that thing. Here is our recipe. And that's a different recipe from the previous one, right? And in comes a new bottle of wine. Blue. Troubling. Most troubling. If you look in any textbook and ask, what is a reasonable, classic, respectable algorithm to use for this situation? Some textbooks will tell you this one, some textbooks will tell you that one, some textbooks will tell you both with a completely straight face. These are the things you need for this situation. Okay, so then you follow the textbook's advice and you end up in this situation where one of them says we'll like the bottle, one of them says we'll hate the bottle. They can't both be right. So which one of them is lying to us? Who is the imposter? How do we tell? Well, we remember that the whole point is, does it work on new stuff? And so we simply see which one actually does work on the new stuff. The point is to generalize beyond our data. So that is how we evaluate. Let's find out who wins on new data. So in comes some new data, and we apply both of our recipes to it. And of course, we get different answers. And I'd like to remind you, when we ran these two algorithms on our initial dataset, the training dataset, they both gave perfect performance. They managed to split the space so all the red went to red and all the blue went to blue. No mistakes. So both of them had 100% performance scores. But now, look at these results. Because they're different, one of them will probably be worse than the other. So let's find out who. How? Well, let's drink some wine for science. Here are the correct answers for that dataset. And all we need to do for our fancy statistical testing, never mind what models it all came from, you can forget all that at this point. Compare the desired answers with the answers given, and I feel like I have a preference here. I don't know if anyone else does, but I sort of strongly prefer the one on the left. And then I would iterate towards my solution with that one. And I would do a careful launch test before launching it, which we'll talk about later. So what is machine learning? It's an approach to making repeated decisions that involves algorithmically finding patterns in data and using these to make recipes that deal correctly with brand new data. Okay, now what's under the hood? How does it decide where to put that thing? What's inside that black box? Surprise, it's full of math. And on our menu today, we are going to meet the flavor, rather than the equations, of a whole bunch of algorithms. But here's how we're going to do it. Right now, I'm going to introduce you to this one, and my goal is to set your thinking about these algorithms. What are the important ideas here? And then later, when 90% of you have fled and gone home or went to play outside, at the very end of the course, after we've covered the end-to-end applied machine learning stuff, we're going to look at all of those. So let's dive in. Regression was first used in 1805 by Legendre, who doesn't have a nice painting of him on Wikipedia, so I picked the one for the second person to use it in 1807, Gauss. So that's more than 200 years ago. This has been around for a really long time, and it's still a really popular standard approach to machine learning today. So let's have a look. For our example, we will be making smoothies. Every smoothie will have 1 cup of plain yogurt, 1 secret ingredient, and a bunch of random food dye so that you cannot tell what is in there. I blend it up, I serve it to you, and your goal now is to shout at me, what are the calories in this smoothie? Go. What do I hear? 100. 100. Going once, going twice. 300. 500. Now, I'm doing a little test here, seeing who's got the strongest aptitude in the audience for machine learning. Because the machine learning attitude is not the attitude of perfectionism, of think carefully and get the answer right on the first go and don't even try it unless it's going to be perfect. No, the attitude is go for it, see what happens, get it wrong, because you're going to have to do it over and over again. You're going to fail, fall down over and over again, pick yourself up, try again until finally it works. And you have to try something to know what to do next. And so if you're too afraid to start, you tend not to do well in applied machine learning. So those of you who are brave enough to just go for it even though you didn't know the right answer, yeah, that was what's going to get me to move to the next slide and give you more information, and we'll be able to iterate towards correct together. Okay, so you've unlocked the next slide. Turns out this was, what was the secret ingredient? 58 delicious grams of sardines with 265 calories in there. Lovely. I see you don't want to drink it. Fine, I make you a different one. Guess the calories now. 80, 400. 180. All right, I'm hearing some more responses and rumblings. Now let me tell you what was in here. 50 grams of not delicious waffles that I've shown you in the picture. No, the raw stuff, waffle mix. And this is actually an homage to a standard hazing experience that happens on the 5th floor of the Google office here in New York, which is most new Googlers, myself included, I've done this. You walk up and you see this delicious smoothie and you try it and it is not a smoothie. So standard newbie hazing experience here. Okay, so you don't want to drink this one, fine, I make you a third one, but before I make you guess, I'm going to give you a little more information. This is the 16th smoothie that I've made, and here are the 15 previous calorie amounts. Your first reaction to this should be not trying to read it, but instead stamping your foot and saying, I'm a human. I don't add numbers up, that's what machines are for. Indeed, correct. So the machine's going to help us out and summarize them. And we find out that the average is 237 and the middle thing is 240. Have a guess now as to the calories of this one. 237 I'm hearing, 238, 240. Notice how your range has narrowed a whole lot as I give you more information. That's going to be key to our discussion. Okay, I'll go for 237. It turns out to be 88 grams of quiche Lorraine, clocking in at a whopping 445 calories and proving to us that any liquid diet is beatable. So how did we do? We had an underestimate of 208 calories with that strategy. And can we do better? Well, maybe it would help to have the weight of the secret ingredient. So what we'll do as analysts is we'll make a little plot, and we'll have the weight from 0 to 200 grams on the x-axis and calories from 0 to 500 on the y-axis. And as we look at this, we ask ourselves, is there anything going on, or is weight completely useless here? What do you say, completely useless? Something to it. And since there's something to it, maybe we'll go ahead and we'll try it out, shall we? And regression is about putting lines through stuff, so why don't we put a line through it? You like that line? Good line? We missed. Where should we put this line? By the way, those who forgot how lines work, here's a handy cheat sheet. The recipe, the model, is simply intercept plus slope times the weight. So we'll have two numbers here in red that we have to find or discover that determine where the line goes, and then we pop the weight in there and read the calories off of it. So that's what we're dealing with, straightforward stuff. So you don't like my line? Okay, fair enough. How about that one? You don't like that one? This one? It's a tough crowd. That one? No. This one? You look offended. Why do you look offended by this? Because let me remind you of something real quick. This right here, this is your previous model. And now you're offended. But before, you were very happy to just guess 237 every time. 237 and 0 times the weight means I ignore the weight and say 237 every time. And you were so fine to use it then. Check your feature engineering privilege. What is feature engineering? That's when we create inputs that we might use to learn from. Stuff that might inform our solution. And when we have a feature that we might use, suddenly we can do better. So that's kind of going to be the point here. As we get information that's going to be relevant to solving this thing, we expect to do better and better, and it's going to be up to us to think about what information might be worth putting into the system in the first place. Okay, so let's do better. If we can do better, we're going to find a line that's as close to the points as possible, because you seemed offended when I wasn't doing that. Fine. So we better define a notion of an error. What's an error? It's just the point minus the line, the truth minus what we were saying we should predict. And because we all have type A personalities here, we hate errors. So we are going to minimize a function of these errors. That is going to be the score for how this thing performs. And a good score is to have fewer errors, and we will use the RMSE here. And this thing is very creatively named. It's actually the recipe for calculating it backwards. Get the error, square the error, take the mean or average, and take the square root of that. Root mean squared error, or RMSE. Okay. Or you could just think of the RMSE as the calories we're off by on average. Not technically correct, but good enough for government work. We're off by about 85 calories on average, and that'll do. That'll fine for a morning. So now we're off by 85, and we want to be off by fewer. So let's see if we can just jiggle those two parameters there in the recipe to make things better. What do you want to do? Maybe you want to increase the slope a bit. Okay, that's getting better. Good. How about we increase the slope a little more? Not so much better. Maybe now we want to move the intercept down, so let's do that. And what we could do is we could continue tinkering with these two numbers, with slow, boring tinkering, or we could get on with it. So what are our options? just play by hand with those two numbers, which is what we were doing. Or we could use calculus, but who even does calculus anymore, so old school. Or we could just use an optimization algorithm to get us the answer immediately. So what does an optimization algorithm do? It says, for this setting, you are trying, what's your goal? You are trying to get this function right here to be as low as possible. Let me figure out for you what settings on those two parameters that I'm allowed to play with give me the best possible performance here. And then it outputs you that answer. And that's going to be in the heart of every machine learning algorithm. So we're going to need to know what the scoring is, what the goal is, and then it's going to figure out where to set the free parameters in the recipe based on that. Okay, great. And we have come a long way. I'm impressed with us. Nice. Let's look at Quiche Lorraine, though. It's taunting us. We did not predict Quiche Lorraine well. How did we do? Better. Our underestimate has gone down. Okay. Can we do even better? Can we? Well, there ain't no such thing as a free lunch, she says at Google. To do better, we actually need something else. So what is it going to take? We need, any guesses? More information, exactly. That was actually very nicely put, because that says two things at once. More information in the sense of just more of the same data, or more information in the sense of other kinds of information that might be helpful. In other words, more features. Features in this setting refers to variables, attributes in other settings. So I'm going to be generous, and I'm going to give you the fat percentage. How do you feel about that? Is that going to be helpful? All right, so let's see. So this is what we were working with before. This is our form, and we just had to muck about with these two parameters here. And we used an optimization algorithm to set them. And notice, who here has taken a stats course of some kind? Yeah, you probably saw regression. It was an entirely different story in that course, the way that you were going about it. There was all this other stuff about what it means, and p-values and t-tests. None of that is relevant here. All we are trying to do is optimize that function to set these two numbers so that the difference between the calories predicted and the actual calories is as good as possible. That's it. That's all there is to it here. Much, much simpler than what the stats course did. So there we go. Those are our answers. Lovely. Now, it's not going to be a line anymore if we add fat percentage. It's a bird, it's a plane. Same structure, just we add another one of these right here. And now the only pertinent thing for you to realize is that there are 3 widgets to tinker with. Nice. And plotting it there, we need to add a dimension. I can't make heads or tails of this, so a little shout out to better plotting. How about adding color? Okay, still not enough because I can't see what's going on. The color is more calories, gets redder, but I can't see what's going on with this fat percentage and weight plane, so okay, now I can kind of see what's going on. And if you're used to looking at these things, you kind of see the punchline that's coming. But even if you don't see it, let's find out what happens if we run the algorithm. So again, our job is to get those 3 numbers to be as good as possible. We have our 3 options. I pick the getting on with it. And so we have this mosquito netting fitted through our data for us. What is it trying to do? Get as close to our points as possible. And those are the numbers that do it. Quiche Lorraine is still taunting us. How did we do? We are now off by 47 calories on average. Before, it was 49. I don't know, I'm not feeling it. I had to double the number of ingredients into my recipe, and all I get for that is this measly tiny improvement. Maybe after all, this isn't such a promising direction to go in. Maybe I would prefer the simpler model, but of course, don't worry about that too much. You can always try both of them in a new dataset and see which one is working better. So how are we doing so far? Using only the mean. There's our underestimate. With simple linear regression, that means 1 ingredient. we've improved, and only a slight improvement with multiple linear regression. That means more than one input into the model. All right, I'll take a question.
Can you do a model that has fat percentage times weight? That's actually tells you how much fat content it is.
Can you do a model that does fat percentage times weight? Absolutely. And there's a good reason to think about doing that, like the bit about the water amount of the secret ingredient. We didn't even cover that, right? If I just dilute the secret ingredient, I can mess about with the fat percentage. The reasoning around whether or not you should go ahead and try a model like that is, does it take a long time to try it? If no, just do it. Even if you don't have as solid of a logical argument, try it anyway. You can always try something like that, and yes, it's very, very easy to adjust the method to input something like that. You just make the feature by multiplying them first, and in it goes, job done. So certainly could try that. Okay, can we do even better than that? Sure. How about if I'm really generous? This is non-alcoholic, and I'm going to give you the fat in grams, the carbohydrate in grams, and the protein in grams of our secret ingredient. Does anyone want to spoil the punchline for us? Who knows about nutrition? Let's have it.
9 times fat plus 4 times carbohydrates plus 4 times
9, 4, and 4, the magic numbers. Because we as humanity have figured out a whole lot about nutrition, and we already know the answer. Well, doesn't matter if we know the answer. Why don't we see if we can recover that same answer from this data set with machine learning? But yeah, let's hope that our final answer is going to look something like that answer. So here we go. This thing is now not a plane anymore. It's now a hyperplane. So let's go ahead and plot it. Let's not. There's no real reason to be plotting it here, because at the end of the day, the way that we check how well we're doing, how we get that score that we're optimizing, it happens the same way no matter what is in here. All we need to know about is that we take what's predicted, we compare it with the truth, and we see how we did. And inside this thing, however beastly it is, there are some numbers that we are allowed to tinker with, and we'll use an optimization algorithm to do the tinkering for us, and hopefully some researcher somewhere has written that optimization code so we don't have to. So that's a much better thing to spend your time on if you're in a research division, or a research in industry, or a research division in academia. Good, and they have, and so we don't have to worry about it. All we need to know is 4 things to tinker with. We'll still assess the results the same way, doesn't matter what's there. So let's get on with it and use that optimization algorithm, which we don't need to know how it works. And there you go. How did we do? 9, 4, 4, something like that. Looks pretty good to me. FDA, by the way, confirms what you say. This is a quote from their website. Carbohydrate provides 4 calories per gram, protein 4, and fat 9. So very good general knowledge. What on earth is this 143 thing? Well, we ask ourselves, if there is no fat, no carbs, and no protein, if our secret ingredient was water, what's left? Well, there was yogurt in there every time. Now, it turns out our yogurt base had 145 calories. We're predicting 143. There's a little bit of a mismatch, so maybe there was some error in our data. But you know what? Our score is getting pretty good. Not perfect, but pretty good. We're off by 4 calories on average when it used to be 47. And this is again a shout out to feature engineering. The fact that you had the knowledge about this domain and realized that having the weights in grams of all of these things was going to be useful, that is the reason that you get a model that's this good in the end. It pays off. You can convert your domain knowledge into good solutions. And how did we do in the end? Our underestimate for quiche Lorraine is only 4 calories. I say good enough, let's drink it. Okay, and we will see the other method flavors for that big laundry list at the very end, and you can stay for that if you're interested, or flee earlier if you're not. Right, so what is AI? Well, it depends on whom you ask. AI was named a pretty long time ago, in the 50s, artificial intelligence, and back then it kind of meant something else in regular usage. And I wonder sometimes whether today's calculators would have seemed like AI to folks in the 50s. Sometimes I like to joke that that version of AI was whatever would have impressed those folks, and whenever that was achieved, you just move the goalposts away a little bit. But in that old school sense, it is a sort of superset. And machine learning would be in there somewhere. Where machine learning is, let's remind ourselves, thing labeling, using examples. But the way that AI is talked about today is actually something else. It's more of a subset to machine learning. So let's have a look at some AI tasks and see what they have in common. There are tasks like figuring out whether an image has a cat in it or not, having a natural-sounding, human-sounding conversation, playing games that you don't know the rules for, that you have to use intuition to figure out the rules. Well, when you, the human, do these tasks, you are taking in information through your senses, and you get the answer as if by magic. You don't even know how you know that's a cat. You don't know how to move that joystick in that game. You just know it. You do something with these pixels, and you don't know what you do. Now, think about trying to solve a task like this the traditional way. You have to really think hard, brainstorm what to do with every pixel, and then give the computer those instructions by hand. Here's how you take the pixels for this photograph, and here's how you figure out whether it has a cat in it or not. Now, what recipe are you going to write? And as you're thinking up that recipe, are you sure it's still going to work for that situation? It's pretty hard to write these rules. You need complicated instructions to do this task. And you have the benefit of eons of evolution. Your brain just does this. You have no idea how it does it. And the task is easy for you. And generating the examples and checking whether the task is done correctly, that's really easy for you. But you don't know how you do the task. So how can you express that to a computer? You can't solve it the old way. AI, the way we think of it today, is about succeeding at those complicated tasks that programmers cannot write instructions for by hand. And you need super flexible algorithms, neural networks, and that is part of a class of stuff called deep learning. It's part of machine learning. And so when people say AI today, they tend to mean deep learning. That's the way that it's used. So solving these really complicated tasks that you couldn't solve a different way, except by teaching the computer with examples. So this is about automating the ineffable. You can't say how that task should be done. You can't solve it the way that you do the calorie prediction. Now, I also want to point out something really powerful here. When we as humans communicate with one another, when we are trying to get another human to do something for us, we have 2 modes of communication available to us. Direct instructions, or, hey, look at a bunch of examples and you figure it out. And we use both as the situation demands. Before machine learning, we didn't have the ability to communicate that way with computers. All we could do is give the instructions directly. So that's like a huge part of our natural communication that we want to use, gagged. Think of this as an ungagging. Now, as a programmer, you can communicate with the computer 2 different ways. So don't think of this as something sci-fi and robotsy with a mind of its own. Think of it as unlocking a second way to get computers to do stuff for you. That's what we're about. And this is really powerful because it's a whole class of tasks that you can automate that you just couldn't automate before. So why now? I mean, these things have been around for a really long time. Neural networks were named in the 50s. Linear regression, Gauss was doing that 200 years ago. Why only now? Well, if you're going to build these more sophisticated recipes, you're going to need more. More sophisticated algorithms, more data, and more computing power than before. And until fairly recently, and I'm talking this decade recently, we just didn't have that. So I'd like to introduce you to 3 of my colleagues at Google who've been working in these 3 areas, and they, along with others, have been instrumental in changing all that so that science fiction is now here. So first off, Geoff Hinton. Geoff Hinton is one of the pioneers of artificial neural networks. Artificial neural networks, and that will be the last of the methods that we'll get a flavor sense for on our menu, they are essentially many layers of mathematical transformations. Not much to do with brains. But if you have all these layers of transformations, you effectively have a very flexible recipe. And if you have such a flexible recipe, you are able to fit those boundaries for a much wider, more interesting class of tasks. I mean, think of those surface boundaries with neural networks. You can pretty much sign your name in cursive, which you can't do with a bunch of lines. So you can solve more interesting tasks because these algorithms are very flexible. The price, though, is you do need more data and more computing power to make them tick. So, introducing Fei-Fei Li. Now, Fei-Fei started her career as a computer vision researcher at Stanford. And, well, actually, when this was going on, Fei-Fei was at Caltech. And Fei-Fei was thinking about why a 3-year-old human child is just so much better at this cat-no-cat game than any computer vision system out there. And she realized that 3-year-olds have something that computers don't have. A loving parent who bothers to give them a bunch of nicely labeled examples to learn from. The parent is saying, "No, sweetie, this one is a cat, not a dog." And she did a quick back-of-the-envelope calculation and realized that a human child would have on the order of millions or tens of millions of examples. She thought, okay, well, maybe that's why machines aren't succeeding. Of course, these computer vision folk who are trying to use a few thousand examples aren't going to get anywhere. You're not going to get performance like a 3-year-old. Based on that, fine. All I need to do is I just need to pick up a data set that's nicely labeled and big enough, and then off we go. All right, who's got this data set for me? It turns out people like their kids more than their computers and haven't bothered to make that data set. And so you can't have any progress. And Fei-Fei decided that she was going to change that. And whether or not they would force her out of grad school, she would sit there and organize a project around getting great examples, nicely labeled data that everyone could learn from. At some point in this project, she was running something like 60,000 mechanical Turk workers, all sitting there labeling things as cat, not cat, for you so you don't have to do it. And then when ImageNet, her project, launched in 2009, it had something like 2 million beautifully labeled photographs. And she made that available to everyone so that the whole community could make progress. But algorithms and data aren't enough. You actually need to be able to, lift and process that stuff. So you need the hardware and computing power. And Jeff Dean at Google is instrumental in the TensorFlow project. Now, TensorFlow, from the data scientist's perspective, looks kind of like most other data science frameworks, except much more finicky and annoying to program in. You force your data into the thing with some fuss, hit run, out comes a recipe, off we go. And you could probably do that in any programming language subject to your degree of masochism. That's not the part that makes TensorFlow magical. The part that makes TensorFlow magical is the way it uses the hardware. It doesn't waste it. What would have not been enough hardware, would have taken much, much longer, is now fast enough that this whole thing is viable. And then there's also this little bit about specialized hardware. And somewhere around 2010, some researchers noticed that the calculations that you need to do for neural networks are very conveniently performed on hardware that was developed for an entirely different industry, which is teenagers playing video games. And that's why you hear GPUs this, GPUs that all over this neural network space. Graphics processor units just happen to be pretty efficient for this, and so those researchers realized, Jeff Hinton was one of them, hey, if I just grab a standard gaming console and hack that thing, I've got myself a supercomputer for $300. And that's a big part of the birth of this AI revolution. So you've got the hardware, you've got the specialized processing frameworks, now open sourced, so everyone can use it and contribute to it. You've got the huge, beautifully labeled data sets and the algorithms. And with all that, the future is here, and now we can actually use this deep learning stuff for real business applications like cat, not cat. That's how the Google Photos thing works, where you can type in cat and it pulls up images of cats. But it's not all cat, no cat. Airbus, one of our customers, is in the business of making high-quality satellite image maps. And it's not a very high-quality map if it's covered in clouds. So you'd do a few flyovers, and you'd want to remove the cloud cover. But see, the clouds change, so does the snow, but you want the snow, and you don't want the clouds. And so then maybe, imagine this task, my friends, you have to do it. You go into the photograph and pixel by pixel determine which one is snow and which one is clouds. Is that a job you want? I mean, maybe, I don't judge you. I prefer to spend my time a different way. I would much prefer to have a machine learning system identify for me, hey, these ones are possible clouds, approve or deny these changes. So now I'm more the supervisor of the system rather than the manual laborer who has to do it all by hand. In communication, I don't speak Chinese, but I'm assured that this is not a word-for-word translation. You can use deep learning to capture meaning, power things like Google Translate, or cutting out communication drudgery. I know how you love to actually type out those words that you use over and over again in your emails. You prefer to write the full thank you rather than th. Now, to cut out some of that drudgery, Smart Reply gives you those three options, and if one of them seems like what you were going for, you can select it, and if not, you just keep writing. So it helps you make your life less tedious. Playing games. This game-playing AI seems pretty frivolous, and yet the math powering this is pretty close to the math powering those self-driving cars. But you know, at Google, we let nothing go to waste. So we figured, how can we use this game-playing AI to do something useful? Let's give it a useful game to play. And the game we gave it was the game of Data Center. As inputs, it gets information about what's going on with the data center. Its joystick is the cooling system controls. And instead of that high score, its score is energy efficiency. Get the energy efficiency to be as good as possible. Now, before, the way to solve the problem of how can we make our data centers more efficient, it was a standard analytics approach where a bunch of analysts and a data science team would go and collect data and think about it and profile it really carefully, and then think some more, suggest some changes, test what that would mean, and they'd get maybe like a 1 or 2% improvement, which you shouldn't sniff at. A 1 or 2% improvement in energy efficiency in a data center is a huge thing. Huge cost savings and pretty good for the environment too. Now, when we gave this to AI, what do you think the improvement was? If you don't know the answer already, what would your guess be? 15%. I hear 15%. Bold, 15%. That's a lot of money saved. 15% going once. 15% going twice. Sold for 15%, except the answer is 40. Yeah, huge savings and an incredible reduction in carbon footprint. And there's so much more you can do with it. Have a look at all these different bits of inspiration, but I've got a different way to get you inspired as to how to get started. How do you find a machine learning use case? Here's what I proposed. Imagine that there is no machine learning. It's all a hoax. There's no AI, there's just a bunch of people on an island somewhere, sitting in cubicles behind computer screens, and you send them some information, like a photo of a cat, and they are going to con you and write back cat, and we're all going to pretend that that's the AI. Imagine that. The only way you can communicate with these people is to send them tasks by example. No instructions. You're not allowed to write instructions to them, but you can send them examples. If I allowed you to use this resource for almost free, and there were a lot of them, and they were very fast, you could really scale them up, what would you use these humans for? What drudgery would you cut out of your life? And as you're thinking about that, you're coming upon the right kind of applications for machine learning. But wait, you don't know how drunk these people are. So you can't just trust them with your important tasks. You need to check that they can actually do those tasks. And for that to work out, you need to be able to say what it means to do your task correctly. And if they make mistakes, which mistakes are worse than which other mistakes? And how would you like to score that performance? Because you're going to want to check whether this island can actually do the job for you. And if it can't, you don't want to hand over control of some important process to this thing. Now, you do see these creative applications like, hey, Drunk Island, write me a poem. And for those, you don't really know what it means to write a poem well. You kind of hope for something good to come out of there, but you're not sure what you're expecting. Well, for those things, you shouldn't really hand over the task entirely to the system. Instead, what you should expect is that it is just a way to inspire your human creativity. It's just going to mush up some information for you and propose something that looks like a poem. That's just some way of combining a whole lot of data. And you're going to look at this, and you're going to actually use your own judgment as the human creative, and you're going to ask, does this inspire me? Can we work with this? And if it doesn't, you're going to kick that island, tell it, hey, go do this a different way. Over and over again, until something looks like it's worth pursuing. And then you're going to do that trick that all these other folks do, which is you're going to put that out there on the internet and pretend like that was the only version ever. Look at the poem machine learning wrote for me. Machine learning writes poems, says the newspaper heading. It's actually you that's writing the poem. Machine learning is just jumbling stuff up for you in some haphazard way, like monkeys on typewriters, just a little better because it's finding patterns rather than doing it purely at random. But it's a way to filter human creativity. That's how you should think of those applications, where we're not quite sure what we're looking for. There we have it heavily interfacing with the human, and the human is at both ends of the process. And what about this other kind of application where you have, hey, Drunk Island, generate for me the face of a celebrity who doesn't exist. That application is a real application. That works. The technique there is called generative adversarial neural networks, or GANs, and it's all the rage these days. Here's how to think about those. There are 2 Drunk Islands, not one. Drunk Island number 1 is taught to figure out whether the celebrity is a real celebrity or it's some fake generated image. So it's a thing labeler that's doing a bit of truth detecting, which one is legit, which one isn't. And this second Drunk Island is supposed to trick the first one, generate images that get past the other one's defenses. And both of them learn together and both get better at their game as they battle it out in cyberspace. And by the time they're done, the tricker is good enough at it to trick you. And its output looks kind of legitimate. Still the same kind of components. And still for both of them you need to be able to say, what does it mean for the first one to succeed? What does it mean to correctly identify the face? What is the other one trying to do? If you cannot say that, you will not be able to use machine learning to solve your task. All right, why should you trust machine learning? We have a particular problem, as we move towards the AI applications, we're beginning to automate the ineffable. That means that we are solving things where we could not come up with the recipe. I don't know about you. I take a pretty positive view of my species. And I imagine that we are actually fairly smart creatures. And if the recipe were simple, and there was enough reward in it, I imagine just through sheer bloody-minded stubbornness, we would find a way to figure out and handcraft that solution. So if we are forced to rely on something like deep learning to solve it, and we can solve it no other way, I imagine maybe that's because the underlying recipe is now so complicated that it's too much for us to read and think about. There's a memory capacity limitation in here. And so if that thing is really complicated, you can't really expect to open it up and read the recipe and go, aha, well, that's how it's figuring out what's a cat and what's not a cat. If the pixel in the top right-hand corner is blue, then it's a cat. It's not going to be that simple. You're not going to be able to read it and understand it, so you're not going to be able to base your trust of it on the recipe. You're stuck. Now, what I propose is that that's not a great basis for trust in the first place anyway. Think about going on a new kind of airplane. An entirely new kind of airplane. A spacecraft, let's do that. New kind of spacecraft. And you've got two options for the spacecraft you're going to sit in. Spacecraft number 1, all the physics is written out exactly for how it works. All of it is available and you can read that thick stack of documents. Spacecraft number 2, no information on how it works, but lots and lots of information about all the previous flights that it's completed successfully, all the trials, all the testing conditions. Which of the two would you like to trust yourself to? The one you know exactly how it works, but it's never been tested, or the one that you don't understand how it works, but it's been tested thoroughly? Number 2, I have a strong preference for number 2. For a lot of our medication, we have no idea how they work, we just know that it does work. That's good enough for us, as long as we can be sure it works. I submit to you that that is a much better basis for trust. Checking that it does work. Knowing how it works, that's a pleasant extra thing. But checking that it does work, that's what you should be basing your trust on. And so the analogy for thinking through this stuff in machine learning is the professor analogy. You already know all this stuff because you've taken exams, and if you've ever set exams, even better. So let's have a quick look. You're the professor, and your student is going to take a calculus exam tomorrow morning. So the student has written, luckily, something down from the board to study from. There we go, an equation. I said no equations, and look at me lying. So the entire job of the student, the machine learning system, is to go from the inputs, the left-hand side, to the outputs, the right-hand side, correctly. And so this is what the student's going to learn from, going to learn really, really hard, and find a pattern that works. You can just turn the 8 on its side, and there you go. And I want to point out that in these data, where the student is learning, training, it works. This is correct. 100% accuracy. Now, at this point, would you go to the exam if you were the student? I mean, I've certainly taught some undergraduates who I think would have gone to the exam. I've had to grade their papers and cry a little. But you, my dear enlightened audience, you wouldn't just go to the exam based on this, right? What would you do? What do I hear? Try another one! Exactly! But there's an important difference between you and my student. My student also tries another one. They try it on the exam, where it matters. Whereas you have the wisdom to try it in the safety and comfort of your dorm room, check your understanding while you can still go back and adjust your model if you don't get it. So what you are doing and they're not doing is validation. That is what validation in machine learning is all about. A safe environment to try it out, where you're still allowed to go back because the stakes are not high here. A soft interim test. So let's try another one. Apply our model. We get performance, and turns out that's not how math works. And based on this signal, we then can ask ourselves, fine, should we go to the exam or should we go back to training? Then the student sits there and tries out all these extra practice problems that you, the professor, have given to them. And finally, at 3 o'clock in the morning, you, the professor, get an email from the student. Validation passes. I did all of the practice problems correctly and all of the in-class examples correctly. Please give me my A+. I don't need to go to the exam because I've done it. And your response is? Of course not. Now why? Why do you say that? You say that because your student could have contorted their understanding to the in-class examples and the validation examples and just memorized the whole lot. Maybe even without realizing that they'd memorized them. Just formed some recipe, some model that fits what they've studied. It doesn't generalize to anything else because it's just some crazy mishmash of the peculiarities of those examples that they worked with. And you don't know if that's what they did because you know they were allowed to retry both the in-class problems and the practice problems many times as they want. You don't know what kind of mad logic is going to come out of that. Memorization is possible there. And so you, as a wise professor, are going to say, absolutely not. I'm so glad for you, student, that you feel like you've gotten yourself to a state where you're confident, that things look good for you. But to really make sure that I don't release any really bad students out onto the world, you should come to the exam, and we'll check that you know it. Now, professors, you already know the requirements for the final exam questions. What has to be true about them? The most important thing. The student is not allowed to have seen them before. Because if the student has seen them before and knows the answer to them, the student could be memorizing. And your entire goal as a professor in this machine learning space is to make it so that your system cannot win by memorization. It cannot just do the look up the old answers insofar as I remember them and submit that as my new answer. And the only way you catch memorization is if you give truly new stuff for the testing. And that's why we have that separate test phase. Now, a lot of the pitfalls in machine learning tend to boil down to this learning and teaching thing. People just lose the common sense of learning and teaching. They don't think about that. They get so stuck in the math. So I implore you to think about this carefully first, and then you can think about the mathy stuff if you wish to. This is obvious when you have it spelled out for you, and yet you keep seeing these disastrous things over and over again that just are this. Obvious stuff. So let's look at these obvious things. First, you want a calculus-enabled student. You should use relevant examples. So the only thing that the student's going to learn is what's in the textbook you give them to study from. Just because you have textbooks doesn't mean your student is going to learn awesome stuff. What if those textbooks are Japanese-English vocabulary pairs? How is that going to help for calculus? Now, your student will be able to go and find patterns in that and learn it, but they won't do the task you need them to do. So we need to stop saying data with a capital D, like just having data makes things magical somehow. And even worse, data with a capital D plus the holy water of machine learning means it just works. No, data is just examples, information, and you are trying to express yourself by example. Your examples should be relevant. And so I say to Google engineers, if they're going near machine learning, they should consider tattooing this sentence on themselves. the world represented by your training data is the only world you can expect to succeed in. So you are in charge of what's in your training data. And if you pick a silly training data set, you're going to be able to succeed in the world represented by that data set. That's just not the reality that you inhabit. So your system's going to crash and burn in the real world. A classic example is one where you're interested in all your users, and the data that you choose to learn from is your users who inhabit an island near Antarctica or something, and nobody else. Those users might be something unique and special about them. They don't represent the whole world of what you're interested in, and you'll build a system that succeeds there, and then you'll be so surprised why it fails in New York City. That is your fault. You are supposed to open the textbooks, check that you like what's inside them. And a lot of this stuff about bias and fairness in machine learning also boils down to this. If you choose textbooks that are written, collected, curated in a way that reflects the biases of the humans who did that curation, your system's going to learn that stuff. And whose fault is that? Jointly, the author of the textbook and the professor who failed to check whether that textbook was something that you wanted to give to your student to study from. And so really checking your data, making sure that it's relevant, making sure that it describes the reality you want to succeed in, that keeps you safe. And it keeps you away from these surprises that people don't see coming, that they really should have seen coming. The other one is catching memorization. The whole job here is not to parrot, but to succeed on new stuff. Otherwise, we wouldn't need machine learning. And you fail at your one job if your system can beat your test by memorization. So please design that test so it can't be beaten by memorization by having a truly pristine dataset to test on. If the system has seen the dataset in any context already, it is not okay for testing. And the system is jointly the algorithm and the human working on it. Because the human knows some stuff about how this context works and kind of knows how to arrange all the pieces so that they can get a good performance. If the human already knows too much about that data set, they know how to beat it. A good data scientist is a scary thing. Okay, what is decision intelligence? You might have heard of decision intelligence. And before we go there, you told me you took stats courses. Let's do a quick review of stats. Remember the errors in statistics. Type 1 error. What is type 1 error? Incorrectly rejecting a null hypothesis. What is type 2 error? Incorrectly not rejecting a null hypothesis. What is type 3 error? Statisticians? Correctly rejecting the wrong null hypothesis. Let me say that a different way. Using all the right math to answer the wrong question. Type 3 error is the one that really plagues data science today. We've spent so much effort developing the math, developing the algorithms, getting the data sets, figuring out the code. And we've spent almost no effort figuring out how to ask the right questions and how to run an end-to-end applied process without messing up. And so what you end up seeing is you have these folks who graduate from their PhD programs and they know how to very studiously, very meticulously do the math correctly. And they cheerfully go down rabbit holes doing that math uselessly because they're answering the wrong question with it. Decision intelligence is about fixing that type 3 error. It is applied data science augmented by the other sanity-giving sciences, like the social sciences and managerial sciences, to look at decision-making as a whole. So why do businesses fail at machine learning? It seems straightforward. These algorithms have been around for a long time. Well, it kind of boils back down to this stuff. What they don't tell you about machine learning is that there are actually two machine learnings. The research machine learning and the applied side, the decision intelligence side. And these are as different from one another as building microwave ovens and innovating in recipes in the kitchen at scale. And for the research side, you're building general purpose algorithms, microwaves, for other people to use to solve their problems. And you're trying to build that better and better microwave, and you have these benchmark data sets that your microwave has to succeed on. And of course, if you want to improve on today's microwave, you've got to know how it works. Because how are you going to improve on it if you have no idea how it works? It's impossible. And so to train you, it's going to take many years, and it's going to take graduate degrees as well, probably, if you really want to make cutting-edge stuff. And of course you need the details of that wiring diagram. And that is how almost every course out there teaches it. It is teaching you how to make the microwave. Fair enough. When there's not many microwaves around, if you want to use a microwave, you have to build it yourself first. But it's almost like no one thought about the era where finally we would have warehouses upon warehouses of these things, all waiting, ready to go. And still, all we're teaching the world is how to build more microwaves. Who's using these microwaves? And how do we start using them better? I mean, if you're going to run an industrial kitchen at scale, it's not trivial. There's a lot to it. And if your entire plan for doing that is that the first people you're going to hire is a team of 20 PhD researchers who've been building microwave components their whole life, and they're supposed to figure out how to make gorgeous dishes to satisfy your customers, I mean, what could possibly go wrong? Right? And that seems to be the approach that businesses are taking these days. It's this over-focus on building and understanding the algorithms, and going beyond that and going to the applied side is it's a matter of hope. The entire strategy here is hope. You hope that someone will spend their whole lives learning every little detail about how to make a better microwave, and at some point will transcend and become a great chef. And okay, some do, and sometimes you hire such a person, and you have an amazing chef and a well-running kitchen. Please don't pat yourself on the back for good decision-making. You did not plan that. It was an accident that your amazing microwave engineer happened to be a great chef also. So we need to start thinking about training people to look at the applied side. Don't over-focus on the algorithms. It's a good reason why in this course I took all the nitty-gritty of what's going on inside the black box and I moved it to the very end, and I'm going to exhaust you all first so you don't stay for it. Because it's not that important to the application. If you want to be a researcher, then you need to know it. If you want to use these things, then you need to focus more on process. And you need to focus more on teamwork and decision-making, and that is what this course is more about. Machine learning, again, is about explaining yourself with examples instead of instructions. And the way you stay safe when you automate the ineffable is that you test carefully and make sure that it does work. So the statistician has your back. At the very end of the day, we're going to check that the student knows it. Okay? Who sets the exam, though? Who decides what it means to work? Who tells the system what to optimize for? Because the only levers that you have to communicate your wishes are your way of saying, this is what it means to do well, here's your score, and here are a bunch of examples you should learn from. The decision maker on the project is supposed to do that bit. Now, decision-making, as it turns out, is not something that you will pop into this world being fully knowledgeable in. It's both an art and a science. It takes some talent, but there's a lot of skill to it as well. And it is the decision-maker who's responsible for this stuff. Are our decision-makers today skilled? I want to ask you a question about workers. Which one do you prefer? A reliable worker or an unreliable worker? Which one is better? Reliable. Yeah? Any dissenters? Because I would say it depends. It depends on the quality of the decision maker. If you have a great decision maker, you want the reliable worker. You want the reliable worker who scales up really quickly and does what they're told, does exactly what they're told, and follows the instructions of that good decision maker. Scales up the intelligence of that decision maker. Unfortunately, something that's good at scaling up intelligence, machine learning, is also really good at scaling up stupidity. And if the decision maker doesn't know how to do their part, instead of good outcomes, you get terrible outcomes. And that all gets scaled up before anyone knows what hit them. And so there, with a bad decision maker, you want the unreliable worker. You want the worker that's not all in on the incentive function given to it by the decision maker, that instead wants to play with its kids and hang out on the beach and what was on TV yesterday and am I hungry, in addition to whatever they were told to do at work. Because all those unreliabilities, all pointing in different ways, people, you, unreliable workers, relative to machine learning, all of you kind of cancel out the badness of the decision maker a little bit. It's hard to scale that stupidity. Right? There have been cases in humanity's history where that got out of hand a little bit, but for the most part, you're the reason it's self-limiting. Machine learning, though, does what it is told, optimizes for what it is told to optimize for. And if the decision maker doesn't know how to ask, you have a problem. And that is why data science, machine learning, and AI future needs skilled decision makers. And needs good process here and teams who know how to actually carry this off safely and reliably. Decision intelligence is about wishing responsibly. And I think of machine learning as a bit of a proliferation of magic lamps. It's never the genie that's dangerous. But genie can be told to do fabulous, lovely things for the benefit of all of humanity. What's dangerous is the unskilled wisher. And not necessarily even the wisher who has some malicious intention. The wisher who doesn't think through what they're asking for. Who thinks it sounded good in their head and I'll ask it and that'll be fine. So here's a classic example. We use this in our machine learning training all the time. It's the parking lot example. Your business has a parking lot. 1,000 spaces in that parking lot. And it's in a pretty busy place. So at any given point in time, about 10 of them are empty, on average. And what you want to do is you want to have a big sign out there on the outside of your business saying how many empty parking spots do you have right now. And you're going to use machine learning. You're going to have a camera on the top and it's going to do some thing labeling for each spot. Is there a car in the spot right now, yes or no? So that we can put an accurate count. How many spots are available here right now? And then you're like, okay, what metric should I use? Accuracy sounds good. Yeah, accuracy is nice sounding. And how accurate should I ask it to be? They use 95% in all my stats courses. That seems like a good number. I'm going to require at least 95% accuracy and then I'll launch this thing. Who sees it? Anybody? I'm looking for the horrified expressions. Who sees why the business is about to go under? A skilled decision maker with the skills we're talking about here should see it immediately. How do you beat that requirement if you are trying to simply game that scoring system? If you have no honor and no virtue, like the board game power gamer that you never want to invite over, right, who wins every board game playing with their unfun strategies. If you want to look at it from that perspective, what's the way to win? The cheapest, ugliest way to win against that scoring system. You need to get at least 95% accuracy.
Get all the spots with the cars.
Just say they're all full. Because what's that accuracy going to be on average? 99%. On average, 10 are empty at any given point in time. So just by saying all 1,000 are full, you only get 10 mistakes out of 1,000. That means 99% accuracy. That beats the 95% requirement. It passes the exam. Here's the exam, it passes it. And off it goes, cheerfully, labeling 00000, and your parking lot dies. Now, whose fault was that? It was the wisher's fault, whoever thought that it was a good idea to use those examples and that incentive structure. And that's what we have to spend a lot of time thinking about. For an AI future, there's a lot of microwaves already. And we're so focused on building those well. And then we're a bit focused on the testing and the statsy stuff on the other side. We should be more focused on that even. But this first bit, what should we build? How should we check? How do we diagnose what we're wishing for? That we don't spend enough time on. And that's probably the most important bit. And that's how all your projects don't end up imploding. Now, to carry this off, you need to appreciate how crucial skills diversity is. This is a team sport. In fact, my least favorite question in machine learning is the one where you go, Cassie, describe to me what the ideal machine learning hire looks like. And I hate that question because it suggests that this is a one-person game. It really isn't. It's also not a game where you want multiple copies of the same person. Stereotypical computer science, machine learning professor type, you just get 20 of them and everything will be great. There is a real diversity of skills that is required to carry this off successfully. And if you don't cover them on your project, you're going to have a problem. And you might have them all represented. If you haven't thought through how to make them work effectively with one another, you're also going to have a huge problem. Things are just going to fall down the gaps in between these people. You need those perspectives, you need those decision skills, you need the data science, you need the social sciences, the managerial sciences, the reliability folk, the engineers, you need all of it working together. So, what does our future look like with machine learning? We are moving towards more application. We're moving out of the pure research era to the applied era. I hope that this also comes with literacy all around. Machine learning isn't for the select few, that everyone has a basic understanding of the core principles, and not how the nuts and bolts work inside the thing, but what it actually means. That it is explaining yourself with examples. We love democratization. That's a good thing. Everyone should be part of this. We're making it easier and easier for people to have that second mode of communication with machines. That's great. The tools are going to get easier, and they should. And I'm a big fan of our push to make them easier. There's no honor in doing something the hard way when there is an easy way. And those of us who can apply our engineering effort towards making the easy way easier, our hard work is well spent that way. I expect that there will be a lot more emphasis on giving everybody tools. But now that everybody has tools, now you can scale up either the intelligence or the stupidity of their application. How do we think through doing that well? Well, we should think of it in terms of process and interdisciplinary stuff. That's what this course is going to be about. It's going to be a 12-step course. All my courses are 12-step programs for taking an idea from conception to having it running successfully in production. And we're going to use a kitchen analogy to also set our expectations for how this process is going to look. So we'll dive into the process after the break, which is coming in 3 minutes, but we'll set our expectations here with this analogy. Say you want to create a recipe for sausage. And there may be vegans in the audience, so we will make it vegan sausage. And the sausage is not only vegan, it must be low-calorie, gluten-free, sugar-free, and Michelin star compatible. The goal. Our goal is to innovate in the kitchen with recipes. We can afford all kinds of microwaves and whatnot, and we have that in our lovely kitchen. What is the process actually going to look like? Do you know how long it will take to get you that sausage? Can you look up the solution in a textbook and really think through the biochemistry one time and just do it once? Are you even sure that your endeavor will succeed? But how will you go about it? Well, the same way as how you go about machine learning. So let's say a preview of these 12 steps. And of course, I love 12-step programs here way too much. I force all my courses into them, and this should really have been 13 steps, so we started step 0 to make it work. So our steps, a preview of what we're going to dive into in detail after the break. Step 0 to 1, asking the right questions in the first place. Like, what are we trying to make? Which customers are we trying to please? What does it mean to succeed at this sausage? Do we have standards? That kind of stuff. 2 through 4, getting the right ingredients. And when we talk about getting the right ingredients at scale, there may be a lot to it. We're not going to, because this course is not a data engineering course, I'm not going to cover that in tremendous detail. I want to give a nod here to how hard this actually is at scale in practice. Data engineering is not a trivial thing. I mean, at small scale, it's, can I download the spreadsheet and open it on my laptop? Yeah, sure. It's just when the scale gets big, it becomes quite a sophisticated discipline in its own right. So we're getting the ingredients, we're sourcing them, and ingredients matter, right, chefs? They matter a lot. Just because I have ingredients, I'm going to be able to have my vegan sausage. True? No, certainly not true. Steps 5 through 7. Tinkering in the kitchen, trying different stuff, and iterating towards a better recipe. 8 through 9. Actually, maybe taste it first before you subject your customers to it. So, a soft taste test, validation, the chefs in the kitchen are doing it themselves. The testing is a much more rigorous, strict process of should we actually even be putting this in front of customers. 10, streamline your kitchen so you can start serving this. Your productionization step. Because your thing that you made in a bowl is just a prototype, and if you're actually going to do this seriously and at scale, you need to think about rearranging the kitchen. And that is going to be quite an investment, which is why tasting it carefully beforehand was kind of important. You need to know whether it's worth arranging your whole kitchen and menu and everything else to be able to serve this dish. Then, actually try it on some customers first, as produced by this streamlined process of yours, to make sure that the customers like it enough for you to make it a permanent fixture on your menu. Don't just add it to your menu and hope. There might have been some bugs introduced into how you arranged your kitchen. Or maybe your customers just hated the dish, and you didn't realize that because your prototyping process didn't reveal it to you. And then finally, it's going to be the gift that keeps giving. You're going to have to maintain and monitor this thing in perpetuity, and your world is allowed to change. You were expecting that you can source rice, and suddenly there's no more rice in the world. Well, what are you going to do about it? What's your plan? Now, hope is not a strategy, you need a plan, and how do you think through that planning? And that's what we're going to cover after the break, and I'm here for questions. So let's dive into our 12 steps, starting with step 0. Should we even be using machine learning? And to think about this, we need to be fully aware of what machine learning is about, which is label all the things. So we are doing this in order to label things. If we cannot even think of what things need labeling, we're going to have a problem. So you need to think about which things you need labeled. That is your first step. So what I never want to see is we're going to use machine learning, and let's find some place where we can shove machine learning because we have the goals of using machine learning. Don't start there. Instead, think about what it would be nice to have automatically labeled. And then maybe machine learning is the thing for you, maybe it isn't. So articulate the decisions that you want coming out of the system when it is fully operational. And you don't need to have any kind of specialized experience to do this. Just imagine it's already functional and it's outputting some labels. What are these labels? Are they labels like cat, not cat, or is the wine good or not? Or maybe a dosage in milligrams, an amount in dollars? What group does this thing belong to? So the sort of label that you want is going to determine what kind of machine learning system you're looking for. So let's learn about some machine learning jargon to do with labels. First off, if we are looking at binary or multi-class labels, things like cat, not cat, or cat, dog, bear, giraffe, elephant, etc., then we call that a classification task. If the label is a number, we refer to that as a prediction task or a regression task. Now, I'm saddened by the use of this jargon of regression because that means all kinds of other things in all kinds of disciplines, and especially in statistics, which is far too close for comfort. Regression refers to a certain kind of algorithm that has to do with putting lines through stuff. So I prefer to say prediction. In fact, prediction for all of it is fine. But just to introduce you to standard jargon so you don't get confused, this tends to be the first few minutes of every machine learning course. Let's just orient ourselves. Classification if there's categories coming out, and prediction or regression if the label is a number. Then you want to think about your learning type. These are 4 classic learning types. It's not all of them. Let's take a quick look at these ones. So first off, supervised learning. And some jargon even before the jargon. When we have a data set in the typical form that we would lay it out if we flattened it, the examples that we're going to learn from are in the rows. And we call them in machine learning instances. Here we have 4 instances. For each one, we have the correct label, also known as ground truth, handy. The label is what I am going for, so you might also see that called targets. That's our correct answer. And then finally, feature. This is a bit of a head explode moment for jargon because all of you are from all kinds of different fields, and I bet you have the word feature in your field, meaning something completely different, but whatever. Machine learning helps itself to your jargon, and here a feature is something that we know about our example that we can put into the recipe to learn from. So in other disciplines you might see feature called variable or predictor or attribute. What are the features in these data that I have given you? Can anyone tell me? All I have given you is the information about what color the pixels are. Pixel this one, here's its red, green, blue. Pixel next one next to it, here's its red, green, blue, and so forth. So this is a very short, very fat matrix. 4 rows, lots and lots of columns, all about those colorings. And you're going to be my machine learning system now, and we're going to do a bit of transfer learning. If this was the only visual information you have ever received in your life, you would not be able to succeed on a matrix shaped 4 by too many. But because you already have a trained vision model in you, it only takes a small adjustment for you to be able to perform my task. So, cat, not cat, not cat, cat, and please learn to classify this one for me, please. Not cat. If you said anything other than not cat, you will fail my testing, and I'm going to go with a different system. So again, supervised learning is where, for every example I give the system, I have the correct answer handy. Now, let's look at unsupervised learning. Here I have for you 6 instances, and your job is to put them into 2 groups using whatever rule you like. Just put them into 2 groups for me. Anyone? Tongue out, not tongue out. Great. So what are the labels that are going to come out of this system? Are they tongue out, not tongue out? Or am I doing some trickery? The labels that are going to come out are just like A and B, or 1 and 2. They have no human interpretable meaning. The tongue out, not tongue out, is the recipe that we're going to use to separate them. The output is just like thing 1, thing 2. And so, all right, 1, 1, 1, 1, 2, 1 is what's going to come out, 2 groups. Some other way to separate them. Sitting, standing, okay. So 1 or 2? You're responsible for this, so you tell me. 1, okay, how about this one? 1, how about this one? 2, this one. 2, this one. 2, this one. 2, see? Easy. Any others? cat selfie, not cat selfie. I love this one. All right, so what do I hear? 1, 1, 1, 2, 2, 2. Okay, so this happens every time with every audience. You ended up separating these things. I didn't make it sound like there were right answers and wrong answers, but I'm still deeply disappointed in you because here you are saying tongue out, not tongue out, cat selfie, not cat selfie. When I, as the proud mother of these 2 individual cats, really hoped that what you would tell me is here is cat 1 and here is cat 2. But instead, look at you with your sitting, standing, and all the rest of it. And every other audience does this as well. Actually, one audience came really close to separating them, said ugly cat, pretty cat, and I was like, whoa, 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 we're going to have to talk about this later. So here is Huxley, and here is Tez, 2 individual cats. Now look, if we had done supervised learning, and I had given you a few examples of Huxley and a few examples of Tez, of course you would then go and label things that way. But I didn't tell you what I was looking for. I just said, here, take all this stuff and split it into different groups however you like, or by whatever the rule is that is part of your internal algorithm. Now, that's the thing with unsupervised learning. If I don't tell you what I want from you, I just tell you to put things into groups, I get what I get and I don't get upset, right? It's no guarantee that the system is going to come up with what is actually dear to your heart in this example. Just splits things into different groups. And so what you will do with unsupervised learning is you will look at the results and you'll ask yourself, is this something I can use for anything? And if not, kick the system and ask it to split them some other way and keep doing that, and maybe nothing dear to your heart ever comes out. It's just separating them into groups. Now there's another little cautionary tale here. See, if you are like me, these cats, they're where your heart's at. And whenever you look at photos to do with them, you see individual 1 and individual 2. And you expect the machine learning system to be looking for that because it's precious for you. And then, let's suppose the system does give you these splits. 1, 1, 1, 2, 2, 2. The human foible here is to think, look, machine learning is separating Huxley from Tesla. You'd think, right? Except maybe turns out that what it's doing is asking radiator, not radiator. And all the photographs that we took of the first cat didn't have radiator, and all the ones that we took of the second cat did. Or maybe the first set of photographs was all taken on a sunny day, and the second set was all taken on a cloudy day. Well, how do you know that this rule has any human interpretation? At this point, you don't, and you shouldn't, and you should stay cautious. If you want to ask whether there's that story in these photographs, you need to make sure that you design an exam for this system with new data, where if the system passes that exam, the only interpretation can be that the story is true. So the exam had better have cats taken on the same weather conditions across a variety of locations in the apartment. And then, if it still separates them in this way, then you have a bit of evidence to start talking about perhaps it is finding Huxley and Tesla. I don't trust that because this is what's dear to you, it is also doing this. And the other little cautionary lesson that we get here is you, humans, you're a pretty good algorithm for this. I want you to remember that you didn't find what I cared about. You didn't pull out the 2 cats. So a data scientist going about applied machine learning, expecting that the algorithm is going to give them what they care about, well, they are possibly in for some disappointment. And don't think things like, machine learning is better than humans, so it can do things humans can't, so I expect it to work here where humans will fail. Don't expect the reverse either. Oh, humans are so good at all these tasks, they're going to get everything I care about. In fact, this whole testing thing, it holds not only for machine learning, it also holds for stories that humans come up with based on data. When you look at some data and you form some opinion, if you want to be able to take that opinion seriously, design an exam and check that that little recipe that is your opinion actually works on the new situation also. So unsupervised learning is the search for patterns. This is where you don't have any labels, and some keywords here are data mining or clustering. Then, semi-supervised learning, exactly what it sounds like. This is where some of your data are labeled and some are not. So imagine that you're really excited to build yourself a cat-no-cat classifier. And of course, for that you need data. So you download 1 million images, you grab your 6-pack of Red Bull because you want to do supervised learning, and you start labeling them as cat, not cat. Cat, not cat, not cat, cat, not cat. And by the time that you are about halfway through, exactly. Curiouser and curiouser. And then it's 3 a.m. and you have labeled 300,000 images, and you can stand no more photographs, and there's 700,000 to go. What can you do? Well, the first option is the most pragmatic. Remember, our goal is to make it work. Let's see if we can get a recipe that actually works. So why don't you just try it with the 300,000 first and see if you can get success there? No one said you had to label all 1 million of them. See if 300,000 can be made to work. So for now, throw away those 700,000 and see what you can do with what you got. If that is not good enough for you, then you don't have to go straight for labeling all the others. You might be able to squeeze some goodness out of the unlabeled photographs. I hope your intuition already tells you that the unlabeled ones are worse as data than the labeled ones. Makes sense. But they're better than nothing. And so by combining the two techniques, essentially, you might be able to do better without having to label everything. And that is the nature of semi-supervised learning. So you do that if you couldn't get supervised learning to work. I want to point out that we are never here by choice. We're here because time is limited or budget is limited, and we want everything labeled because supervised learning is the easiest learning type. If you can frame your problem in terms of it, do it. Sometimes we just don't have the luxury of everything labeled, so we're forced to rely on these other complicated techniques. So this is a blend of the previous two, where you've only got some of the correct labels. Then, finally, reinforcement learning. So in our Atari slider game, when we ask the thing to optimize its score velocity, we're giving it a little bit of reinforcement, some reward or punishment signal, but what are we actually asking it to learn? What are the labels that we are getting as output? If it's trying to output the score, why not just set the score to infinity and call it done? It's not trying to output the score. It's trying to output the movement. But it's not just working with one movement. It's dealing with whole sequences of movements. The thing that really separates it from supervised learning is that there isn't immediate feedback for every individual move. When we move our little paddle left, for that move, we don't get immediate feedback. We don't know if that move is the one that's going to be responsible for us dropping off the screen later. There's some element of delayed feedback, and you're dealing with whole sequences of stuff. And you need to go to reinforcement learning, and that is, I'm sorry to say, harder than supervised learning. So you can diagnose your task. If you're dealing with sequences of actions, there's some notion of reward or punishment, there's some notion of score, there's delayed feedback, so you don't get an immediate signal for the total goodness of every little movement. And the system influences its environment and input. So there's that last bit. The actions that the system takes also influences the data that it will be seeing coming in. So if you have all these, you have reinforcement learning. Reinforcement learning today is hard. You are going to have to be buddies with the researchers, and if you read research blogs, they'll tell you the gory truth of what's actually involved here, which is a lot of failure. And they will, there's a blog I love by a Googler on this topic where he describes just, it's best to just think of this as a demon that hates you. and then you'll feel better about it. It's beautiful when it works, most of the time it doesn't. So we'll focus on supervised learning for the rest of this course, but now at least you know how to diagnose whether you have this one. Just very researchy today. Okay, so if you cannot even imagine what sort of decisions or labels you want, please stop. Machine learning is not for you, not yet. Maybe you want some other area in data science, like data mining or descriptive analytics. Actually, let's talk about what is data science even. I think of data science as the discipline of making data useful, and within that discipline, you have statistical inference, you have data mining or descriptive analytics, you have machine learning, all under that umbrella. How do you figure out which one is which? I mean, some people will joke that machine learning is just statistics on a Mac and stuff like that. I quite disagree with that. Let's see if we can figure out a taxonomy. So one proposal, I hope you're enraged, I am, is based on the tooling. No. You can, with some creativity, use all of them for all of them, especially since we at Google are doing things like making BigQuery able to do ML for you. So now you can have machine learning right in SQL. So that's just confusing if you try to do it based on tooling. So instead, how about not that? How about the algorithms and math stuff? Actually, a good data scientist with cunning and the right level of stubborn perversity can use any algorithm for any of these things. It's not the algorithm that determines which is which. So instead, I propose this separation. None, many, few. Any guesses what none, many, few refers to? Data points? Whoa, hang on. How do we describe when you don't have any data? I think we'll have a problem. The number of decisions, exactly. Here in data mining and descriptive analytics, we are not making any decisions. We are simply trying to get inspired from data. We're having a look at what is here. We're learning what is here, and we're not taking it too seriously. We're not learning anything beyond what is here in our data. In machine learning, we are going beyond our data in the sense that we are trying to make a recipe that's supposed to work on new stuff beyond the data that we have on hand. And statistical inference, statistics for short, is for making one or a few careful, important decisions where we don't have the correct answers until we've made the decision, and then the universe punishes us or doesn't. So we are carefully working with making a few important decisions. And the whole discipline together, data science, you can think of that as the discipline of making our data useful. Let's have a flowchart to diagnose which one we're dealing with. So our first question should always be, are we making decisions? And if the answer is no, descriptive analytics, data mining, that's the one for you. And if you want those fancy algorithms, you can use machine learning algorithms for descriptive analytics. You can use statsy stuff like t-tests for descriptive analytics. It's just the way that you use them is very different. You don't worry about the philosophy behind it. You don't worry about whether it's right or wrong. You quickly apply a whole lot of different algorithms, and you see if anything seems to inspire you. And whatever inspiration you get, you just interpret that as, when this math is applied to these data, the combination together gives me this result. What does it mean? Nothing yet. So if I'm going to go for meaning beyond the data, then I have to look at one of the other two areas. So descriptive analytics in some sense is like a printer. Let's take this image and see what is here. It starts out as a thing on an SD card that we can't make any sense of, so we can't get inspired from it. Well, let's look at it and see if there's any inspiration. And just like with photographs, you should know that if you are walking down the street and you stumble upon some image lying on the pavement, you shouldn't pick that up and learn all kinds of marvelous things beyond that photograph. Data science is essentially Photoshop. You can do benign things with Photoshop, like have a look at what is here. You can also slice it and dice it and make it tell any story you want. So if you want to use that photograph for decision-making beyond what's in the image, you need to be in control of how that image was taken, and you need to be in control of what has to be in that photograph in the first place to sway your opinion. If you just found some data lying around and you looked at it, please don't take it too seriously. All it says is, this is what happens to be in this particular image as it is sitting in front of me. And that could be inspiring. Just don't learn more from it than you should. Next question. If we are making decisions, can we just look up the answer? So maybe our decision is directly based on last year's revenue figure. Let's look up last year's revenue figure and off we go. Well, back to descriptive analytics, just look up the answer. You're dealing with facts. But if you can't look up the answer because all the data you care about isn't available to you, like you care about tomorrow's data, and you only have today's data, well, then you have to deal with one of the others. So then the next question is, how many decisions? And if your answer here is many, machine learning is what you want. And that is where we build a recipe out of today's photos, out of this pile of photos, that we might use for determining whether we have a truck in a photo we take tomorrow. We're making a recipe out of our old data to succeed in new situations. If the answer is few, next question is, are we scared? Is the decision important? Because if the decision's like, hey, based on what's going on in fashion today, should I buy a blue t-shirt or a white t-shirt? Please don't waste your PhD statistician's time on this. Get inspired and go buy your t-shirt. It's only when the decision is important, when it matters, when you want to make it carefully, rigorously, in a risk-controlled manner, that you want statistical inference. And in order to purchase that rigor and careful control, all the conditions need to be carefully put in place. You don't get those guarantees just by sort of math on some bad data and off we go. Everything has to be done carefully, especially the framing of the conditions at the beginning, which the decision maker makes. So what's a really careful risk-controlled decision that we might want to make? Should we launch this machine learning system we've built? This is a system that's important. If it doesn't operate correctly, we'll lose all our users. Should we release it? Yes, no. That seems like a pretty important decision that we might want to verify with statistical inference. So I kind of think of machine learning as make it work, and statistics as now that you think it works, does it? It's about coming to conclusions beyond our data safely. And yeah, don't forget data. As part of step 0, we're still talking about step 0, machine learning just simply does not work without data. And this should seem obvious now that I've talked on and on about how this is expressing yourself with data, with examples. And yet I still end up in these consultation situations where people ask me, like, if the thing can know that this one is from Canada when I have never given it any information about Canada. You're like, well, if there's nothing to learn from, and if you have no examples of what's relevant, then how are you possibly going to make up the idea of Canada out of nowhere? You can't do that. And then, even worse on that one, I was like, so what are these objects that you have information about that you're trying to predict what country they're from? They're like, we actually don't have data on them either, we just have the country names. I hope that you won't be in the situation of trying to proceed too far with that with a straight face, right? You will see why that's a problem. You need the ingredients to learn from, otherwise There's nothing to base your recipe on. At best, it will just be predict the most common country in the set, like we did with our regression example. We just use the average calories every time. Same here, it'll just give you most of them are from this country, just keep repeating that. And if it's never seen Canada, it's not going to make Canada up for you. You need the data to learn from. So if you know you don't have access to data, you don't have access to the hardware that's going to move the data around, fix that first before you go to machine learning. Alrighty, step 1, set your objective. And I hope you've been noticing that the team members change in each of these chapters. So here our main players are our decision maker and our domain expert. Now, setting an objective can be nuanced. Which of these is the good behavior? Oh, come on, which one is it? The one I'm looking for is it depends. What does it depends on? On the owner, the decision maker. What were you trying to get out of your dog? Do you want a sheepdog or a police dog? Because if you wanted a sheepdog, this is probably not the good behavior. Now, when should you be answering this question if you are the dog owner? Yeah, before the training, when the dog is a puppy, maybe even before you got the puppy, you should say, aha, what I'm going for here is a police dog. And yet, for some reason, teams will try to do this much later in the project, after algorithms have been done on some data for no particular reason. Now that is just like putting the poor dog in the basement with food and water, leaving it for 5 years, and then opening up and saying, so how's my sheepdog coming? It is not going to work. Now, you don't need to know how the dog's brain works in order to start training it towards being a sheepdog. You don't even need to know exactly how to do that training to start answering this. The first goal is to say, well, what's the goal? Now that we know we want a sheepdog, once we've made that decision, we can start looking into how to get the sheepdog. The first question is, what are we actually trying to do here? And it's amazing how often this is not the first step when people try to apply machine learning. Things crash and burn when you skip this. So let's do a quick example, learn some basics with cat classification. So we're going to build a cat classifier, and we have a little guide here. This is a pen and paper step. You can do most of this step 1 thing with pen and paper. You don't need special expertise. You don't need to be a mathematician or a programmer. Anyone with common sense can do this. So what's thing 1? Write down the outputs or labels for our cat classifier. May I have some suggestions from the audience? What should it output? Cat, not cat. Very nice. Couldn't have said it better myself. Fine, what's next? Consider mistakes. What mistakes can it make? Now, this is a very simple setting, so there's only 2 things that can be true. Cat, so you can see him in there, or not cat. And over here, the machine learning system only has those options. So if there's a match, we call that a true something. If there's a mismatch, the system's being false with us. We have built the system to be very excited about cats. And so when it thinks it sees a cat, it goes positive, positive, I got you a cat. Which is why we'll call that a positive event, and no cat, no, negative event. Now, of course, sometimes it goes, I got you a cat, and it's just seeing things. Mistakes are possible. So putting that together, we get the standard jargon in classification, the event names here. Next, assign project scoring. Figure out how to score many, many decision outputs and expect that this system will make mistakes. So imagine it has made some mistakes. Which mistakes are worse than which other mistakes? And this is about lots of outcomes. You're not going to use machine learning to just make 10 decisions for you. We're talking hundreds, thousands, millions, billions, that sort of scale. So it's going to have made lots of decisions. How would you score different combinations of those outcomes? How were you going to think about this? Well, first off, how about you use a little brainstorming tool? Why don't you imagine that 100 such decisions have been made, and there's some of every kind of good and bad outcome, and you tally up the counts out of 100 of each possible outcome. You just make some numbers up in here that should sum to 100. Are you confused? If you're confused, good job, you have named this thing. Its name is a confusion matrix. And a confusion matrix simply shows you exactly that. The outcome counts all the total number of times that each situation has happened. And you're going to use this for brainstorming. Confusion matrix, what a cool name. And then you realize it's just this? Like, seriously? Just a 2x2 table of what happened versus what should have happened? And then you realize that this is all of machine learning. The names are just so fancy. And then when you look at what's under the hood, you're like, are you kidding me? I was intimidated for years by this. And it's also quite funny, some things have been named both by statisticians who love the thing to just be called exactly what it does on the tin, and by machine learning folk who love the real fanciness. And you can kind of even tell who did the naming just from the name. Confusion matrix, neural network, artificial intelligence. Maximal margin classifier. Anyway, yeah, actually, if statisticians had named machine learning, we probably would just have named it thing labeling with examples. And can you imagine the industry getting all excited about, like, today the new hot thing in the industry is thing labeling with examples. Let's all go to a conference on thing labeling with examples. It's sold out in 11 minutes. Machine learning. Anyways, grumpy statistician right here. So what's the score? Well, the score is up to the decision maker, and there's lots of options. It comes down to what is important to the business. The decision maker chooses this. This whole thing, decision makers, see it as a board game that you are making. How do you want to score better players versus worse players in your board game, the Solve This Problem board game? Which outcomes are worse than which other outcomes? That's up to you. And let no nerd ever bully you on this. Because the machine learning research folk, they work on building the algorithms, and there's certain things to do with the algorithms that make them like various scoring functions. We'll talk about that shortly. It doesn't matter what scoring functions they like. What matters is what is important to your business. And that is how you should evaluate the performance of your system. How well does it deliver on what you have asked for? So please ignore all that stuff. It might come at you, and I'll explain to you why it might come at you. And seriously, just go with your heart. How do I want to score this? And remember how important it is to pick a metric carefully. We looked at that parking lot example. Picking a bad metric can tank your business, or worse. So they were going to ask about the various types of mistakes. They're just going to see which one should get a worse score than which other one. So they're going to imagine that 100 photographs were classified, there were some mistakes. What's worse, this situation where we made up a bunch of cats but we didn't miss so many, or this situation where it's reversed? How differently do you want to score these things? And by searching your soul a whole lot, you come up with a scoring function which we'll call the business performance metric. So let's create that performance metric. And there are a lot of options here. Not only these, many more, but here are some classic ones. So let's learn these classics. So accuracy, precision, and recall are the ones that you'll find in many 101 courses. Let's look at them. But before we do that, I need you to help me classify these images as cat, not cat. So everybody shout, just to wake yourselves up. Cat, not cat. 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 Not cat. Cat. Not cat. Not cat. Come again? Big cat is not an allowable option. We said at the beginning, that's why we did this at the beginning, cat or not cat. Big cat and maybe cat aren't allowed. you see now why the decision maker is so important. The right answer here depends on why the system exists and what we're trying to achieve with it. And I guess I'd better fill those big shoes for the purpose of our example. So I'm going to tell you that the system exists as a pet recommender. And whenever it says cat, it should be saying cat about something that's from the cat family, which in its standard adult form is safe to cuddle. Not cat. If you're still saying cat, take out more life insurance. Okay, and then we imagine machine learning has a go. Oh dear. Thanks, machine learning. So this is where it says not cat, that's where it says cat. Let's compute accuracy. That's simply how many did we get right. So we got 3 right out of 8. There's our accuracy. Let's practice saying these labels out loud. This one is true positive. How about that one? Allow me to show you how to speed yourselves up. Don't try to say it in one hop. True positive, false positive, whatever. Instead, did it think we got a cat? Did it get it right or not? Let's start with the second one. Did it get it right or not? That's false. Did it think it found a cat? That's positive. False positive. False positive. True negative. Say, don't think of them together. True. Not cat. Negative. False negative. There you go. And so when you are fluently showing off that you are totally cool with this whole classification conversation that's going on in the meeting, you'll use the separate them in your mind first thing to ramp up your fluency. Okay, let's look at the other metrics. First, precision. Precision is the fraction of actual cats among the cats that the system found. So in order to do that, in order to compute that metric, let us ignore all the things it didn't find as cats. Boom, gone. This is our denominator. All the ones it presented to us as cats. Of them, how many were actually cats? 2, giving us a precision of 2 out of 5, 40%. Recall has the same numerator, different denominator. Recall says, of the things that were there that were actually cats, how many of them did it return for us? In order to compute it, we need to know what was actually a cat here. And that's those 4. And of them, how many did it give us back correctly? 2 out of 4, giving us a recall of 50%. A different metric. Now, whether you'll be in more of a precision mindset or more of a recall mindset depends on your application. So let's brainstorm. You're going to tell me more precision or more recall for these 2 examples. So for the first example, you are busy people, yes, everybody? And you read, everybody literate, yeah? Okay. I posit that there are more books in existence that you will enjoy than you could read in all the spare time that you have. Yes? Happy? Okay. So you want to build a book recommender that is going to suggest to you what to read. Suggest to you that you like it, don't like it labeling for books. Will you be in more of a precision mindset or a recall mindset? What do you say? I'm hearing precision, and that is correct. If you want a recall mindset, you're saying, I need an exhaustive list of every book that I could possibly like, and I'm willing to accept duds also. Now, who's got the time for that? Come on. Precision is a way of saying, hey thing, don't waste my time. Leave things out. Leave out books that I would like. But what you return for me, let that actually be good. That's what precision is saying. Hey, let's try another example. When we're not reading books, what's our other favorite weekend activity? Robbing houses of jewelry. Now, when you are robbing a house and you have a big bag, are you in a recall or precision mindset? If you're saying precision, you are going into that house with your jeweler's magnifying glass, and you are checking every item Is it valuable or not? Because you'd better not get any costume jewelry in your bag. Is that how we rob houses? No, you're flinging everything in there because you don't mind getting the duds in your bag. You want to make sure you don't miss out on the diamonds. You want to make sure that of everything that was valuable in this house, you got all of that. And if some plastic comes along for the ride, you're cool with that. That is recall. And so, again, depends very much on your application which one you want to go for. To summarize, a system with high precision is going to leave good things out. But what it returns is of high quality. A system with high recall is going to give you a lot of duds, a lot of plastic jewelry, but it returns most of the good items that were there all along. And you don't have to go for one or the other, or even accuracy, which is all mistakes are equally bad. Hey, there's all kinds of crazy blends you can go for. There's something called an F measure, if you've heard of that. That's just a way of balancing precision and recall. I care about them equally, so that's the harmonic mean between them, whatevs. Figure it out. You are allowed, as business decision maker, to choose what is important to you, to your business problem. And let that be the metric you pick. What is optimize? If I talk about optimizing a function, what does that mean? Well, essentially, that is about picking the parameters or values to fill in into our recipe that do the best job of achieving what we're after, in this case, a taste score. So maybe we have many different ways that we could make soup, many different options for how much salt to put in and how much onion, etc. And so we would figure out what is the relationship between these potential values and the taste. And instead of having to individually try every combination in order, we would have an optimization algorithm tell us, boop, go for 2 teaspoons of salt because that is where you get your best value for the taste. And similarly, in this machine learning setting, there is a score that the thing is trying to optimize, and it's going to try to figure out where to set our settings so that the score is highest on the data that we learn from. And you're going to see that in action when we look at the black box section. So essentially, optimization is all about figuring out what the particulars in the recipe need to be so that our performance is as good as possible. I forgot I had this slide. So, optimization boils down to finding values in the recipe that give our best metric performance. And ideally, we would be working with the metric that the business decision maker cares about, but beggars can't be choosers. We don't feel like reinventing the wheel and rebuilding an algorithm from scratch. So we're going to take an existing one when no one asked us what metric we wanted to work with. And so we will then be optimizing some other function. All right, so what's next? It says here, think about the loss function. At a loss as to what a loss function is? Well, look. Our business decision maker just made a performance metric for scoring the system. Ideally, that is what the algorithm would use for learning how to do good behaviors. Unfortunately, that algorithm is not something that your team custom made. It's something that some researcher already made for you. It's already prepackaged, and it was made long before anyone knew what your particular business application was going to be. And inside that algorithm that you get off the shelf, in there is already a performance metric encoded. That thing is called a loss function. So that's the actual function that the algorithm is going to work with, because no one asked the business decision maker what they wanted when the algorithm was made. And it's called a loss function because machine learning folks need to rename everything. Before they came along, we used to call them objective functions. And that's because the objective could be positive or negative, but they take a very sticks are better than carrots approach. So they term the scoring of the board game in terms of errors and how much we want to penalize those errors or mistakes. Yeah, could always put a minus sign in front of it, whatever. So it's generally framed in terms of computing the badness, and the system is trying to bring the badness down. Less loss is better. So this is the function that's operating inside the system, and it is different from your business performance metric. And this is what I mentioned earlier. Don't be bullied by those researchers who tell you that your business performance metric should be a loss function. I've seen this so many times. Stat 101 says RMSE is a great choice for a regression problem, so your business performance metric should be RMSE. Your business performance metric should be whatever your business cares about. And so effectively, you will end up with two functions in operation. One that the system is going to optimize, and one that you actually care about. Now, surprise. If they're moving in opposite directions, machine learning will hurt your business, not help it. Which is why it's a good idea to think about comparing the functions. So, take your performance metric, let's say ours is accuracy, and compare it with a classic loss function, and see if they kind of align. So, a classic one you see here is called cross-entropy loss. Guess who named that? It sounds fancy, and it comes with an equation that has logs in it, oh my goodness. Or if we say it simply, are your ones near 1? That's what that function is doing. And you don't even have to read it. If you're lazy, there's an even easier way to compare it than to look at the formula of the one, look at the formula of the other, and math on them. You can simulate. Simulation's like the best thing in the world. I loved simulation before it was cool, because you needed the computing power, and really early on you'd have the lazy stat student that's like, hey, you could just simulate everything except like it takes all weekend to run, and now it takes that amount of time, and now everyone's getting on board with it. You should all simulate all the things. Okay, so let's simulate the comparison. So what are we going to do? We have implemented, we go to some package, R, Python, whatever package that calls itself cross-entropy loss, whatever, cool. And we don't even have to read the formula. We've got another one that says accuracy. We simulate a fake data set. That random, fake one. Fake outputs. Cat, not cat, cat, not cat, whatever. And then the truths. It was actually a cat, it was actually not a cat, so forth. And then we score it with this function, and we score it with accuracy. Okay, so we get a pair of scores. And then we put it as 1 point on a plot. And then we do that again, and we do that again, in a loop, lots and lots and lots of times, until we get such a thing. And now we will look at this glorious mess. We do it over different conditions, different data set sizes and so forth. We get this glorious mess, and what does this say? So, accuracy. Is accuracy better or worse as there's more accuracy? Better. More accuracy is better, so this direction is better. Okay, how about a loss function? Does that get better or worse in this direction? Better. So what are we seeing here? This one is, when this one is going better, this one is also going better. That is a wonderful thing to see. They are not countering one another. Inching towards doing better on cross-entropy is not going to shoot us in the foot for accuracy. Okay, they're not the same function, so we might take a little more time getting to where we're going, but at least we're not on a wrecking path here. Great, I can proceed. That's the kind of reasoning. Now, there's no need to commit yet. Actually, you'd be crazy to say, I'm definitely going to use the cross-entropy loss function, because you are a long way away from selecting your algorithm. That happens way later in the process. And you don't know what the actual loss function is that's going to be implemented in that algorithm. So why am I even making you do this? To make sure you're not asking for the moon, that's why. After you've developed your business performance metric, it may so happen that there is no classic standard loss function that captures the idea there, that goes along with what you're asking for. And if that's the case, machine learning is going to be really, really hard. Maybe you should back away slowly, or maybe you can go to the researchers and start talking to them about making an algorithm that is customized around what you, the business decision maker, care about. And the final thing, most important thing, is set performance criteria and commit to them. Performance criteria for both of our decisions. What's the minimum we'll accept to take this from prototype to production? This might be an important decision if that's a lot of engineering effort. And then, what is the minimum performance that I require to release it in full on all my users or customers? And you need to decide these up front. Why do we decide up front? Because we are human. And as humans, we fall in love with the things we build. As we pour our hearts into it and we put effort in, even if what we have made is a pile of poisonous rubbish, we look at it and we say, oh, but the performance is not so bad. And that's how awful things get released. And so while we are still sober, before we have fallen in love with anything, we take a good, cold, hard look and we ask, okay, what is the minimum I accept? And then we commit to crushing this thing if it doesn't make that minimum. Because we have just answered before we've poured all our love and energy into it, like, seriously, if it's less than this point, it just really shouldn't exist. It would be a bad idea to let it out there. And that's how we protect ourselves from bargaining ourselves into bad situations. Now, this is not an aspirational metric. You can have that as well. That's a guiding star thing, and that can move around all you like as you need to change it to motivate your team. But what you test against later has to be preset at this stage, and it has to be a minimum that you're going to accept. This is, as economists like to say, incentive compatible. If you use the guiding star here, then you'll test against it, and if you end up performing above that, well, you would have performed above the minimum, so same thing. But maybe you end up getting a performance that lands somewhere between your minimum and your guiding star, and the conditions of testing say, well, under that, you have to kill the system, so you miss out on a system that actually would have been viable for life. So I hope you realize why I have to laugh to myself a little bit when people ask me, hey, Cassie, is machine learning like better than human? Well, it depends on you, the decision maker, because tautologies are tautological. If you said that the thing must be better than human, and you tested it correctly, and it now exists, it is better than human. But maybe that wasn't the performance you required, because you could have made a profit on it being at scale, but a little worse than human. That's maybe still fine and profitable. And maybe you set your performance requirements at below human performance, and that's okay. Maybe it's below human performance. It depends on you. If you need it to be that good, then don't release anything that isn't. That's all there is to it. So key message here, the proof of the pudding for machine learning is always in the eating. And you have to figure out how you do the proving up front in this step. Decide on how you're going to measure success and set that cold, hard minimum early so you don't bargain yourself into releasing rubbish. Step 2, getting data. So this is where the data engineer works with the domain expert and gets data. Now, I realized at some point, to my horror, that people had this funny idea about how machine learning systems find and ingest data. Approximately this. The system sits, according to popular belief, sits on top of the business somewhere, floats around, and then goes and finds data, which it gobbles up, and when it's done with that, it goes and finds by itself, runs about finding data. This is not how it works. Instead, it is the careful effort of the engineers that feeds the data into the system, and it will not look at anything that you do not tell it to look at. So it won't go and figure out all by itself that it has to go and look at those examples and not those, or these features and not these other ones. That is up to the engineers to figure out. And so you need to think about which data sets, which ingredients would you like to feed into it, and then you need to go and write all the code, especially if it's at scale, to deliver that. That can take a long time. Then in step 3, you are going to split your data. This is the step in which I'm going to introduce a really important concept. We are going to give a name to the scariest nightmare in machine learning. And I'm going to, hopefully, if I do my job right, have you want to split data at a sort of visceral, emotional level. The idea that someone might not split data would disgust you. That's what I'm going for. So let's see if I manage it. Here we have a deterministic application. We have a feature here on the x-axis, 0 to 100, and our job is to use the feature to predict the ground truth, 0 to 200 over there. Can we do it? Can we find a recipe that takes us from the feature to the ground truth? It is so difficult, it is so hidden, that recipe is so hidden, it's in fact hidden over there. All we gotta do is take the feature, double it, and add 5, and we're good to go. And as long as we do that, there'll be no mistakes. That is way too easy, come now. Why don't we put in some noise? Noise that you will not be able to ever predict with any information available to you. Boom, random. 200 data points that are based on our line plus some random noise. There we go. Now that we have noise, does that mean that we are stuck, that we should just guess entirely at random, haphazardly? Or can we actually do better than guessing at random? I think we can do better. Let's use machine learning to do better. Let's predict our ground truth, our label, our target. And let's use this objective function, this performance metric, which is called RMSE, or root mean squared error. That one is probably named by statisticians because it is named for the recipe that you use to calculate it backwards. First you compute each error, then you square each error, then you take the average of all those squared errors, and then you take the square root. Boom, that's the score for the whole thing. Nice. Or another way of thinking of RMSE is simply that. Stupid model, be less incorrect. That's what we're going for. So we do better when RMSE goes up or down. Better is less of it, less error. And what's the best possible RMSE? 0, no errors at all. Fantastic. So we are going for be less incorrect. And let's look at half of our data. So I've split it into 2 pieces. I've taken the 200, I've taken only the first 100, and we're now going to learn from this. We're going to make some recipes. So the first recipe we're going to try is to use the model that we saw before, the true one. We're cheating a little bit. We know what the right answer is. Let's see how the right answer model does here. And it gives us an RMSE of 22.24, because there's errors. It's not perfect. There's noise. Okay. But maybe we hadn't seen all the behind-the-scenes setup here, and we didn't know what the conditions of this universe were. Maybe we were just a data scientist with this information arriving to us. That's all we got. And we're told that our job is to fit a great model that makes as few mistakes as possible. And so we start to do a thing, and you'll totally recognize this thing. You've done it yourselves in science, you've seen your science colleagues do it, it's amazing. So here we go. So you start looking at this plot, yeah, analytics. And then you see it. And when you see it, you can't unsee it. There is a wiggle here. Yeah? Do you see the wiggle? It's totally a wiggle. Come on. The data have a wiggle. This is absolutely a system. And you know what? The science says that wiggles make sense here. So let's attempt a wiggle model. Okay, there we go. Now, do you expect that the performance is better, lower? RMSE is lower when it's better than before? Or do you expect that things are worse, so this number has increased? Better or worse? What do you think? Better. Better? By definition, better. Because we are closer to our data points now, and the errors are the distance of the points to the thing, and that distance has been shortened by us contorting a thing through it, so of course better. You know what? While we're on this reasoning track, why not just take things to their logical conclusion? What's the RMSE here? 0. The very best is best. I take my bow. You look disgusted. But maybe you don't yet have the vocabulary to express what it is about this that offends you so much. So let me see if I can fix that. Remember, we have one job: to do well on stuff we haven't seen yet. Not to memorize our old stuff. To memorize our old stuff, that was a perfect solution. But we want a system that can do well on new things, so can this one actually do well on new things? Well, why don't we find out by looking at how it does on new things? So here's the other 100 instances. Let's see the performance. First, the model that entirely consists of signal and no noise, the true model, if you will. Above, in blue, will be the previous data's performance for that model, and this new 100 instances on the same model, below in red. About 22 for both of them. Pretty similar, and that's what we should expect. Now, when we look at wiggle, so remember this is 22 as far as you're concerned, let's see what happens with the numbers. Higher is worse, lower is better. This one, what do you think will happen? You saw it already. Down, better. How about that one? That's reading more like 23 now. More badness. Uh-oh. That looks like an uh-oh. Again, let's go to our logical conclusion and see if it feels like an uh-oh. 0 versus uh-oh. This situation is called overfitting. And for the last time in your lives, you get a free pass not to feel emotion when you hear this word. From now on, and I will quiz you after lunch, when you see or hear this word, you will feel horror, terror. This is your worst nightmare. This is the profanity in machine learning. Overfitting is what you spit at your enemies. You have one job. Make it work on new stuff. And instead, when you have overfitting, what happens is, there you are, memorizing your old stuff, learning all about the noise and irrelevant stuff in your old data. And when you release your system to go operate on new data, it crashes and burns horribly. And you ask yourself, why did I even get out of bed this morning? It would have been better if I hadn't data scienced. That is overfitting. And we're going to try really hard to avoid it. So overfitting is our worst nightmare in machine learning. It happens when our model is just the noise, the peculiarities of the old stuff, and has nothing to do with the general reality of the new situations. And you need to realize that any fool can get excellent results in the data where they build their models. As proof of that, I need only remind you that even toddlers can play that game where you connect all the dots. The real test is, does it work outside of where you got to cherry pick and torture those solutions? And actually, you should apply this thinking to every endeavor, not just machine learning. When you look at academic results, what scientists publish, it's very easy to make a compelling story pop up out of the data set you used to make that story. Ask, does the story still hold up if you go and collect a bunch of new data and then test the story? In the old data, it's just an opinion. If you want to see if the opinion holds any water, go to new data, test it properly. You can contort some beast of an understanding, both as a human and as an algorithm, in whatever data set you use to do that process. Might have nothing to do with reality, though. Just because it involved data and math doesn't mean it creates truth. Even toddlers can play that dot-to-dot connecting game, right? You can always connect your dots. And you can even connect your dots without realizing it by using a system that's complex, like neural networks. So you have one job. Optimizing for fit on fresh data. And if you don't do that, you may as well not have a machine learning system. And for that reason, you need fresh data for checking performance. That is why you split your data. There's two ways to do this, right? There's the way of saying, I promise to collect more data later, and that might just be a pain. Or you have one big data set now, so in advance, just split that thing so that you have some test data for later. That's like you're a professor. You have a bunch of calculus problems. You can either show them all to your students up front, but then you have to go invent 50 others for the final exam, or just save some, then use those for the final exam. Split your data. Now, we talked about overfitting, and you may be wondering, is there such a thing as underfitting? There is. Underfitting happens out of hubris. When you say something like, I learned about straight lines in school, and I insist on using a straight line to solve this problem. There you go. The straight line doesn't fit your data nicely, you didn't let your data speak, and so you get bad performance. Congratulations. It's much better to let your data speak. But be careful, when it starts to speak, it begins to overspeak very enthusiastically, and so there's going to be this balancing game where you're going to need to rein in that enthusiasm. That's why we have all those extra steps down the line. Now, in practice, underfitting is not the scary one, and you almost never hear about people fussing about it. And the simple reason for that is that you can diagnose it easily right in the data where you've done it. You fit your model, you got the performance score, it is obviously a bad performance. And so you don't even move to any next stage, and you don't even try to launch a system like this because it obviously sucks. Overfitting, on the other hand, is a silent killer. If you don't check it on new data, the performance in the data set that you use to build your stuff will look too good to be true. You won't know there's something wrong. If you connected all the dots, things will look perfect. And the only way you see that is if you test properly on new stuff. And if you're not very careful about testing properly on new stuff, you end up with systems that will bleed horribly. So you got to take this really seriously. This is the nightmare. What we're actually worried about, the monster, is bad performance, right? We want good performance. Make it work is what we're about. And the reason that overfitting is the one you hear about is that overfitting is the manner by which you end up with applied disasters of bad performance, because this one's easy to catch and that one's less easy. So, the way to overcome this is to be very careful about data splitting. And excuse me while I wax lyrical, sometimes my friends tease me that if I had to have 4 words written on my tombstone, they would be, split your damn data. I think this is pretty much the best idea in science, data science, and so forth. Data splitting is the reason we can have machine learning. When you have no data, you have, at best, an opinion, and there's no way to test the opinion. One data set, and you can either use it to form an opinion, but who knows if that opinion holds any water, or you can form an opinion in advance of the data set carefully by meditating in a closet, and it's really hard, and you have to use your imagination, but you can check if that opinion is nonsense. 2 data sets, you can now use one of them to get inspired, and another one to check if your opinion is nonsense. But your second data set has only 1 round of ammunition. It's a one-shot thing. So if you got inspired by some nonsense, yeah, you can find out that it was nonsense, but you go home empty-handed. So you're protected from going and spouting nonsense all over the place, but you don't get the thing you wanted. So then it makes you very careful about whom you trust to do the exploration and analytics, data mining stuff, to suggest the thing that's worth following up rigorously. And you sure aren't going to trust that to some dumb algorithm, are you? 3 data sets. Well, with a 3rd data set, you have a soft interim check, and now it doesn't matter who can have a go at getting inspired, because you can filter out all the clearly bad ones in the interim check. So now you can let, I don't know, you have a go, machine learning has a go, tea leaves have a go, what have you. And you can take all those opinions and you can check them on the next data set, and you can throw all the ones that are obviously not worth going for. Or if all of them suck, you can go back and iterate on this as many times as you want and then have your final one, final test at the end. And so it is 3 data sets that unlocks the whole thing, the whole ability to do machine learning properly. And today the modern way is 4 data sets. And we'll talk about what the 4th one is later. Most people still say 3. Humanity is evolving to 4, now that we have lots of data. Anyway, so let's split our damn data. So our original data set, we're going to split into 2 pieces, as I mentioned, for exploration and testing. Refining and designing solutions, and checking whether those solutions should or should not be built. Then, the exploratory data, we will split another 2 ways into a training piece and a validation piece. In-class examples, practice problems. This allows us to build models. This allows us to check how we're doing and have do-overs if we want to. So, the reward for this is letting you tinker as much as you like. You don't even have to understand what you're doing. Just try stuff. Out come some recipes. Put them in here. If you don't like what's happening, go back there. Back and forth as many times as you like. And when you think you've got the one, moment of truth, test it and see if it actually is legit. And as a trained statistician, a lot of that, and undergrad and grad, by the way, so a lot of years in this mindset, the world of a statistician is very dark. We're so twitchy, we're so nervous, because we are dealing with those situations where there's no do-over, and then it really matters how we have said we think our universe works. We curate the assumptions. We're very careful. With this stuff, all we're asking is, does it work? And so it actually doesn't even matter if the assumptions do or don't hold, if we know what they are, if we don't, if we check them. As far as building this stuff, run the data through it. Don't worry about what the underlying method is, because if it doesn't work, and if those assumptions were all screwy, you find out immediately, and then you go back and try something else. So you don't have to be anxious anymore. Be free, my friends. Realize just how freeing this is. You wanted to go and math through the assumptions? Why? Just have fun. Just tinker, dabble, play. It's a great time to be alive. Step 4. Look at some of the data. Are we going to look at all of our data? What do you think? Exactly. You have gotten the point of the previous stage. Which data set will we look at? The training data only. Now, why might we do this? Partly because we might be spoiled for choice in terms of features. We have the option to put any of 3 billion ingredients in. Which combination of ingredients should we put into our cucumber salad? Well, if we don't know anything about these ingredients because they're all labeled with barcodes, it's like being in a dark warehouse full of ingredients, and one way to do it is grope around there at random and pick some up and put them into your microwave and hope for the best. Another way is to do analytics first on your training data set, bring your flashlight, and have humans look around and think about what might be worth pursuing. Not for sure what's going to work, just what seems to be a fruitful endeavor. The domain expert plus the analyst together. Analytics pays off, as we saw. It helps you engineer good features. It helps you zoom in, narrow in to good solutions. Another reason we'll do this, say we're doing this wine picking thing, and we're working with the age of the wine. And that was calculated from data where we recorded the year. And we had a big wine tasting party, and our friends were there. They were also drinking, which affected how they were recording the data for us, which is great. And so we have this big spreadsheet with the years of the wine. And we could just pick that up and put that right into our model and never look at it. But we might also open up that training data, and then we notice that the computed age of the wine is sometimes reasonable, 2 years, 6 years, and sometimes it seems to suggest that the wine is from the Roman Republic. Now, maybe it is indeed Roman wine. Or maybe someone put in 2 digits where they should have put in 4 digits. for the year of the wine. And we wouldn't realize that unless we put our eyeballs on the data and actually checked what might be going wrong with it. So this is a step where we are inspired to see if there is any smelly bug in there, and should we write a fix. And we will hopefully not clean that up by hand. We'll clean it up algorithmically, and we will apply the fix not just to the training dataset, but to all 3 datasets, because you want the world represented by all 3 datasets to be the same world. So you shouldn't only fix one and leave the other 2. Then you've got Roman Republic wine in your test dataset, and things will go wrong. So this exploration thing really helps. Feature engineering, cleaning things up, selecting feature subsets. Step 5, getting the tools. So in this step, we're going to get hold of some algorithms, and we are going to apply them to our dataset. And as I mentioned earlier, the difference between all these named algorithms tends to boil down to what is the allowable shape of the final recipe. What sort of object are we going to use to try to separate our data? Are we going to try to use one line that can have any slope it wants? Or are we going to say, no, it has to be vertical and horizontal, but feel free to use multiple lines? Are we going to go for something super flexible? There are many more options beyond these. The math in machine learning, let me spell it out again, is in service of one of 2 things. Finding patterns in old data, or figuring out if new stuff works. Machine learning researchers care more about this one, and that's what's in the machine learning courses. How do you build a better microwave if you don't understand how this one works? Applied machine learning cares about this second one. This is the statistical math. This is not to be sniffed at. It's still something that you should take seriously, and it is math that you should master if you want to be part of the technical side of the application. So it's not like applying it means there's nothing, that no equations ever in your life. There should still be someone who's responsible for that careful, rigorous assessment, that statistical stuff, in your project. And that's what Applied will focus on. But before you get to testing it, though, from your applied perspective, what are we dealing with? We've got ingredients, then we are shoving through some algorithm, we get a recipe out on the other side, and of course we don't just serve that recipe immediately, we got to taste it, but the first recipe you try is never going to be the one that works properly, so in practice you're going to shove a whole lot of different ingredient combinations through a whole lot of different algorithms, and you're going to get a whole lot of results out, and then you will taste them all and see what's worth iterating on, just like in a kitchen. And this seems straightforward until you realize that your world is this. Oh my goodness. Okay, take a deep breath. First things first. Not all of these will be available to you in whatever framework programming language you have chosen, so it's already simpler. After that, you will aggressively eliminate bad options. So don't look for the perfect right option. Instead, take everything that's available to you and throw away the obviously bad ones. So some ways we do some throwing away. You know what label you want. It's a binary label, like yummy, not yummy. This method wants to output for me a multi-class label, like cat, dog, bear, giraffe. Clearly not a match made in heaven. Throw away that method. What about learning type? You want to do supervised learning? That method is for reinforcement learning. Okay, throw it away. It's not for you. How about dataset size? Can it actually handle the dataset that you're trying to deal with? If not, what are we even doing here? Available info. Your inputs have nothing to do with the timestamp. It rather insists it wants a timestamp, okay? Not for you either. And so you go through this list, and eventually that's what you're left with. It's aggressive elimination that you're going to do. And then of these, which are you going to try? Whichever you have time for. So then the trick, the applied machine learning engineer, they eventually do end up learning a lot about the nature of the algorithms just from practicing. They don't have to when they start out, but they end up learning this stuff kind of in the way that you learn the names of a cast of bad soap opera characters just by being in waiting rooms. Not because you're trying to, but mere exposure. So you learn this stuff in the end, but what you want to try to study up on purpose, is not how the algorithms work. It's how long does each one take to try on the various kind of data situations. If you have a good handle of that, you are an extremely potent, powerful machine learning engineer. And so if you know this one takes 2 seconds, this one takes 5 seconds, and this one takes 2 years, well, what order are you going to do it in? You'll only try the difficult one if the other ones don't give you any love. And so Google engineers, they keep coming to me because they spend too much time around researchers. We've got a huge research division here. They keep coming to me being like, Cassie, here's my problem. They tell me the problem. Which algorithm should I use? Should I use thing or should I use thing? And I have to remind them, okay, thing 1, how long does it take to try? 2 minutes. Thing 2, how long does it take to try? 3 minutes. Why are you here asking me? You should have tried them already. And even if the textbook says don't try it anyway if it takes no time. Because what the textbook is recommending is based on assumptions. Your business problem is not in the textbook, and you don't know whether those assumptions hold for your business problem. Hey, try it anyway, you never know. You find out by tasting it. So, in practice, if the inputs and outputs into an example that comes with that software package look kind of like your inputs and outputs, and it doesn't take that much fuss to re-wrangle your data set to shove it in there, go for it. See if it works. If it doesn't, try something else. Iterate towards a solution. That's what you're doing. Let go of anxiety. And so my advice is not to be the person who suffers most in machine learning, the perfectionist. Perfectionists have a really hard time here. They really are anxious about getting it right first time. You're never going to do that. Free yourself to make a glorious mess, because that's what it takes to succeed in the end. You never get it right first time. Okay, now it is time for lunch. Let's do a quick review of what we've learned. The 12 steps always start at step 0. Figure out whether machine learning is actually what you need and find a good application for it. And so there you're thinking about what labels or outputs you actually want from your system. Then in step 1, what are your goals? Which mistakes are worse than which other mistakes? Step 2, get your data. Step 3, split that data. Step 4, look at some of your training data. Step 5, get some tools. And then step 6, actually train your models. So let's look at training. We have our data split into 3 pieces. Training dataset, a validation dataset, and a test dataset. This section focuses on the training data. And what you're essentially doing is shoving your training data into a machine learning algorithm, cranking the handle, getting a model out on the other side, then checking whether the model works, and if it doesn't, trying a different approach, either by adjusting your ingredients or adjusting the algorithm that you use. Now, in practice, training is a little harder than the way it sounds. I mean, intellectually, all it is take some data, shove it through some algorithms, and keep doing that a bunch until things look promising. In practice, though, turns out that, different people packaged up these different algorithms for you, and somehow they didn't make it so that wrangling your data into a format that's acceptable by one instantly makes it compatible with all the others. Oh no, you have to go and put all the effort into individually customizing how your data set is going to be squeezed through those algorithms. That can take a really long time. Now, how many features should you use? Let's talk about training and dataset sizes. So what do I mean by use, firstly? If I mean store, the answer is as many as you can afford. How many you're going to put through the algorithm, that's a different answer. You shouldn't expect that you're going to shove everything in your dataset all at once. Now, if you have enough computing power, and you don't care how much it costs to process it all or how long that takes, then maybe you can get super lazy and try all possible subsets. But you probably don't have that kind of time and computing power. In some cases, that's going to take till the cold death of the universe. And so you're going to need to be selective about what you show to those algorithms in the first place. That's what you use the human analysts with domain knowledge for in this setting. And now we come to that really awkward part of the day where we have to talk about body shape. A dataset's ideal figure. Over here, in the leftmost position, is the worst possible dataset shape, which has as many as or more features than instances. So a very chubby dataset. When you have that situation, you are guaranteed overfitting. Just from a matrix algebra perspective. And even when you don't have more features than instances, if you simply just have a too chubby dataset, you are flirting with overfitting. How do we feel when we hear the word overfitting? Horror, terror, exactly. So this is not something we like to flirt with, right? So if you find your dataset in this situation where you just have way too many columns and more than you can sustain with the number of rows, a better figure is this one. Don't be so greedy, don't try to cook with everything all at once. Slim down and only use a subset of your potential features or ingredients. Now, if you have the computing power to move it around and you have the ability to get more instances, well, more is always better as long as you can afford it, processing power-wise. But once you have this, you can now afford more features again. This is best, even though this one has the same width as the one over on the left. The point here is that the complexity of your model and the number of ingredients that you're allowed to cook with is constrained by how many examples you have. In order to make a really complex model and to use a lot of ingredients, to pay for that, you have to have a lot of data. And so, I'll mention this now, but this will come up more later. One has to be aware and sensitive of one's data privilege. If you are an organization that has a hang of a lot of data, Spotify, Google, you know, those, then you end up being able to afford some crazy, cool, complex models because you have enough data to handle it. Not everyone out there does. And so, talking about success with things like, say, neural networks, it really applies to certain situations where you have the processing power and you have the amount of data to make it tick. It's not a one-size-fits-all solution. You need certain conditions for it to be right. And the price on those things is pretty hefty in terms of how much data is required. So this is something like an ideal figure, and you're like, okay, but what's the ratio exactly? And the statistician in me wants to be like, no, I'm not answering that because it depends, and power analysis and all these fancy things. But if you kind of wanted an emotional take on it, my emotional reaction to your dataset, because of course the particulars of your situation are going to determine how much width to length you require. But just my immediate gut reaction, if you show me your dataset, if I'm seeing that the length is less than 10 times the width, then I'm raising an eyebrow. And maybe you're fine, right, when we dig deeper, maybe it's okay. Maybe 100 wouldn't help you because of your particular situation, but just the kind of practitioner's lazy gut instinct is about there, about the 10 to 1. But certainly, if you're seeing that you have almost the same width as length, you're absolutely going to have a problem. Just don't. So don't try to cook with everything all at once. Slim down. Now, how might you think about slimming down? You might either slim down with analytics, so you have that human flashlight process where you go and look at potential ingredients and you think about what might be worth using and you pick which ones to try cooking with, which ones to exclude. And of course, like making that vegan, gluten-free, etc. sausage, you don't know whether you picked the right set the first time. You'll probably need to come back to this in any case. Now, there's also an algorithmic way to slim down. And that is a class of methods called dimensionality reduction or feature selection. And within these, you'll hear the ICA, PCA, those types of ones, principal component analysis. That's where they sit. And what they are about, generally, all these beautiful jargons, is about taking your input features and then doing some kind of transformation and outputting fewer super features, if you will, which are not really recognizable as the originals. So if you squinted at them, you'd be like, what is this and what's going on? But maybe putting these into your recipe would make it work very nicely. And so if you see that you are dealing with a data set that has a bit of a width problem, then you want to make friends with methods for feature selection and dimensionality reduction. Don't end up cooking with the whole cupboard. And in practice, tinkering can also be slow when you have a lot of data. It just might take a really long time for that optimization to finish and for your recipe to be cooked, or when you're starting right off the bat with software geared at production, so something like TensorFlow. TensorFlow is not designed to be fun to use. Incidentally, says some chuckles from those who know. I keep saying, I dream of a day when we can have a laptop sticker that says, I love TensorFlow. Not, I tolerate TensorFlow because the damn thing works. But at scale, for certain situations, nothing else will do the job, and so we have to be grateful that we have something that works. But it's not really geared at prototyping. It's geared to be the beast that works at incredible scale. So, here's the thing. That mindset around I have to run all of my data through it all in one go every time is going to slow you down a whole lot. What you should be doing is having a place that you can comfortably prototype quickly on small subsets of your data. So you don't have to wait for all the churning through your data set that takes all weekend just to try out a thing, and then you make some subtle setting adjustment, then it takes another few days for you to see how that does. Rather, take a little bit of your data, and in an environment that's not geared at this serious production stuff, just try out some algorithms and see what seems to be worth investing the waiting time for the whole data set, right? So you inch towards a solution. You don't have to do it all in one go. You don't have to go right to TensorFlow. Use some other implementation that's really simple and quick to interact with on a small subset of your data. And that will tell you whether the approach itself seems promising. So even if you're doing neural networks stuff, you can use a smaller data set and some package that isn't very fussy on how you have to wrangle the inputs and do all the settings, just to see if that's even worth pursuing. Do that first. And then when you have to scale up, then you know why you're putting the effort in. Okay, then you're like, great, training phase. Do we use statistics now? Well, there is statistics, and there is statistics. Statistical inference, the discipline, is a heavily philosophical one about making decisions under uncertainty, where we don't have do-overs, and we really have to think carefully. Very rigid, I consider it very beautiful philosophical pursuit. And we do care about what we think things mean over there. And then there's statistics. This training part, is at best this one, where we're just going to kind of muck about with methods developed maybe for other purposes that you might see statisticians using, t-tests and whatnot, but we are at no point interested in that philosophical pursuit. We are just trying to get it to churn through our data and make something that does the job. So you can let go of all of your philosophical anxieties. Don't worry, those will come later in step 9. But here, you're just shoving your data through a bunch of stuff, throwing it at the wall and seeing if anything sticks. So it's very freeing, it's very fun. So let's train. And training is party time. Because all that anxiety should just melt away. It really doesn't matter if the assumptions are right. Try it anyway, because if they were wrong, you find out in the next step, you go back and you try again. No big deal. So you don't need to hold your breath at any point, just keep trying stuff and iterate until it works. It's so fun and freeing. So this is a bunch of tinkering and dabbling it's emotionally painful if you expect that other approach, where you expect you have to understand that everything is perfectly set up. But when you realize that you don't, you are all qualified to, if you're actually able to write the code that puts data into these things, you're able to do this. So you're going to send your data through a bunch of stuff, you're going to tinker, and you're going to kind of work your way towards something that seems to be working. And when we say fit, that means perform well on an objective. And your algorithm behind the scenes is going to be trying to perform well on the loss function, remember? You should also be checking how are we doing on the one we actually care about, our business performance metrics. So at every point, just put your answers you're looking for and the answers you got through your performance metric and see how you did there. So your mission is to make it fit in this sense. I'll make it fit. But please try to make it fit rather than overfit. Now, you'll overfit anyway, but do it with a view towards fitting. So here's a little process preview. We're going to start and we'll do some training and tuning, where we're going to figure out a potential recipe. And then, when we've done that, certain things might be true. We might be fitting, we might be overfitting, we might be underfitting, we might simply be making a mess. These are all options. If we're making a mess or we are underfitting, we will be able to discover that fairly quickly in the same data where we did it, and we'll go back to the drawing board and try something else. So if we're thinking of moving on, we don't have those other two, we have one of these, fitting or overfitting. Okay. If we happen to, and we can't tell the difference, remember, in training data, we need a different data set to diagnose this. Now, if we happen to have a good solution that generalizes, that models what we care about rather than our noise, then when we take it to validation, what happens? Validation should pass. And when we take it to testing, testing should pass, and we launch it and we get promoted. Nice. If, on the other hand, we have overfitting, you know, the worst possible thing that could happen, right, is that we launch some horrible system that destroys everything, that crashes and burns. Well, don't worry, we have a seatbelt, we have protection against that. Validation will prevent that bad situation. So we go to validation, and because we have this problem, validation fails. Good, no big deal. We were protected from launching something horrible. We could just go back and try again. Now, as you examine this diagram, you begin to notice something. It's the dreaded infinite loop of projects that never end. Yes, you're not launching horrible things, but you're not launching things. You're protected, but it never ends and you never get anything good. By continually being in this overfitting limbo, constantly overfitting, okay, validation fails, go back, try again, overfitting. So you want, ideally, hopefully, to launch good things, yeah? And get promoted, as I said. So what strategies should you take? Can you do anything? You can learn to love simplicity. This really helps. See, turns out that the more complicated your model is, the more you open yourself up to overfitting. And you can go and poke around in the mathematical details later, but actually layman's terms work pretty well for this as well. You can just think of it like this. The recipe you're going to use to convert inputs into outputs, the longer it takes to write that recipe out, the more complicated it is. So a recipe with more ingredients in it is a more complicated recipe. A recipe where you torture your few ingredients more is a more complicated recipe. And the more complicated you make your recipe, the more places you give your model to contort itself to your data and to connect all the dots for you. And so, learn to love simplicity. Don't right off the bat give it the opportunity to connect those dots. So, what am I saying? What I'm not saying is always use simple solutions, people. Straight lines are great. I mean, I already had a rant about that, right? That's the hubris of underfitting, insisting that the solution's got to be too simple. Well, that's not what I'm saying. What I'm saying is start simple. And then if that doesn't work, then try something more complicated. And if that doesn't work, then try something more complicated. So inch your way up to the complicated thing rather than go right for it. Which sounds all good and well. Except then we wonder why people go right to neural networks and try that as their very first solution. Probably because it sounds really good in the performance review, yeah? Like it's such a cool sounding thing because it's got brains in it. Neural networks is the method that has the most flexibility and complexity among your options. And so it's going to be good at fitting. It's also going to be good at overfitting. So you want to watch out for that. And you want to use it when it's the right thing for your task and not just as the very first option. So unless you know everything else is dead in the water for your task, don't start there. Work your way up to it. Try something else simpler first. You may as well just try the line. It takes 2 seconds in any software you're using. At least use that as a benchmark for what performance can you get from the dumbest possible model. And one way to enforce that love of simplicity is through the process. Another way is to algorithmically enforce that. So the algorithm will itself prefer a simpler solution to a more complicated one if given 2 options. And that is what regularization in machine learning is all about. It is simply about an algorithmic love of simplicity. Before, your loss function is all about don't make mistakes. And points are only assigned from how well do you avoid mistakes. Now we can adjust how our game is scored. Now we get a good score if we don't make mistakes. And we also get good points if we have simple solutions. Maybe you'll phrase it in the opposite manner. You'll say, errors give me penalties. Complexity also gives me penalties. And now we can have our algorithm balance those 2 concepts. How much nice fitting am I willing to give away if I'm going to do that with fewer features or with a less complex version of my model? That's all I'm going to say about regularization. You can read a whole bunch about it. It's a very favorite topic in machine learning, but at least have a passing familiarity with it as a love of simplicity. And if a researcher says to you, hey, would you like a regularized version of that? The correct response is, yes, please. Why isn't everything done that way? Because the researchers haven't finished working on it yet. Key message. Start simple, build up the complexity only when simple doesn't work. And the final thing may be sophisticated, the initial thing probably shouldn't be. Other training pitfalls. Avoid training on data from the future. You'd think. For example, you're trying to predict tomorrow's stock price, and you use tomorrow's interest rate to predict tomorrow's stock price. If you're going to do that, just use tomorrow's stock price to predict tomorrow's stock price. It's cleaner. So how does this sort of thing happen? Well, you tend to treat your labels with some respect. And you put them separately and carefully into your algorithms. But sometimes you don't treat the features with very much respect. And so you take the whole pile of features that you have access to, you put them into the algorithm, and because you haven't gone and dug into how that algorithm works, you don't know what it's doing with them, you've given it access to stuff that it might use, if convenient. Because if you have a year's worth of data, then you have given it access on January 4 to January 5th's interest rates. And if those help to predict January 5th's stock price, especially if the algorithm is allowed to do such stuff and has the flexibility to do it, it may just help itself to that for your solution. So you'll want to make sure, if you don't want to go dig into how these algorithms work, that you find a way to lock it out of attempting to use stuff that you just cannot have in production. Because on the day that you want to use this thing, you don't actually have tomorrow's interest rate. And that's part of a more general principle. Please think about what you are submitting, what you are allowing the system to train on. Don't allow things that cannot be used or processed in production into your solution. So run a little check on the solution and see if there's anything dodgy there. A classic example here is one where you need to serve your user things quickly because your user is not patient, isn't going to wait around 5 minutes for your algorithm to churn and output something. And you've used offline data that you have saved, you had in an attic somewhere, to build the prototype. And you made a feature, which is an awesome feature. But in order to compute the values of that feature, it takes an awful long time. But don't worry, because this was a big data set you saved, you just put a week up front computing that feature. And now you've got that column, fantastic. And then you do all kinds of learning involving that column, and it works, and it keeps working, and it's great. But now, because the recipe requires that thing on the fly, you're going to have to compute it, and that takes too long, and then your user wanders off. Resist temptation. Just don't use it if you cannot actually use it at the time that this thing has to operate. Or work with your engineering team to make that computation faster. Now I'm going to have a skipping slide for each of these sections. What does it mean if you skip this one, and is it safe to do it? Well, with training, no. If you skip training, you kind of missed the point of machine learning. You didn't let the data speak, and the whole point is to use the data to generate the solution. If you wanted to handcraft the solution, well, that was traditional programming. It's not this. Key message: in training, your goal is to find useful patterns in your data. Scratch that. Useful patterns. Your goal is to find patterns, whatever. We'll figure out if they're useful or not later. Just find patterns in your data, turn them into recipes, make a short list of models that seem to work. And don't worry about getting it right. It'll take a few tries. Let go of that perfectionist attitude. I used to be a perfectionist before machine learning. It got beaten out of me with a stick. So step 6 is finished when you've got your candidate models and you know how they performed in your training data. And you expect that their performance in training is better than their performance elsewhere. And so if they're not meeting your bar in training, don't proceed. Keep on keeping on in here. Then, tune and debug. I would like to announce my lack of desire to get into any terminology debates, discussions, or fistfights. Call it what you want. I am tired. Maybe you will say that what we're doing in this 7th step is training-ish. Maybe you'll say it's validation-ish. Maybe you'll ask me to put it back to step 6 or forward to step 8. I don't mind. The point is, it gets its own step because it gets its own data set. You need a separate data set to pull this one off. So you can call it what you like, but please give it a 4th data set. So the things we're going to do, the training-ish thing is tuning, and the validation-ish thing is debugging. And in practice, you can either have this data set pre-saved at the beginning, so you can split into 4 in the splitting step, or you can take this on the fly out of your training data. So in step 7, you grab some out of training, and now you have a training data set, and you have this data set separate, and then later, you can recombine them and pull them apart differently if you want to. So it's okay to reuse and mix the data here. So you're going to take it out of the training data, unless there is something very particular and special about how your team wants to do the debugging, in which case it might make sense for you to curate that debugging data set up front and have that 4th one. Who here likes debugging? Actually, I should have asked that question better. Who here likes the idea that someone else will debug? Aha! All of us like that one. Now, if you want debugging to be a possibility, you need a debugging dataset. So, what will you do? You'll set it aside, and you're going to fit your model in the remaining piece, which I'll refer to as the training data here, but you got the debugging data out of the training data in the first place. Then you will use that for your interim performance check before you go to your validation dataset. And you're going to look at the individual instances and see whether you are inspired by what is actually going wrong with those individual instances. Debugging in your training dataset, as in the dataset where you ran the algorithm, doesn't really give you an honest view of what's going wrong. Because you know that the whole point, right? It's trying to put the boundary or the line as conveniently through the data as it can. It's already contorting itself to your data set. And so you don't really see where it fails. Like debugging that is fine and you get some insight, but the real insight you get is by taking a data set where it didn't have the chance to contort itself and seeing, all right, which ones did it get right? Which ones did it get wrong? Doing a bit of analytics and seeing what's common among the failures, what's common among the successes, and how might I want to adjust my training based on what I'm seeing. So in our wine example, it would be a matter of you look at, you run your algorithm in the training set, you go to your debugging set, you have a look at what's common in the failures, and you happen to have the name of the bottle of wine also as one of the columns. You didn't use it in training, but you have it. And you're like, hey, look, all the ones where I'm failing, they sound awfully French. Maybe I should have a feature that's got something to do with country of origin. Maybe that would help me. Maybe I don't realize I like French wine or something. And that then inspires me to do some feature engineering and maybe get the information on what was the country of origin of the wine, and that makes me create a new feature, and then I try another approach again with the inclusion of this new feature. So it's really this debugging process where the human, the analyst, ends up interactively updating, adjusting, and creating a better solution. So for that, you use a debugging dataset. If you skip this step, you lose your explicit debugging strategy. Now you cannot actually look at individual instances. If you look at individual things that went wrong in your training set, well, fundamentally, your entire algorithm's job is to contort the solution insofar as it can, based on the rules of what it is, whether it's a line or a squiggly thing or a bunch of vertical and horizontal lines, whatever it is, it will try as best, according to its nature, to contort itself to your training data. So its performance will be pretty good for that training data. If you really want to know about how it fails where it doesn't get this chance for contortion, then you need this other data set. So looking in individual training instances doesn't really give you the full story of what it's getting wrong. It gives you some, but a better insight would be a withheld dataset like this one. And you're not allowed to go poke around in the validation dataset, you're not allowed to go poke around in the test dataset, so you want a sacrificial dataset where you are allowed to poke around. You can take that out of your training data, or you can have it explicitly preset at the beginning. When is it okay to have no debugging strategy? It's preferable that you do actually interact and put your eyes and brains on the data and think about the solutions that you're making. I'm loath to say that there is a time that it's okay. I mean, today in practice, you should be debugging. But there are folks who have a vision of a hands-free, human-free machine learning of the future. And if you're going for that fully automated thing, then you're trying to skip this step. That's the goal of those projects. So then you wouldn't be manually debugging. But today, the reality is that you should be doing this. Now, tuning. You just ran an algorithm. And somewhere in that code, there was some place where you had to put like regularization parameter or learning rate or whatever. And you're like, look at this thing. And you're like, what even is that? 0.1. I'll just put 0.1. Where did that 0.1 come from? How did you pick that number that went into the settings? Oh, you just picked it out of nowhere, didn't you? Didn't you? We should have a little talk about hyperparameters. First off, what is a hyperparameter? I give you multiple choice. Hyperparameters are either A, parameters on too much caffeine, or B, numerical settings in an algorithm. Which one is it? B. So what is a parameter in machine learning? When we were doing that regression example, the numbers in red that we could tinker and fiddle with to adjust our solution, like the intercept and slope, those were parameters that we could mess about with. A hyperparameter is something that is there before your data even hit the algorithm. So here's how you might think of it in our kitchen analogy. You have this meat grinder thinger. It has a coarseness setting on it. You have to put the coarseness setting to something to even be allowed to turn the handle. If you try not to have a coarseness set, then the handle falls off. Then you can't even use this thing. So when you get this thing out of the box and you want to try it, where are you going to set that coarseness dial to? Whatever the factory setting is, or maybe you have a favorite number, some unprincipled choice. And you try that, maybe a few settings haphazardly, just to get a sense of whether you even want to use this tool in your cooking process. And when you think that this one is something that you might actually go for, then you're going to fine-tune that dial and pick a setting that works best. That's how tuning hyperparameters is also going to be in practice. You can almost think of every different hyperparameter setting is essentially something like a different algorithm. It just makes your head spin to think about how many different algorithms you're effectively trying if you have a continuous hyperparameter. But the parameters depend on your data. The hyperparameters, you have to pick them before you can hit run. Now, if your algorithm has these numerical knobs and dials, you must tune them. How do you do it? Well, I'm about to make it look way easier than it actually is in practice. If you have a very simple setting with one hyperparameter, what you can do is this. You take your training dataset, there it is, and say you didn't have a dataset withheld for tuning, you take one out. Okay, there's your fourth dataset. Now this is your new training dataset, that's your tuning dataset, and what do? We're going to use a good old trusty for loop. Begin with your hyperparameter set to its lowest possible setting. And now train your model with that setting, evaluate it on this tuning dataset, and store. Then, next setting, same thing, next setting, same thing, next setting, same thing. Tally up your results, and do you have a preference? I sure do. It looks to me like the third setting here is giving me the best performance, at least in training, and so that is the one that I'm going to prefer. It's not ideal. We know that there are a whole lot of issues with taking our results in training seriously, but at least this gives us a principled choice rather than having to have a guess or use our favorite number. So the result that comes out once you have picked your setting and set 3, now you can just rerun it on the entire set, training set, and the result that comes out, you're going to call it your tuned model. And at this point, you're like, tell me what cross-validation is. When I used to run this course, I used to try to avoid talking about cross-validation, and someone would always be like, but cross-validation. So, okay, I succumb to your tyranny. What is cross-validation? So first off, cross-validation is not validation. Yeah, I know, right? It's tuning. I wish we had called it cross-tuning, but there you go. Actually, cross-validation was developed by statisticians to serve as validation in really unpleasant circumstances where the normal approach was not available because you had very little data and it sucked to be you. And then if you were going to take that approach to validation, you would want to have 2 statisticians holding your left hand, 2 statisticians holding your right hand, and the 5 of you would tiptoe very slowly towards the cliff's edge and probably fall off it anyway. This is a hard thing to actually use for validation without messing up. Messing up in the sense that you end up knowing too much about your data and then having overfitting problems. And if you need to be doing that, you know you need to be doing that. I'm not going to talk about it here. The safe thing that you can always use it for, in all circumstances, is step 7, tuning. That you can and should and please do use it for without worrying about making mistakes. So let's see how we'd use it for tuning. Here we go. I'm going to show you k-fold cross-validation, where k simply stands for the number of non-overlapping chunks that I'm going to split my data into. Okay, so my training data set is split into 5 pieces. Now let's do 5-fold cross-validation, like so. Again, set our hyperparameter to 1, and now take 4 pieces as my training data, fit the model with that hyperparameter setting and evaluate it there as before, store this bunch. But before I move to the next hyperparameter setting, I'm going to do this all again, except now the evaluation set has shifted. And again, and again, and again, 5 times. Move to the next setting. Here we go. And so forth through your hyperparameters until finally you can aggregate over the 5 models that you fit each time what the performance was. And then again, you say, which one do I like? I now have a principled choice. I set it to 3. I rerun the whole thing, and the result is called my tune model. Now, there are some lovely reasons why this is a little bit more of a robust technique for tuning the hyperparameters, so it's more computationally expensive, it gives you slightly better results. But there's some additional thing that's even more beautiful than that. This allows you to check model stability and see if there is something really bad going on. It is, in other words, the ability to debug inside your model. This is going into the brain with a scalpel, if you will, and seeing what's going wrong with the model without having to read the model. Because the model might be too long, remember, and too complicated. And you'd like to see if there are issues with it, and you don't necessarily understand how the model works. How can you debug the model? Well, this is a way. And here's the logic. Every time you run it, you're taking 80% of your data, for this case, right? You can break it up into as many pieces as you want. Here I've got 80% of my data. And that means any 2 of these have 75% of their data here in common. So if I'm basing my model in 2 different runs on 75% the same stuff, what do I expect about my results? Like, if this is a real thing, a legit thing that generalizes to the universe. Right? 75% of the ingredients are in common. I'm expecting kind of the same thing coming out of them. So if I get wildly different results, that is a huge red flag. Alert, alert, something is gravely wrong with what's going on. Now, what might be wrong? The classic. Not enough data to even be doing this kind of model complexity. Then you get, if you have some very serious overfitting because you have a chubbiness issue in your data set, or flexible algorithm that's got too many moving parts, parameters that it's going to try to set, and you don't have the data to pay for that, you will end up having those parameter settings all over the place across your different models, and you will discover that they all predict different things. You're having a lot of overfitting to the peculiarities and the 25% different data points. They are generating enough contortionism to make the results really very different from the other 25% over there. Another thing that it might alert you to when you go debug and dive into those instances is a model that is very susceptible to outliers. So what's an outlier? Just think of that as a weirdo data point. A data point that is different from the others. And there are some methods that are totally cool with outliers, no problem. But there are other methods, think of the line, the regression methods, where if you have a data point over here, the line might be pulled towards that one single data point. And just that one fellow is going to change your solution a whole lot. And so if you have that kind of situation, then you will have very different models here, and you will have very different performance. And then you'll be able to see, well, what is different if you have 4 results that are all the same and one that's very different, where that weirdo was in the evaluation set. You'll actually be able to dig in and find that data point. You'll know it's one of these. You'll have a look. You'll see what's weird about its particular inputs. And this is pretty valuable when you're dealing with very high-dimensional data sets. We've been looking a lot at things that you can plot and see by eye, but if you have 1 million inputs and 1 billion rows, it's really hard to know that there's something like this going on. What are you going to plot and look at by eye? This will alert you to it and allow you to zoom in on where the problem is. So it's a very nice technique also for analytics and data mining. If you skip tuning, what do you get? Silly hyperparameters. Your coarseness is set to wherever, and maybe that's not good for cooking. When is that okay? If there weren't hyperparameters, of course you don't have to tune them. Or if you have lots and lots and lots of data, or if you have a method that isn't perturbed by outliers. Tuning tends to become more important later in the projects, just as with cooking. You're not going to start fine-tuning the knobs on your implements until you're pretty sure that you want to base your solution on those devices. So, key message, allocate some training data for debugging and tuning, either at the start of the project or on the fly. Debugging gets you insights. That's how you figure out what to do next, how to engineer better features, and so forth. Tuning saves you from poor hyperparameter choices. So this is finished when you've got your debugging opportunities identified and you've tuned your hyperparameters. Next, avoid buyer's remorse with validation. What if you got to this stage and you have overfitting? Actually, let me just tell you now. You will get to this stage and you will have overfitting. And what emotion do you feel when you hear that word? This is your quiz. Terror. Horror, terror, exactly. Overfitting is your worst nightmare, remember? And now I'm telling you, you're going to get to this stage and you will have overfitting. Your model will have memorized the answers instead of learned what you needed to learn. And you won't know that this has happened to you unless you're able to check on fresh data. So you'd better have some fresh data for checking. This is where you validate. You simply take your model and you get your performance on a different set than one you trained it on. If you don't like your performance, go back to training. If you do, go to the next step. Now I say simply, there is that little gotcha. You have to keep your data set fresh. And keeping your data set fresh means you can't go learning from it. You can't go debugging in there and effectively training too much on this data set. So you're going to use this one, this second piece out of your set that you have assigned for exploration. The first piece was training, this is validation. And what is going to happen is this. You're going to love the model you've just trained, it's going to look so promising, you'll take it to validation, and it crashes and burns. Well, you should expect this is a long, iterative process, and your first solution won't work. So now that I've warned you, you won't have a nasty surprise. You're going to go back and try again. And so when you find that it doesn't work, what can you do? In order of likely goodness of approach, try make other features. How will you know what other features to make? Well, through that debugging step where you see what's common among the instances you succeed on, what's common among the instances you fail on, and what sort of new features would that inspire you to go and construct out of the ones you already have, or ask your engineering team to help you collect. Then, feature subsets. Maybe you got greedy. Maybe you said to yourself, well, all of these features are awesome and I can't bear to part with them. And like the hoarder that you are, you put them all through your model and it was too chubby. And now you pay for it by having overfitting. Well, okay, then you say, fine, I will slim down my model a little bit, try it with few things, see if that works better. Trying a different algorithm. Why is this in position 3? Because I'm guessing that if you have followed your instructions to get to this point, you have already tried all the ones that were easy to try with minimal fuss and coding effort. So once you're here, you've already got a whole lot of validation scores on all the things that were easy to try, and it's going to be an engineering annoyance to try something else. So because that's annoying, we put it in position 3 in terms of its effort to payoff ratio. Then tuning. Tuning tends to pay off a little less than actually changing your algorithm class. So that's in the 4th position there. And finally, changing your model complexity. Okay, there are these situations where it just doesn't work no matter what you do because you're dealing with image recognition and you need neural networks and you've been trying to do it with a line and you've been ignoring the fact that your training performance sucks, and you took it to validation and you really got that reality check and it said, this is too simple, doesn't work, okay, then maybe you need to increase your complexity. Chances are, though, that you did diagnose the underfitting earlier and you are already in the more complex set. Fundamentally, tuning is part of training. This is all part of the larger process of making the solution in the first place. And so, training data that is assigned for the purpose of making the solution is supposed to be looked at. You are encouraged to do as much analytics on that dataset as possible to inspire you to direct your efforts. Which ingredients should you use? Which algorithms seem to be working better, and so forth. Validation, on the other hand, is blind. That is the whole point of validation. You are not supposed to look in your validation data. You're not supposed to learn about it. It is not validation if you already know what's in there and you have designed your solution to game your validation data. And this is supposed to be a check on fresh data. How do we do on data where we don't know anything about it? And so the way that you make sure that validation stays validation is that you only look at the final performance metric. So in fact, ideally in your infrastructure, you wouldn't even allow anyone to look inside it. You hit the validation button, all it outputs is the final performance metric, nothing else. But of course, engineers, you know that if you have just fallen in love with your model and you take it to validation and it fails horribly, every bone in your body is screaming what? Debug! Find out why! What went wrong? No, that's what your debugging dataset is for. Because the problem is, if you debug in the validation data, you are eroding and ripping off the seatbelt you have against overfitting. Consider, when you look at those validation instances, you're doing it so that you can adjust your strategy. In other words, you are training on them. You wouldn't be looking unless you intended to learn from what's there and change the nature of your solution based on what's there. So, all right, if we are going to do this fairly, we should take any instance that we looked at and we should move it to the training dataset because we have trained on it. So, we've made the validation dataset a little smaller. If we were debugging at random, the only effect is that our validation dataset got smaller, and that might not be a big deal. But come now, engineers, who here debugs at random? What do? You don't debug at random. You go to the most heinous failures, and you examine them. And you adjust your solution to beat the hardest instances. Well, all right, what are we going to do with those instances? If you take them out and put them into training, your validation dataset is easy to beat. You've just taken the hardest examples out. If we leave them in, you already know what they are, and you're going to go and adjust your solution so it wins against them. So when you check performance and you find out that you have good performance, you have exactly fitted it to those few data points. That's overfitting right there. So there is no way to win here. If you want a validation data set, and you want to do validation, you have to only look at that final performance metric. And of course, I really endorse your desire to debug. Do it. Just do it in the debugging dataset. If you want to do debugging, have one for it. If you want to do really high-quality debugging, have an entirely separate, very large debugging dataset. But just keep your debugging out of validation and out of testing. And don't have illusions about thinking that you're still validating if you routinely use your validation set for debugging. Now, since we're getting so cautious, I'm sure you've realized that even if all you do is look at the final performance metric, doing a whole lot of it still teaches you way too much about what's in the validation dataset and how to beat it. I mean, a data scientist is a dangerous thing, right? You'll learn all kinds of things very quickly. You get good at this. So yeah, you do erode and pollute your validation data by reusing it. That's not the end of the world. The whole point here is that you've got one more layer of protection, the truly pristine dataset. That's next. You're using this to get towards a viable solution, and yeah, with every round, the seatbelt erodes a little bit. This validation step is part of the training, tuning, validation process for getting solutions that are likely to work. The test step is the question of, do we use them or do we have pens down? So this is something that helps you succeed on your exam, students. You can cheat, you can mess up here, that's fine. There is a final protection for you. This will just make it more likely that instead of leaving your project empty-handed, you end up getting something good. It will erode as you go on, but there is a later protection for you. When I was first designing this course, I did a survey of over 100 machine learning researchers and applied machine learning experts at Google. And one of the questions I asked them was, what is the one thing that you most want people to learn about machine learning? And overwhelmingly, the favorite answer was validation. The real one, not the one they think they're doing. As in, not debugging. I think there was one comment that was like, teach them to validate or get out of machine learning. So I figured, why don't I step up how visceral I make my analogy and talk about the game of Russian roulette. You know that game where you put the bullet in, spin it, close it, and clump. Now you have the option, if I force you to play Russian roulette, you have the option to either play traditional Russian roulette, that one, or you may play Russian roulette with validation. How does that work? Starts the same way, in goes the bullet, spin, close. But just before you pull the trigger, you open it back up, you see if the bullet is the next one ready to go. And if it is, you spin it again. Which do you prefer? With validation or without validation? I have a strong preference. I strongly prefer with validation. Then I say to my Google colleagues, if they do machine learning around here without validation, they are playing traditional Russian roulette with my stock portfolio. Friends don't do that to friends. Do real validation, people. So, skipping validation. Let's see. If you skip both validation and testing, the result is that you will launch some poisonous rubbish. That is bad, bad, very bad, don't do that. If you only skip validation, and you do have testing, unless you are solving a really easy problem, and your first solution just so happens to be a great solution, all you will find out is that it doesn't work. You have no more ability to do any more refinement. Pens down, no machine learning for you, so you end up going home empty-handed. That's a bit sad. It would be great if we could instead use machine learning for awesome things and actually get something out of it. So stay safe, don't skip validation. Key message, validation is all about checking if your model succeeds on a new dataset. It protects you from the monster. And make sure you only view the final metric. If you're going and looking inside, that is debugging. And then you should worry about what it means if your project doesn't have a validation step. So step 8 is finished. You have your best candidate model and you've evaluated how we do in fresh data and whether to start again. Step 9, testing. Should we actually allow this thing to move to the next stage, get productionized? We've got some kind of solution. We don't know how good it is. Should we just release it upon the world? Or do we, I don't know, like maybe have standards? That's what this section is for, having standards. Now, if you've been wondering when I'm going to start preaching about statistics, and you've noticed that I've just been all like, dabble, tinker, play, don't worry about it, don't take anything seriously, everything will be fine. Wait no longer. Now entering the statistics zone. Now we get to do everything on tiptoe and worry about what our assumptions are and do all our rigorous decision making. Awesome. Why do we need both testing and validation? Well, as you go through more and more refinement rounds, validation performance tends to go up and to the right. Some part of that is that you actually built a better solution. Some part of that is that you are now overfitting on both your training and your validation data, especially on the edge cases and heinous failures in your validation data. And you don't know how much of that is which one. And that is why, when you think you have the solution, you're really considering releasing it upon the world, take a moment and properly check whether it actually works. So, you've polluted and eroded your dataset. Only a pristine dataset will actually tell you how you're doing. What makes testing testing is that this is a clean room where we're going to use truly new data that has not been used in training in any way. And we are going to be very rigorous and careful with the statistical testing. So this is a dataset that hasn't been in play yet, that we have held under lock and key this entire time. Now, one time and one time only, we unlock it, we get the result, and either we get to take our model to production, or no more machine learning for us. So it's a pretty big decision. This model is the best model you have. Should you actually build it? And we'll have another similar statistical step where we ask, should we launch the model? That's later. For now, should we build it? So this is where we get to statistics, and this is where we need that hypothesis testing. So a quick reminder of what the point is of statistics. In frequentist statistics, classical statistics, you use that for decision making, and it is essentially the science of changing your mind. Every statistical hypothesis test in that philosophical framework is saying, does the evidence that we've collected make our null hypothesis look ridiculous, yes or no? So it is about changing our minds. It's about saying, here is what we have chosen to do by default. Here is what the world looks like when that's an okay thing to do. That's the null hypothesis. And then we ask, does the data make us want to change out of that, or should we just keep doing what we're doing? Now that's the framing. And because our step involves describing what the world looks like, where we are okay doing what we were going to do anyway, that world's the null hypothesis, because we have to describe it, we have to carefully state all these assumptions about it and say, what do we think we mean about this world? What does it look like? And how would we know if our evidence makes that world look ridiculous? And then we have to think that through. So it's an intensely philosophical pursuit. So this is about changing your mind, and you've completed all the steps figuring out what your mind is set to in step one. So I was kind of light about the amount of statistical setup that's actually part of the statistician plus decision maker effort that happens in that very first step. And now I'm going to talk about what should actually be in your document from step one. So these are the 12 steps of our statistical thinking course at Google, which is, I think, our most popular course, because I guess they like the comedy hour from me really ranting about stuff. I'm totally chill in this one, by the way, compared to that one. That one's like where the anger comes out. That one also has 12 steps, and I'm going to give you just the quick summary. We spent from 9 a.m. to 7 p.m. getting through them in the other course, but you get it in a couple of minutes. So all this stuff from 1 through to 10 is already done before you get to this course's step 9. So what are we looking at? So first, I'm always surprised and slightly appalled to see that people use statistical inference, frequentist statistical inference, without realizing that all of it hinges on the notion of a default action. That is actually the first thought you should have if you go near statistics. Philosophically, none of it makes sense without that object, because we are trying to change our minds. We need to know what is our default, what are we going to do in the absence of further information or data. And if we are actually completely agnostic, we have no opinion, we also have no business using these techniques. Just go with the best guess, otherwise known as the estimate. Because when we are doing these techniques, we're asking, is the evidence enough to change our minds? Is the estimate good enough? That notion of good enough doesn't make sense if our mind isn't set. So if you're totally agnostic, look at how the data have fallen out. Okay, it's on this side of the bar, off we go. The complicated stuff makes sense when you already have a preference. Now, in machine learning, what would your preference be? Launch it or don't launch it? Well, that's up to the decision maker. Be honest with yourselves. If your preference by default is launch the thing, and you have to be talked out of launching it, that's a very different analysis. But I think it's usually safer to be on the side of how about don't launch it by default, unless we can be talked out of it by the evidence. So we will err on the side of if we're ignorant, we won't release this thing on the world. Let's see if the evidence changes our mind. Operationalization is what I did force you to do in step 1. This is saying what our words mean, designing our metrics, where we stop using fuzzy words like happiness, and we hammer them down to when we say user happiness, we are referring to the propensity to click 4 or 5 stars on a survey. We understand that this is not happiness. But when we say happiness, that is what we mean. Okay, that's the social science thing of operationalization. So when you design the metric, the performance metric, that is what you were doing. 3, population. Which world are you wanting to succeed in? And therefore, which world does your testing apply to? Are you asking about succeeding on all users you see on Tuesdays ever? Are you asking about the users you expect to see next quarter, the users that are from Africa? What is the population that you wish to draw your conclusions about? And so, in that, you answer that by thinking about where the system needs to operate, where it needs to succeed, where it's important that it doesn't mess up. Simulation, this is an optional step where you're going to go and make some pretend data and try out statistical testing methods and see if the data required by those methods is actually available to you. Do you need to change your logging? And that is also the point when you can bake in the story that you think you have, like, I have a great system, here's its performance, cat, not cat, etc. Can I recover that story? Do I get the right result from my statistical test? That's optional, but in the really complex testing situations, statisticians will tend to do it. Your data strategy. All this has even happened before you've thought about your data ingredients. So going to step 2, how are we collecting them? Or if the data's already collected, what's the history of that? Let's look at some of those data pipelines. Were there any bugs? Is anything wrong with it? How are we going to get the data about the population that we're interested in? Then, assumptions, assumptions, assumptions. The decision maker has to lay out all the assumptions, not just the mathematical assumptions, but assumptions like our logging works, or all the users that we're seeing here are actually all our users, and there's no kind of thing that's missing a whole component of them accidentally that we don't even know about. Hypotheses. This is translating a combination of your criteria and your default action into statistical language. You're saying, under what circumstance are you happy to keep doing what you're doing? And what does the opposite world look like? And you're saying that mathematically. Method selection. Which statistical methods are appropriate? And maybe a statistician has to stitch that together for you. Luckily, in a machine learning setting, typically, the statistical testing is actually pretty easy. Output versus output tends to be an easy sort of test. You don't have to take into account the fact that it came from a neural network. You just have to compare, hey, how many not cats versus cat situations did we get right? Power analysis. What on earth is that thing? Do we have enough data to even come to conclusions? How much data would it take? And code review. Make sure someone's looked at the code because you want to take this decision seriously. Data collection. If your data wasn't collected before, now you execute your data collection strategy. All right. All this other machine learning stuff happens. Testing. You run the test, you run the code, and you report the result. Now, what comes out of that code? Might be something like a p-value or a confidence interval. Most of you took statistics, right? You told me you did. So you won't mind a pop quiz, but we'll have a little twist. Does anyone have a coin for me? Coin? Coin? Who's got a coin? Oh, we've got real money in the audience. That's good. That's good. I hear a jingle. Yeah, thank you. Okay. Everyone mentally pick heads or tails. Flip your mental coin to heads or tails. Got it? Pick heads or tails. Now what I'm going to do is I'm going to flip this coin. And if the result on this coin matches your secret choice, you will be shouting out loud on the count of 3. We'll go on the count of 3. You will be shouting which of these is the correct definition for the p-value. If there is a mismatch between the coin and your choice, you will be shouting which of these is your favorite letter of the alphabet. And no one will know which one you are answering. So you are immunized against ridicule. Because as far as the person next to you is concerned, you are simply telling us your preferences. So everyone please shout out and please answer the question assigned to you by the magical coin. So take a moment, decide what you would pick if there's a match. And of course, if you haven't heard of p-value, you must guess. And pick what you would shout if there is a mismatch and you have to choose your favorite letter, to make your peace with fashion now. Take a moment. All right. We good? Can we do this? All right. We'll have a volunteer. Do it? All right, what do we get? What do we get? Where you can see it.
Okay. That was it. I can't tell what this is. It's a tail.
Tails. It was correct. It does not. Look at it. It's not a trick coin.
It's a tail.
It's a tails. Yeah, okay. So if you picked tails, you're telling us about the p-value. If you picked heads, you're telling us about your favorite letter of the alphabet. On the count of 3, everybody go. 1, 2, 3. And the answer is F. None of the above. Why didn't I hear any F's shouted at me? Now, okay, I was nastily tricking you, but look, I imagine some of you who took stats courses picked tails. So I imagine some of you were attempting to answer about the p-value. And so I am appalled to see you've entirely forgotten what this thing is. Actually, that's pretty normal. I'm not really sad about that. That's probably a sign of healthy psychiatric functioning. What I am appalled by is that whoever taught you statistics did not impress upon you that the p-value is something so complicated, its definition cannot possibly fit on one line. So all of these must be wrong because they are short and pithy. This is a mistake that people make. These statistical concepts, both the p-value and the confidence interval, they are not designed to be pithy to talk about. They are designed for reporting the outcome of a hypothesis test. And the thing that's supposed to be short to talk about is, based on what I see there, default or change. That's short to talk about. The meaning of what this object is, though, is crazy complicated, and it's designed that way. And don't make the mistake of trying to understand it in a pithy way. And if you leave this class today and you report a pithy understanding to your friend, you have missed the point. And if someone else attempts to explain it to you in one line, they don't understand it. Great. So let's actually see what this p-value thing is. Whoa, look at that word salad. So I'm going to read this out. And I'm going to read it out only so we can wallow jointly in the length of it. And what you're going to be watching for is, can she do it in one breath? Or will she have to take a breath in between? Okay, so here we go. A p-value is the probability of obtaining a sample at least as extreme as the one we just observed in a world where the null hypothesis is actually true. I did it. And that probably felt reasonable and sat on your minds and slid off onto the floor. And none of that went in. Fair enough. You got two choices. Either you can really try to understand it, and then you have to, go wrestle with the philosophical meaning, and you'll at best have a tip of the tongue feeling about it if this is your first exposure. Or you can say, fine, I won't understand it, I will just agree to use it appropriately and make sure that I use it safely every time. Okay, so if you just want to use it, here's what's up. Don't worry about what it is. Let's see what it does. When it is small, it makes your null hypothesis look more ridiculous. The smaller it is, the more ridiculous your null hypothesis is. That's not what it is. It is something complicated. That's what it does. If you want to understand it, let's use an analogy to get at this. In a nice modern society, what default action should we take with respect to the suspect of a crime? Innocent is not an action. I'm asking you, here's a person, we have no evidence, what should we do with them? I suggest let's not convict them. When there's no evidence, let's not convict them. How about that? I like that one. Okay, good. Right, now we look at the null hypothesis, which is the world in which that choice makes sense. So if I knew everything about the universe, when is it a good idea not to convict them? When, in fact, they are innocent. The null hypothesis is the world in which you want to do that action. The sample is my evidence, and rejecting the null hypothesis is changing my mind, making a conviction. Here we go. Let's see what it looks like in machine learning. All right, now let's look at this word salad again real quick. A p-value is the probability of finding at least as much damning evidence if the person or dog is actually innocent. So here's how this goes. You come home and you discover this in your kitchen. And imagine it's your dog and your kitchen, otherwise it's a bit stranger. So this is in your kitchen. To compute a p-value, you have to have incredible self-control. You have to take a big deep breath and go, okay, Fido. I'm going to imagine that you are innocent. You did not go sticking your head in the garbage bin. Okay, you're innocent. Now, in this world I've imagined where you're innocent, how surprising is this evidence? Or something even worse than this. How much would it surprise me? And if you live with an 8-year-old, maybe you answer not so very surprising. Perfectly plausible that 8-year-old put a new collar on doggy. And then you will say, I learned nothing. I don't know if you're innocent or not because I have no compelling evidence. But say you live alone, just you and Fido. You can still imagine a way in which that evidence or something even crazier happens. Maybe your crazy next-door neighbor climbs in through the window, runs all around your apartment, puts the bin lid on the dog's head and out the window again. This is possible. It's just not very probable. The probability is so teensy tiny that squinting at it makes you feel ridiculous. And so you say, Fido, I find you guilty of digging around in the rubbish bin. And that probability of seeing evidence that's at least as bad as your evidence, in the world where you should have cheerfully done your default action, that is what the p-value is. And similarly in this machine learning setting, and I'm hopelessly addicted to murder mysteries. In fact, if you want to email me with some suggestions of like some super obscure detective thing that I wouldn't have watched already, I mean, I'm forced to source them from Russia now. When I watch these things, I am computing p-values. So geek. Though I submit to you, if you like detective stories, you are also computing p-values. Let's see. We have an episode. A victim is found dead in his apartment. The suspect is the victim's best friend. The police search the victim's apartment for fingerprints, and they discover a wine glass with the suspect's fingerprints on it in the victim's apartment. How do we feel? Convict? Guilty? No? So innocent then, yeah? Innocent? Of course not. You learn nothing here. This does not tell you that the suspect is certainly innocent. It does not tell you that you're making the right choice by leaving them out of prison. It tells you nothing. But because your default action says, upon learning nothing, I leave this person out of prison, that's what you go and do. But you learn nothing, because this evidence is not informative, doesn't make you change your mind. A little reminder here. Okay, on the other hand, imagine if instead of a wine glass, they found the murder weapon with the suspect's fingerprints on it. How are you feeling now? Convict? Guilty? I see some people nodding, and I see some people vehemently shaking their heads, and that is exactly the point. You are comparing the strength of this evidence against a threshold that you have set for how much evidence you require in order to pull the trigger, if you will. And different people have different tolerances for the risk of being wrong and sending an innocent person to prison. And so when you do the testing, kind of the whole point of the procedure is that way at the beginning, the decision maker gets to say, here is where I set my tolerance for the risk of making a mistake. And when I have set those risk preferences, subject to them, let's see if I should change my mind or if I should keep doing what I was going to do. And so the results are individual to the decision maker who has set those risk parameters up front. Statistically significant means nothing to you unless you have chosen what your risk profile is, what assumptions you're willing to live with, and how you want to frame the whole decision. The best you can do with it as an innocent bystander is be inspired or not, and not take it too seriously. So this is a decision-making tool where you are allowed to specify very clearly how much risk you're willing to take, and then have the method guarantee that it sends you to one action or another action in a way that makes sense according to your risk profile. And in this case, the particular number here is the significance level, which is your maximum tolerable probability of leaving your default action incorrectly. So that's the kind of story here, and so it involves a whole lot of settings from the decision maker. It has no meaning unless there was a lot of thinking there about what we were trying to do and how we wanted to execute the decision. When can you skip testing? If there is no decision to make. If you, the decision maker, have said this isn't that important, I'm already going to go with building it no matter what, you don't have to do this. But if it matters, and if you want to control your risk, then you want to go and do this stuff. So make it sound like a very short part of this course, just because there's another course that covers all of that. It's actually a much huger piece. So this is where the statistical rigor enters the picture. So, key message, testing is the final frontier before you take your model live. If testing fails, you can only try again if you have the ability to collect a data set that is a legitimate testing data set. That means a pristine data set. If you have data constantly streaming in, you're in that lucky situation where you can always go try again. Everything is a dress rehearsal for what happens next. Whereas if you're in the situation where you have a static data set and that is all that you can use, well, if you fail testing, pens down, no more machine learning for you. Please have the strength of character, the guts, the courage to accept those results. It says this model is dead now. if testing fails. Please kill it. Don't start bargaining. Don't be like, oh, I could adjust my settings for my risk tolerance profile to let this thing sneak out. That's kind of missing the whole point. If you were going to launch it anyway, then just launch it anyway and save everyone the stress. And please don't test the same model on the new pristine dataset. If your goal is to launch some poisonous rubbish, you know you can just collect a dataset. Because you're doing statistical testing, there's some random error, right? So you collect a dataset. Did I get the metric I wanted? No, throw away the dataset. Don't even tell anyone I've done it. Get another dataset. How did we do on this one? Keep going until one of them works out. That's the only one you tell anyone about. And off you go. The point here is that when your model fails testing, your model is dead. A different model can be tested later with a new test dataset. Not this one. This one is dead. When are we willing to skip testing? If you have no standards, essentially. If you say, no matter how good this model is, I'm okay to take it to the next stage, I'm fine with building it. Well, in that case, don't worry about testing, just go straight to the next stage. And you can't report performance honestly. So if an SVP asks you, hey, how good is this thing actually? Unless you've done this step, you go, here's my training performance, it's worse than this. It might be minus infinity for all we know. Somewhere between this and minus infinity. That's the answer you give. So if you want to be able to give an honest answer, you got to do this step. And it's okay to skip, again, if you're happy to just build it and you don't need to do any honest performance reporting. So please never test on data that was involved in any way in training or validation. Kind of the whole game is looking at the evidence after you've set the decision criteria and the risk criteria and saying something like, in the world where the null hypothesis is true, does this evidence surprise me? And so if you've already seen what's in these data and you already know that they pass all your evaluations because you've already trained or validated on them, how can you ever be surprised by the evidence? I mean, you've already picked the answer, you've cherry-picked the answer. So though you can still compute p-values and confidence intervals, they don't make any sense there. It's not a fair statement of how we're doing. So please never test on data that was used for anything else. You're going to fool yourself into launching something horrible. And so, just to make sure that we all stay safe around here, I'm going to extract a promise from you now out loud. So please repeat after me, everybody. I will never test on data that was involved in any way by myself or my colleagues in training or validation. And that is all of our stock portfolios now singing in delight, because now we're not going to make some horrible messes around here, and all of our users are also singing in delight because we're going to release nice things that they're going to like, enjoy, and that are going to make their lives better. And of course, because you've given me this promise, and you consider yourself honorable, you keep your promises, you cannot find yourself in the following situation, where you do not even know what data set your data point belongs to. That is why you need to make sure that when you split your damn data, as I like to say, it is recoverable, that split. You will be able to know which data set something is assigned to. And so you cannot just use some kind of process like where you do some querying and there's a little bit of randomization in the back end and it spits you out 3 data sets and then you forget all about which ones they were and then you rerun it and it gives you 3 other ones. That's not allowed anymore. Now you have to start storing either the ID tags or having some kind of deterministic approach, like if it comes from a Tuesday, it's in training. If it comes from a Wednesday, it's in validation, and so forth. So plan to actually store the IDs. And step 9 is finished. You have a document detailing whether or not you're going to take it from prototype to production. And machine learning doesn't have to involve these big launches in production. I mean, it could just be taking that wine picker model, writing it down on a piece of paper, putting it in your pocket, and going to the bottle store. Or it could be a whole engineering symphony. Let's talk about productionizing a machine learning system. Just launch it, right? Like the rocket just has to go up. That's all there is to it. There's a little more to it, especially since what you have right now is not that, but that. And you have to launch that, but you have that. So there will be some things you need to do to actually enable this thing to run with all the rest of your intense infrastructure. Then you'll need to retest it on live traffic, and the whole time you will need to stay very cautious. I've chilled out a little, but I'm still, the echoes of the statistician mode are still ringing there. So, as you start thinking about how to do the engineering, let's go through a few good ideas. But first, a little reminder. Machine learning is the high-interest credit card of technical debt. You are signing yourself up for the gift that keeps giving. Okay, now that we know that. Also, let's mention that this serving part is not trivial. Please do invest in good engineering or you will regret it. So as you are designing the actual grown-up version of the system, here are just a few topics that I really hope your team talks about before you release this thing. So this section won't tell you how to solve these problems. That'll depend on your application. But please don't skip the part where you think about these problems. So first things first, most production machine learning systems have new data flowing in. So why not retrain our model? Why not refresh the parameter settings based on what's coming in? Hey, good idea, do it. So steps 6 through 9, what we looked at, they tend to take place offline. That prototyping tends to be an offline thing where you've got that static data set, you play with it, you split it. But then, after that, you now have new data flowing in and you can adjust your solution based on what's flowing in. So do that. Think about a few things on the way. The first, what's the good direction to repurpose data? Let's examine. What makes a dataset a valid dataset for training? Pretty much anything goes, with a little asterisk which we'll deal with later, but for now, whatever, anything. How about validation? Back to our professor analogy. What's good for validation? Only data where we have not dug into the individual instances, where we don't know about the individual patterns in it. And how about testing? Totally pristine. And so, flowing this way is a bad idea, but you are allowed to repurpose backwards. Any old exam questions are allowed to be discussed with the students in class later to help them learn. Then, have you separated querying and retraining? So sometimes you hear this complaint. Machine learning is too slow to use in production. Okay. The retraining part is the slowest part. And so if you insist on doing things in the following way, the user comes and wants something from you. You've just finished with the previous user. You've just gotten the data from the previous user. If you now take that data point and you start retraining the whole thing based on that data point, and you say to current user, whoa, we just have to wait 5 minutes while I make my adjustments, then of course the user is going to be long gone. So instead, what you should be doing is keeping these things separate. Retraining is happening in an attic somewhere where the users are not seeing it on the fly, unless you have some specific algorithm that's really, really fast. But if you don't, separate the two, retrain over there in the attic, and then when the egg timer goes ding, new model is ready, test it, of course, and then plug it in, change the engine in flight so no user ever sees the bump. So you don't have to think of this as a bottleneck piece in your pipeline. Please know the speed of your retraining. How long does it actually take for this algorithm to update itself? Are we talking a weekend, a minute, a second? What is it? Because that'll determine how you want to do the engineering there. And then you want to think through the frequency of retraining and the data. You want to think about how fast your world is changing. So we've already seen this sentence. The world represented by your training data is the only world that you're going to succeed on. You should really bear that in mind. And in addition, you should always think about whether the world that you are asking your system to learn from is actually the world you wanted to learn. Is it relevant? So when you think about the frequency of retraining, you're thinking about how quickly your world is changing and sliding away from what it used to be. So for an application like spam detection, the spammers are trying to mess with you all the time, and they're changing their approach very rapidly, so you will have to change your machine learning solutions rapidly as well to stay current. If you say, oh, I'll just retrain this thing 2 years later, I'll leave it for now, by the time 2 years roll around, you may as well not even have any kind of spam filtering. On the other hand, something like language translation, well, language doesn't change that quickly, and you don't need to try to retrain that language model every day. So you want to retrain kind of just a little faster than the speed at which your world changes. So the speed with which your world changes kind of determines the frequency you require. And then you could go a little faster than that if you're rich in terms of computing resources. And always beware the training serving skew. The world you trained this model in is the world it's going to succeed in. Sometimes your training validation test data set that you use for prototyping just isn't like the data that you deal with live. And so that means any model that you've already tested, well, it works, just works in a different world. Works in the world you tested it in. And maybe it doesn't work in yours. This is your other nightmare. The first one was called what? Overfitting. Right. Training serving skew is the second nightmare. This is where you trained your model to work in some other world, and that just happens not to be the world you actually inhabit. And so great, your model works, just not in this world. In order to not be eaten alive by that, you'll need to do live testing and really think about what world you are dealing with. So, a classic example of this is fleeting changes in the data. Say you've determined that your world changes so rapidly that any data older than 3 months is just irrelevant. Shouldn't be part of your model, you only want the last 3 months. Cool. And now it's February, and maybe this is a retail situation, some retail application, and 3 months back does include Christmas. And maybe for your retail environment, Christmas is just a different planet from the rest of the year. Things are entirely different, but you need to succeed now in February. Maybe the information from Christmas is just simply irrelevant. It does more harm than good. Then you want to be able to exclude it. You don't want to have this attitude of, oh, any data I can, I want to use it. All of it is best. No, you want to get a rich representation of the most relevant world. And so if you get some rubbish that's not relevant, you want to be able to not see it. Now, if you don't think about this when you're designing your system in the first place, then maybe no one thought that it would be necessary to selectively blind the system. I have seen such stuff, by the way. And then when people go, oh, whoops, we actually want to exclude this data, they have to go and delete the data and rerun on all. This kind of thing happens especially if you don't think about what happens if your logging breaks, which it might. Right? There might just be a day when pure rubbish is coming in, and you don't want that day to influence your model. You don't want to have to go and root around and delete the original data. You would much rather just say, I happen to know that January 1st was bad, don't look at January 1st. But then you have to design the system to have that capability. Then, machine learning systems rarely exist in isolation when we get excited and everything becomes machine learning. What that means is that machine learning systems are chained to other machine learning systems, which are chained to other machine learning systems. So in other words, the ingredients to your model come from the output of another machine learning model that comes from another machine learning model. And they are all changing because they're all retraining themselves in production. You do need to think about what it means that all the parts are moving when you are building yours. And the analogy perspective is you are a chef. You're running an industrial scale kitchen. Your potatoes might tomorrow no longer be what you think potatoes are. The bag still says potatoes on it, but inside the potato it's a completely different chemical composition. How would you run your kitchen if you knew that you had the possibility of that? That's the kind of thinking you're going to have to do during this design. And let's talk about making tiny changes to machine learning code. You know that moment when one of the folks that isn't on the core machine learning engineering staff kind of looks at your code base and is like, the tiny thing, I'm just going to make it like a little adjustment. It's not really even a machine learning adjustment, I'm just going to do a tiny thing. Well, let me explain about tiny changes. There is no such thing as a tiny change. Please remember, changing anything in machine learning changes everything. Don't do what you might usually do, which is go make that tiny change and say, it's okay, we don't need to do any testing, I know exactly what I did here. Always test, no matter how small that change is. So, what happens if your model fails retesting? Oh, there's a typo here. Who can see it? In this sentence. It's not a hyphen. When, not if. Very nice. Yeah, this is not an if, this is a when. What will you do when your model fails retesting? Because it will fail retesting. Have you built in the capability to revert to an earlier version? If you haven't, all you have is an alert going, broken, broken, everything is broken, it's complicated and it's broken, and it's live, oh dear. Now, I can't tell you how you're actually going to fix that, because that's going to depend on your application. Maybe you're going to revert to an earlier version, but what if the earlier version is also broken? Because broken, it's 2008 and the financial system is experiencing some stuff. Maybe all your models are broken because the world has changed fundamentally really quickly right out from under your feet. What are you going to do about that? Now, I can't tell you what you should do, but I can tell you that it is unacceptable not to think about it in advance. When it's breaking is not the time to form a plan. And hoping that it doesn't happen is not a strategy. As our site reliability folk like to say, hope is not a strategy. Plan for it going wrong, and then consider yourself lucky if it doesn't. That's the safest thing to do. You might switch to another model, you might switch to a rule-based system, you might send it to humans to make the decisions temporarily while engineers are fixing whatever's gone wrong, but please have a plan so it doesn't bleed money or whatever. And another pitfall, you will meet the long tail. What does the long tail refer to? I suppose someone was smoking something when they looked at a histogram, and they thought a histogram where it's counts, right? The histogram bins up your data range, and when there's a lot that falls in a bin, it's high, and then it's low as there's less and less and less in that bin. They looked at this thing and they were like, that looks like an animal with a tail. Anyway, it means the counts are very low. These are rare situations, weirdo situations, data points. And chances are, whatever your prototyping was, it wasn't at the same scale that your production is going to be. So you just run this thing long enough in production, you're going to see the weirdo data points. And I have a fantastically meta story about this. Please no one be offended. So I used to do this whole song and dance about weirdos this, weirdos that. And for my example, I piloted this course with a bunch of Googlers around New York. For my example, I used to say, who here has the joint hobbies of ballet and taxidermy? And no one would raise their hands, and it would be ha-ha. And I would talk about, well, at scale, you meet the weirdos. Anyway, as I expanded this course, eventually, about 4,000 Googlers in or so, in Mountain View, after I'm halfway into a whole thing about weirdos, this and that, hand goes up. I had never planned for someone actually saying yes to ballet and taxidermy. I was like Hugh Grant in an awkward British comedy, blah, 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 trying to fix it. Just digging myself deeper into embarrassment. Didn't take my own advice. I should have had a plan for what would have happened when I finally meet the person. And the point was that this actually happened to me directly right in the example that talks about it. The example was saying that at scale you will meet the weirdo who does. And then what happened was, sorry person, very good set of hobbies. And so you should expect that it will mess up, and you should have a plan for what you will do. Like, can you identify the person, store their name, and maybe send them a bouquet later or something? What is your plan for when the mistake happens? You won't be able to make sure that it doesn't happen. Some mistakes that you don't anticipate will happen. These systems make mistakes. Have safety nets in place that are designed to deal gracefully with those mistakes. And in general, data points that are unlike the data that you have trained the system on are going to create mess-ups for you. When the strange data comes in, you'll probably mishandle it. Are you checking whether the data points are strange? Do you have a way to do that? For some systems, that's easy. For some, it's really, really hard. But say you're dealing with something where it's easy, and you know you've never seen anything like this before. It's some kind of language translation thing from, I don't know, English to Spanish, and now there's an umlaut. Like, maybe tag that. I don't know if there's English words with umlauts in them, but, you know, maybe you didn't plan for it, right? So tag the strange new things, and maybe if you identify that, have some other logic that says, careful, careful, do we have an alternative way to handle this situation? Maybe it should tag that for you to review later, or maybe it should even consider switching to manual operation for that situation because it knows it can't handle that situation. That data point is too different from every other data point that it has seen. But most of all, think about whether you will fail gracefully if the data are completely different. And if they start coming in rapidly because the world is changing very quickly because aliens have landed or something, will your system detect that fast enough for you to be able to stop the damage? Your system only works in the world that it is designed to work in. When that world changes, you'll have problems. So please plan to fail gracefully. And one of our final questions, how will you prevent embarrassment? The answer to this is partially. Things will happen that will embarrass you because you won't be able to think up all the ways that things can go wrong in advance. Here's some examples. You decide to train a system to converse by chat with your users like humans do. And what do? You grab a whole lot of real examples of human speech, human texting conversations for one another, and you train your system on it, and then you release it to talk to your users, and you are surprised when it embarrasses you by learning profanity and using that upon your users. You could have seen that coming. The world represented by your training data has this stuff. The system learns that world. It doesn't have any of the additional things like good judgment if you didn't build that. Well, it's just a pattern-finding thinger. It doesn't think. So don't be surprised when it starts using that on your users. Now, some of you could have seen that coming. Maybe others wouldn't have. And if you get caught by surprise, what you don't want to do is be in this situation where you have to say to your team, okay, gather around, let's figure out how to fix this next quarter. And in the meantime, here is this thing cursing out your users. No, you want to be able to fix it immediately. And in order to be able to do that, you need to build a policy layer, and that policy layer needs to grow up alongside your system. So what's a policy layer? It's a little like the filter that we develop as people. When you're 5 years old or whatever, You may look at someone's outfit, and you may blurt out, "Oh dear, what are you wearing? That's a ridiculous outfit." When you are a grown-up, you still think that. It's not like you don't think that. But now you have a policy layer, a filter, where you're like, just before I blurt that out, should I actually output this output? Maybe I should instead say, how about that weather today? That is what a policy layer does. It checks the output. It doesn't go and tamper with the learning. You still think it. But if the output is unacceptable, clips it out. And so you build this thing in a way that is really easy to interact with the policy layer so that when the embarrassing thing happens, you can go and adjust the policy. Okay, from now on, anything that's in this list of swear words just isn't allowed out. Okay, for now, we've staved off embarrassment. And then that's just fixing, of course, the symptom. You want to go and look at retraining and fixing the underlying thing later on, and that is what you gather your team around to think about how that will be done by next quarter. Here's another example of the same kind of thing. In this country, when users buy a baseball bat, what do you think is the most likely item that they buy alongside the baseball bat? A baseball or a glove or something like that, something for playing the game. Now imagine a fictional country where they don't play baseball, but they have a lot of crime. In that country, what do you think is the most likely item bought alongside a baseball bat? Now, this is not a nice world that I have made up for you, but it might just be the reality. Do you want to blurt that out directly at your users? Or do you maybe want to be able to have a think about it? Like, here you are, who's used to baseball in America, you've gone to this country on holiday, you maybe want to play baseball with your new friends, you go to the shopping website and here it tells you this. In your cart is a baseball bat. Users like you, would you like to consider buying a balaclava? No one wants that situation. So please, when you're building these things, if that does happen to a user, they will probably start posting about it, and then social media explodes, and then everyone is trying to poke at your system and find all its funny failures, and that gets embarrassing really quickly, so you want to be able to shut that down. In general, the solution that we're coming around to is building safety nets in the form of policy layers that sit on top of your machine learning system's logic and check whether what it's about to blurt out is acceptable or not. And if it isn't, suppress that. If it looks like a curse word, just don't let it out there. And make sure that you are building this policy layer alongside your other productionization efforts. Build this policy layer so that it's really easy to interact with it instantly. So that when the embarrassment happens, make it so that it can't show up again. Otherwise, everyone will be trying to get your system to do this embarrassing behavior and then blogging about it, and everyone is laughing at you. So you want to be able to deal with it instantly, fix the problem. And if you've engineered everything without a policy layer, you have to go and do big, heavy things like retrain the whole thing and fundamentally change how your inputs are dealt with and logged. You don't want to have to do that. That takes too long. You might want to do that later to fix the underlying problem, not just the symptoms, but in the meantime, have a way to deal with the symptoms so you're not hurting your users or embarrassing yourself. Policy layers, those safety nets, they keep everybody safe. So make sure that you have that on top of your system. And again, if you think about where the fix is most reliable also, think about how you might prevent a kid from using profanity. Option 1, try to shield them and don't show them anything that might teach them something bad. Or option 2, let them see everything they want, but the moment that word tries to bubble to the surface, clipped out, can't even be uttered. Which one is the more reliable fix? It's probably the second one. Because if you try to curate your evidence too much, There's a lot of good intention in saying, this thing would be offensive to even allow the system to learn from, and then you snip it out. Full good intentions. Meanwhile, the system can recover that signal just by combining some other features, some other way to get you exactly that all over again. And you just think you've solved the problem, but you haven't. It's probably safest. You can aim at the root cause, sure, try your best to fix that in the underlying learning, but have that second backup thing that really guarantees that no badness escapes. So step 10 is finished. You now have your production-ready system with automated retraining and safety nets. Now you make your launch decision in step 11. Just when you think this thing is perfect with all its bells and whistles and safety nets and whatnot, and then you release it upon your users, you just release it at 100% and please don't launch it all at once. Little gradual releases is a good idea. Do a gradual ramp up. Serve 1% of your traffic first. Are we okay? Because if there's a big bug in there, you don't want to discover that with all of your traffic served. And consider doing an experiment. So remember this monster of training serving skew. You need to check that it works well in the world where it's going. You'll only know if it does that if you test it in that world. So see what its impact is on that world. And what an experiment lets you do is compare the impact of this thing versus another alternative. So maybe you have a next best way to solve this problem. Now you can race the two and see if yours is better. And if it's better, how much better is it? Because it's always nice to add to your performance reviews. And we also save this many dollars per whatever period and such stuff. Okay. So you'll do your live traffic experiment with another statistical hypothesis test. Very rigorous test, and even more important than your previous one. Your previous testing phase was about, am I going to spend the money to productionize, yes or no? Now that you've done that whole productionization symphony, this one is really the test. Is this okay to subject my users to at 100% or not? Don't skip this. Now, an experiment, contrary to popular belief, is not just let's just see what happens. If you want to describe that, you can use words like trial, or pilot, investigation, analysis, launch. All those things are let's just see what happens. An experiment is something special. It has these three components. And let's see whether our situation also has these three components. First, a hypothesis. Yep, that's the question of, is performance good enough to launch? Next, different treatments. So we can't just passively observe data. We must impose our will on the universe. We must do different things to different parts of reality. So different units get different treatment. Okay, we can serve some users with our system and some users with the alternative. And then finally, who gets which treatment is chosen at random. Well, that depends on your infrastructure, which is why you're thinking about building all this infrastructure up front. If you don't have the ability to serve things serve your traffic randomly, then it's going to be pretty hard to do live traffic experiments. So maybe you want to consider that infrastructure. But if you have all of this, congratulations, you can do a legitimate statistical experiment. You can find out what the impact is of your system on your users. You can find out if you should launch it. If your performance is worse than the alternative, abort, abort, abort. There's no analysis you even need there. I'll tell you the result of the statistical test. It's don't launch. But if the performance is better and enough better according to the criteria you've set, then you can launch it with a clean conscience, and you can say what its impact is. There's massive back pats for you. So you've ramped up, you've launched it. Now you're serving your model to users, you're using a policy layer, you're staying cautious. Step 12, that technical debt. Does your model stand the test of time? Well, see, it worked when I bought it, so it still works, right? Not necessarily. You have to keep retesting it even if you're not retraining it. Your world might change. And then maybe there is that training serving skew all over again. So you need to periodically retest. But not only that, it's a good idea to keep your finger on the pulse of what's going on with the world generally. So you want some dashboards that tell you a little bit about the distributions of your inputs. Something like you are predicting cat, not cat in people's photograph, and you have some dashboard that tracks what's the proportion of cat among all the photos. And then all of a sudden that thing spikes. Maybe you've got some serious infrastructure problems, maybe something dramatic changed in the world. And you're also looking at your product and you're used to seeing not that many users who are, I don't know, under 18, and all of a sudden, it jumps. What on earth happened? This is not the time to write a statistical treatise on what this all means. This is a way to hit that big red button just in case something is going on. So it's really important to monitor, because the world may be saying to your model, hey, it's not you, it's me. You're fine. It's just I've changed. We're not. You're fine, I'm different now. So you've got to listen to what the world is saying and making sure that that's not happening under your nose. And another thing that I would love to do is anytime a team builds a machine learning system, because maintenance and monitoring is a lot harder for it than for other kinds of systems, I would love to just chain that team to the wall and force them to maintain this unholy beast that they have created in perpetuity. Unfortunately, that's not humane. They've stopped me many times. People want to move on to other roles. So if we're going to let people do that, then they had better take documentation even more seriously than they do for other systems. And they have to have a plan also for how they're going to train the people that come and have to support this thing. I mean, if they built it, they understand all the nooks and crannies. It is really hard to make sense of it if you inherit it, and there's no good plan of transferring that knowledge. You don't want to be doing machine learning for its own sake because it sounds cool. I mean, it is a high-interest technical debt credit card. You want to be doing it only because it is worth it to do it. And it's worth it to have that fuss, because it's going to be difficult and require constant effort. So it's got to work. It's got to be enough better than the alternative for you to want to fuss with it. So step 12 is never finished. This is the gift that keeps giving, but a good start is having a monitoring plan, a maintenance plan, tracking dashboards, and stellar documentation. And that is our 12 steps. And so we are done with this section, and if all you wanted was the 12 steps, that's it. Sneak out, enjoy playing outside. You have an alibi until 5 o'clock, so no one's going to come looking for you. But those who are interested, we will be opening the black box at 3 o'clock. My brave survivors. You don't want to play outside? We talked all about how you don't need to know anything about what's under the hood of these things. It's raining! I am ever so slightly more entertaining than being stuck in the rain. That's good. As long as I can maintain that, everything, all is well. So let's open this black box then and have a look at how some of these things go. So we've already looked at linear regression. I moved it earlier in our menu. And now we'll go through in this order, and we'll just get a taste, we'll just get a flavor. So as with regression, we don't go into the nitty-gritty, because I leave that for homework for you. Enjoy the code, enjoy the textbooks. We're just going to get like a feel for it together very quickly. So first things first, clustering. In a nutshell, this is about birds of a feather flocking together. Our example algorithm that we will look at is k-means, and we've already seen this idea earlier in the course. Here are some photographs, and then we said put like things with like, and our clustering algorithm made 2 clusters based on cat 1 and cat 2, or maybe based on is the tongue sticking out, or is the tongue not sticking out, sitting, standing, cat selfie, not cat selfie, or what have you. That's clustering algorithms. So, for our example, do you see any clusters here? I see some clusters by eye, sure, something like that, yeah? Okay. Could we have done this without having labels? That is a trick question to see if you are paying attention. There are no labels here. So Of course, this is unsupervised learning. All we know about is the ingredients, and we are finding those clusters ourselves. Could we have done this without using our eyes? Sure, otherwise what are we doing in this section? So, welcome to k-means. The K in k-means stands for the number of clusters that you are requesting. So this is up to you when you are using the algorithm. You are ordering as if from a menu, I would like 3 clusters, please, or I would like 2 clusters, please. That's the K. What about means? The means are something like centers of mass or gravity. So don't worry about what the math is behind centers. Just think of that kind of as a center of gravity. And your intuition for it will be pretty good, actually. I'll be computing them for you, but I'll be having you guess first where it's going to be, and you'll notice that you'll get the hang very quickly of what this object means. So the technique begins by sprinkling some labels throughout our data entirely at random. Boom. We have a blue cluster and a red cluster. What do you think of the clustering? Looks good? Nice clusters? Yeah, I don't like them either. Let's compute the centroids, shall we? First, do you think that they will be close together or far apart? The blue centroid and the red centroid? Close together? Sure, because there's quite a lot of points and they were assigned at random. There's no particular reason why all the reds have to be in one place with a very different center of gravity from all the blue ones. Fine. Okay, do you think it's going to be slap bang in the middle here or somewhere else? Maybe pulled a little bit towards where there's more points, so a little bit down and left, yeah? There? Something like that. You'll get closer, don't worry, as you see more of this. Okay, what's next? We will forget the old cluster IDs. Boom, forgotten. And then we are going to do something of such astounding brilliance you will never see it coming. We're simply going to give each point the color of the centroid closest to it. So, red or blue for this one? Red or blue for this one? Blue. How about this one? That is why we let the machine do it. It is better at this than you are. Turns out that's red. How do you feel about the clustering now? We're getting somewhere? Yeah, looking better. Let's keep going. Let's recompute the centroids and take a moment to guess where they're going to be. They're going to be far apart or close together? Far apart, and how are you doing? Yeah? Okay, you kind of get what these things are now. And again, we forget the labels. And again, we do the same thing. ID of the nearest centroid. And then we go round and round doing the same thing until the clusters stop changing. Spoiler alert, there will be no further changes. This is the last solution. So round and round, nothing changes. These are our clusters. Job done. So that is k-means. Now, standard burning questions from the audience. I want to see if I can anticipate them. 2 questions that are burning. How do you pick K? That's not on my next slide, so I'll address that right off the bat. Depends if we're doing analytics or if we're doing machine learning. So again, you can use the same algorithm for different applications. If you're doing analytics, you don't know what you're hunting for, you're just trying to get inspired. So what might you do? In a loop, K equals 2. Anything interesting yet? No, how about K equals 3? Anything interesting? How about K equals 4? And you look at the results every time and you see if anything feels compelling to you. It's a pretty nice approach to data mining. If this is a machine learning application, you know exactly why you are trying to do this. Maybe you have some kind of nice app where the users put pictures of themselves and their friends, and then based on the photographs for everyone's amusement, in some way it splits that into 2 groups, puts party hats of different colors on the 2 groups and says these are your sports teams for beer pong or something. Then you know what the purpose of that app is, and you've just said it's 2 teams that you're trying to make, so then fit for purpose, 2 will be the split. It depends what you're using it for. Other questions? Some typical ones I tend to have yelled at me. Google engineers are like, will it stop? tell me, will it stop? Will it just keep going round and round? Because you know what? If I get a point that's equidistant between these two clusters, it could just like bounce back and forth between the two because the coin keeps flipping. Oh, take a deep breath. Yes, it converges because the actual implementation is a little smarter than this and involves, of course, a loss function. And the loss function has to do with the distance of the points to the nearest centroid. And so, even if the point is equidistant, well, the distance computed is still the same, so the scoring for the loss function is still the same. So even if the point flip-flops from blue to red, it still considers itself to be finished and will stop and give you the answer. How about same result every time? What do you think?
Yeah, I think so.
Oh, fight! Fight! The answer is no. The way that you do the random sprinkling of the labels does matter. Imagine if you have 50 data points and you ask for 49 clusters. Try that out. You will notice that you don't get the same result for which one has 2 points in it every time. So I have a try it first slide for all our methods, and here you will try it first if you have no labels. This tends to be the first unsupervised learning thing you go for if you have no particular reason to suspect you should be using a different one. And this is where you want to split your instances into groups. Another kind of unsupervised learning approach is one where you are looking for anomalies, what is unusual. That's a different thing, we won't talk about it here. This one is where you're going for separating things into groups. Now, strangely, I can never understand this. Students get K and N confused with K-means. And I don't know why they do this, because these techniques have nothing in common. Except that maybe if you just squint just right, these two ends together look like an M. That is about it. That is all these techniques have in common. So let's see what K nearest neighbors is. It is part of a class of algorithms called lazy learning. Oh, so cute. And what is lazier than having your recipe be the whole data set? I'm not going to bother to summarize it for you, just use the whole thing. So let me show you an example. Here is a desk area. We've got engineers and managers sitting in this desk area. And we have the north-south coordinates and the east-west coordinates. And we'll see this thing in action with K equals 5. So now the technique reads 5 nearest neighbors. You have no idea what's coming. That K, by the way, it is a hyperparameter. And so we'll need to tune it, and we'll see that shortly. But for now, meet Heather and Sophie, that's where they sit, and we will use 5 nearest neighbors to diagnose them as engineer or manager. First, Sophie, we will find her 5 nearest neighbors in space. There they are. And all we do is we say, what's the most common label? Let's give her that label, so we say she is an engineer. Then we do the same thing for Heather. And that manager is just closer than this engineer, and so Heather gets the manager label. Now, of course, K matters a hang of a lot, which is why you will want to do hyperparameter tuning, and the way you can tune it is simply the start at 1, go to 2, go to 3, if you wish to. Hyperparameter tuning is easy for this case. It gets hard when you've got lots of different hyperparameters that you have to deal with, and it takes a long time to rerun your model, and now you can't just brute force find the right answer. Now, let's look at the effect of K. If we set K to 15, there is nowhere that poor Heather can hide. She will get the engineer label just simply because there's more engineers. If we set K equals 1, and we have my desk nearby, and I'm a decision scientist, then, or statistician, or whatever I am, then poor Heather gets that same title, decision whatnot, even though there's only one of me. And so K equals 1 is where you get judged by your one weirdo best friend rather than the diversity of the friendships that you hold. So you will want to tune and see what's actually working for you. So this has nothing to do with K-means. This is a supervised learning technique. All the following techniques will be supervised learning. It was only K means that was unsupervised in this list. So when do we try it first? If we've got labels. They can be any labels. They don't have to be categories. They can also be numbers. We can find my 5 nearest neighbors and use them to predict salary by finding the median salary among those nearest neighbors, right? Same kind of reasoning. And of course, we don't only have to do geographical stuff with it. We can say, who are my nearest neighbors in the audience in terms of shoulder width, maybe, and torso length, and we can use that for sizing a t-shirt. We use that to predict t-shirt size. And it doesn't just have to be 2 features, we can do this for more features, but careful. This really requires a tall, skinny dataset. It doesn't like situations where you've got too many features and not enough instances. It really suffers from what is called the curse of dimensionality. So what is that thing? Such a machine learning term, it's great. I like to think of it as some methods really don't like it when data points are lonely in space. So let me explain. If I shine a bright light from that wall onto there, and it projects all your shadows against that wall, so now your shadows are in 1 dimension. You are all on top of one another and not lonely at all. Add another dimension along here, and now you're a little more spread out. Now I'm going to add another dimension. Which floor of this building are you sitting on? It's still same east-west, but now the height varies. All of a sudden you look around you, where are my friends? It's lonelier. Now I add another dimension. Which hour of the day are you doing your vigil? Now it's really lonely. And so every time I add a dimension, I don't require only the same amount of data to compensate for it. I need exponentially more people for you to have as many friends around you as you do now. And some methods are really sensitive to loneliness, and so they are really sensitive to the addition of 1 more dimension. Things look very empty around the data point. That is what the curse of dimensionality is about. Okay, this is great for fast model updates. What can be faster than finding out what Heather is and just putting that row underneath the rest of the data set? There you go, there's your updated model. This is good when local structure is key. When you think that maybe if there's a few statisticians around, other ones just pop up like mushrooms, rather than more statisticians as we head towards the North Pole. If you're dealing kind of with the first one, this is a good bet. And in order to pull it off, you have to be able to actually store and query the whole data set, so that shouldn't take forever. Next, support vector machines. That sounds crazy cool and difficult, and you'll be so disappointed to know that all it is about building walls in your data. Now for this section, I'm going to do a fun kind of thing. We're going to develop the method step by step, so we'll go through actually multiple methods in this class of things. We'll need 4 of them. Each time we get an upgrade, and it's sort of a historical note also. How were they upgraded through history? And the rules for this section are that we are only allowed to use 1 straight thing to separate our data. So maybe it's a line, maybe it's a plane, maybe it's a hyperplane. If we want to do curvy stuff, we have to go to a different method. That's allowed, it's just not in this section. So, our application. We have a map, and we have only some of the buildings on that map highlighted here. The blue ones are shiny modern skyscrapers, the pink ones are gorgeous old historical buildings. And you are a city planner. Your job is to make a neighborhood boundary. Where is the historical neighborhood? Where is the modern neighborhood? And what shall we do to separate them? How about put a line? Not that line, not that one. How about that one? Okay, you'll accept this one, will you? What we've just done is tried on various lines that fit, and then we got the first one that works, and we accept that. That method has a name. Stop when you get one that perfectly separates them, and its name is perceptron. For that, you get this name? Seriously? I'm machine learning people. Now, you could have picked that solution. You could have picked this solution. You could pick that solution. There's lots of options. There's lots of options. How do you choose? Maybe you have a preference. Maybe you want to have a principled selection between these. Well, I submit to you PowerPoint skills. Why that thickness of line and not that thickness of line? Or maybe if we stick to the city planner example, you know that one day your successor is going to put some kind of path where you have drawn the boundary. And you don't know if they're going to put a bicycle path or a highway or what. But you notice that for some thicknesses of roads here, it smashes buildings. And you still have a heart. Well, you think maybe you don't want to smash buildings unnecessarily. And so you say to yourself, some of these options are unacceptable. I'm not going to consider them. And looking at this, you're like, actually, there's a way I can squeeze a slightly larger road in here. There it is the biggest one I can put. And the line in the middle of that, that's the one I'm going to go for. And that is named, very creatively, I'm guessing it's statisticians, maximal margin classifier, because that is exactly what it does. It attempts to have the maximum margin around the boundary. And so that's our next method upgrade. What are support vectors? I would have called them points that matter. See, if I take this point and I smash it, it doesn't change my solution in the least. This one, I can move it off the map. As long as I don't move it too close to the road, it doesn't matter to my solution. But these ones over here, if I move them, I get a different road. Those are my support vectors, and this method is going to think about putting boundaries, taking them into account. Now, R, this is a plot in R, is known for its beautiful plotting, and this is not it. I don't know what part of the 80s coughed this up. Like, what colors are these? What's cyan and magenta, and why is this straight line pixelated in this decade? The point, though, is that R is really good for prototyping, and this is what you can get with about 2 lines of code. And with a few more, you can get the beautiful plot. But 2 lines of code and you fit and plot a basic support vector solution. That's pretty nifty. It doesn't take a lot of effort. Whereas if you tried to do it in some more serious production-worthy thing, then it would take you far, far longer than these 2 quick lines. So you try it out in this kind of environment, or some Python package if you prefer that, and then you go to the more serious thing when you're like, okay, this kind of approach is working for me. What if your historical buildings have no respect for anything? Look at them there. They're in the middle of our modern neighborhood. How dare they? We statisticians have a very creative name for this situation. Wait for it. Not linearly separable. As in, you cannot use a line to separate the red from the blue. And the previous 2 methods require you to have linear separability, so they cannot work. So we must upgrade. And our upgrade is to the support vector classifier. The support vector classifier is the kind of solution that most city planners would roll around to eventually. Okay, we'll let them violate the line, but we'll tax them for it. And so now we simply add a tax to the loss function. Things can go on the wrong side, but they do get penalized. And how much you tax them is a hyperparameter that's up to you that you're going to have to tune. So here we go. In R, we can see that we have not got perfect accuracy there, but I much prefer this solution to a horribly overfitted one that tried to do some contorting around these 2 so that it did have perfect performance. I would look at that and be like, is that really going to work on the other buildings that we've left off the map? This is a pretty sensible and reasonable boundary. So that's our support vector classifier. The worst possible situation is where the modern buildings grow up around the historical buildings. This is terrible. Because for this whole section, we are only allowed to use one straight thing to separate the red from the blue. Where are we going to put it? Okay, let's try out our previous support vector classifier. And it suggests, because we have more modern buildings than historical buildings, why don't we put the line up there in the top right-hand corner at plus infinity, plus infinity. Call everything modern and be done with it. That's a little better than calling everything historical and be done with it. Can we do better? We want one more upgrade to support vector machines. And what we will rely on is called the kernel trick. And to explain the kernel trick to you, I have a prop. My trusty cloud, it's a cloud towel. Oh yeah. My towel of the kernel trick. Now, I need you to use imagination. Do your best. And imagine this same thing on my towel. Red ones in the center, blue ones around them. And you need to use a straight thing, a line, a plane, a hyperplane, whatever, to separate the red from the blue. And you look at this and you look at this and you get angrier and angrier and greener until eventually you have become the Incredible Hulk. And the only solution you can think of is to punch the thing because it angers you. And what you do is you punch the space, adding an extra dimension and converting your other axes. And now I can use a plane to decapitate this thing, because the red is now above the blue. So that is what the kernel trick is. And let me show you another plot of that. So here I had some data points. I then make a punch and project them into more dimensions. And in this new space, I can use a plane to cut. So I'm still using a straight thing and I'm still using support vectors. It's all the same business from the previous step. It's just I have transformed the underlying space first. And then once I've done the cutting, I can project down my solution back to the original coordinates. It looks like I used a circle. I really didn't. I used a straight thing. I just punched the towel first. So when frustrated, punch the towel. And at this point, my Google engineers are like, this is the most technical thing you have talked about all day. Tell me more about kernels. Give me all the equations. I have to be like, no. Read a textbook. That's not in the scope of this thing. But then I think, okay, I can't just leave them hanging. I should maybe point them to an educational resource. And I thought to myself, the internet is a magical place, a marvelous place. This is called the kernel trick, yes? I really wonder, is there a website called oneweirdkerneltrick.com? And it turns out that there is such a website. And it is in fact run by someone with a sense of humor who has put real learning resources on there. That, for example, is Vladimir Vapnik, who's one of the co-authors of the original Sport Vector Machines paper, and the other co-author is our head of research in New York, Corinna Cortez, and her face is also on there, along with a lot of other stuff you can go read if you're interested. So oneweirdkerneltrick.com. And when we do an SVM plot in R, we can see that we have much better training performance, only one mistake. So that's our final method. We're like the Incredible Hulk. We punch the space because we get so frustrated. We add a dimension. We transform the original dimensions also as part of doing that. And then we chop it still with a straight thing, project it back down, call it done. So when are you going to try this thing? If you've got binary labels, if you want a flexible boundary shape, not just linear, and this is a solution that lends itself best to moderate scale. If you're working with really large scale, there's another method we'll look at later, logistic regression, where at Google we have done more engineering effort to make that one scale friendly than this one. So you'll prefer logistic regression at larger scale. And now we'll have trees, tree-based methods, decision trees, random forests. Let's have a look at what's going on here. These are, in a nutshell, a bunch of if this, then that for your data. And so I thought, why don't I manufacture an if this then that rule, the traditional programming way, about my movie preferences so you can all recommend movies to me. So I thought about what I like and I came up with this rule. If it is a mystery, a thriller, or a sci-fi movie, hand it to me, I'll like it. And then I thought, but am I not a data scientist? Come now. Should I not maybe add data and see what the performance is of this rule, this algorithm or recipe that I have? Because it doesn't matter whether it came from a machine learning system or I dreamed it out of thin air, I can still assess the performance the same way. See what it predicts, see what the truth is, and look at the results. So what I did was I grabbed the IMDb database, I shuffled it, and then until I couldn't be bothered anymore, and my attention span is about 200 or so, I rated like it, don't like it, like it, don't like it, like it, don't like it, I gotta watch that one, like it, don't like it, anyway. And I have for you the results from the training set, which is something like 100 movies. Let's find out how this rule does. Turns out, precision's pretty good, and I'm aiming for precision here, you know, like with the books. I'm pretty busy, I'll never be able to watch all the movies I like, so let's have a don't waste my time kind of approach here. I'm gonna leave out some good ones, but you know, if you suggest it, hopefully it's likable. And if you follow that rule, 3 out of 4 are gonna go down nicely. It's a relief to me to see that recall is low. That suggests that maybe this doesn't cover the full diversity of my movie preferences. If this were 100% recall, it means I have a very one-track preference, just that, nothing else. Then I thought, all right, why don't I let machine learning have a go? And I'm going to ask for a really simple model, based on any of the features in IMDb, but a decision tree with just one node. I'm going to show you the rule on the next slide. I want you to look at it in this order. First, watch the precision go up. Then watch the recall go up. Then read what the rule is while I stand here cringing. Here we go. If it's long, I'll like it. Above 127 minutes, yes, otherwise no. Now, what does this mean? Well, from a data science standpoint, the only thing it means is that in these data, this rule outperforms my other rule. There is no other thing that it means. If I'm tempted to start spinning stories all about how, yeah, maybe this means something about directors investing more effort in longer movies and so the quality of the movie is whatever, or some story about how Cassie is so pretentious that if I'm tempted to start making such stories, I need to be aware that I'm in danger of overfitting, and I shouldn't take myself seriously unless I go and carefully articulate that story as a hypothesis and then test it in another dataset that I didn't use to form this impression. And if it holds there, then it holds. Now, I didn't have to have such a simple rule. I could have gone for a slightly more complicated one. So let's have 2 nodes. Ah, dear. I'll like it if it's long, but if it isn't, let's have a thriller. Slightly lower precision, but unfortunately this now covers 2/3 of my movie preferences in that set. So simple creature, simple creature. But I could have an even longer rule. A lot of decision tree algorithms, if you don't tell them to stop, they will just keep going and going, and they'll make you quite the tree. Let's read this one. It says, is the runtime more than 132.5 minutes? If yes, then is the runtime more than 143.5 minutes? If yes, is the runtime less than 165.5 minutes? If yes, is the runtime less than 156.5 minutes? Then she'll like it. And your spidey senses are tingling, I hope. What word is bubbling to the tops of your consciousness? Overfitting. Yeah, it fits these data really nicely, but it is probably utter nonsense for the rest of reality. This rule is not going to work if I try to predict movie preferences outside this data set, even though it works really well in training. Look at that, 84% precision, 88% recall. Now, because they tend to be implemented so they make you these big convoluted rules, you will need to run a pruning algorithm to snip, snip, snip back their enthusiasm. And you'll say something like, no more than this many nodes. How do you pick how many nodes? Well, it is a hyperparameter that you're going to need to tune. So that's why you do that tuning step. Decision trees are if this, then that rules, and the resulting recipes are easy to describe to humans. Notice how I don't say interpret. I'm saying easy to describe. I mean, it's hard to beat if someone asks you, how does this thing make its decisions? I say, well, it's as simple as, is it above 127 minutes or below? Very easy to describe. But please don't interpret them without going and following up in other data and actually checking your interpretation. And a little note about interpretability. This is a hot topic for machine learning and AI. Should models be interpretable? And then there's all this fighting. And it's such an angsty debate. And I watch this and I just feel like, can I please translate for both sides why you're miscommunicating? All the ones who are anti-interpretation are doing the machine learning side of data science. Make it work. And they're saying, come on, you don't need to know how it works. Your whole goal here is make it work. So why would you give up performance to be able to ogle that model? That has no use to you anyway. And the other side is like, but how will we get inspired if we don't look in the model and if we can't read it and interpret it? Well, that side is not doing the same work. They are doing data mining, descriptive analytics. They want to have an opportunity to get inspired by data. It's an entirely different process that they're after. And so both of them are right. They're just doing two different jobs. If your job is performance, don't force yourself to only go for these easy-to-read recipes. Get performance and test it properly. If your job is to be inspired by data, then of course you need to be able to see what it's saying to you. And so if your job is data mining, descriptive analytics, this is a lovely, lovely tool. I like to do this when I want to get inspired by data. Even if this has nothing to do with what my final model is going to look like, it's still nice to see how it wants to split the space and suggest to me which parts are worth playing with. Now, behind the scenes, what's going on? So here I have linearly separable yellow and green. Here I have non-linearly separable yellow and green. Here I have the tree. Here I have the support vector machine. And what we see is what we expect over there. Linearly separable can be done with a line. Here it can't. What is a tree doing? A tree starts with one of the features, x1, and says, where shall I put my vertical line? And the way it makes that decision, there's all these equations that you can look at that sound awfully intimidating. Don't worry about them. Think of it in terms of mixing cocktails, let's say. Concentrations of stuff. It is trying to get, most of those metrics have some notion of the purity of the result. So look at this glass. No matter how fat I make this glass, I still have the same concentration of yellow and green. Until I hit this point, and then I have a little bit more green, so my yellow concentration has gone down. So that's not an ideal place to put the line. If I wanted a purer mix of yellow, this would be the best place. And over there I have the purest mix of green. Once I've done that split, I go, all right, down this branch, anything to do? No, it's all green, so I'm finished. It stops short. How about over here? Anything to do? Well, where can I split this one so I get the purest concentration of green on one side and yellow on the other side? Yeah, that one looks good. Anything else to do? Nope, then I stop. And that's kind of how they work. And when you have this sort of space, it's like trying to tile your poor bathroom when there's a diagonal bit. Smaller, 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 smaller tiles, too many branches. If you actually plotted this in your training data, you might be inspired to do a little rotation of the axes, and then it's whole in one. So then you can actually solve this with a decision tree because you do a bit of feature engineering. You have a lot of situations where lovers of some or other method will say, hey, you don't need that other fancy method. Look, we can do the same thing with our method. They just tamper a little bit with the features first to make the features friendly to their method, and then their method works. So you can do a lot by altering the features, or you can approach it by altering the algorithm. So when do you try this first? When you've got no labels, when you want an easy-to-read model, or when, if this, then that seems like a promising structure for your problem. What is bagging? That stands for boosted aggregation, and that is not as intimidating as it sounds. It also isn't only for trees. Let's look at it for trees. The length of my dataset is the number of instances, the width is the features. What bagging does is, instead of trying to swallow the entire dataset in one go, it at random takes some instances. It makes a tree with those, it stores the tree. Then it puts back those instances, and it at random takes some other ones. So it is sampling with replacement and fitting a tree every time, remembering all the trees, and then at the end, it lets all the trees vote to give you an answer. So this one says she'll like it, this one says she'll like it, this one says she won't. Now, this has some fairly nice properties. Under certain circumstances, it actually has better performance than not doing it. But even if it didn't have a better performance, a very compelling reason for this is that you might not want to swallow your data all at once. You can parallelize all that and handle little bits of your data all separately, fit all those trees separately, and maybe that's just a lot faster. And since the performance may even be better, that's some of the black magic behind this, boosted aggregation stuff, it's worth trying. Now, what is random forests? Now, that sounds like some science fiction thing, like something from Lord of the Rings or The Hobbit, like the forest rises up and marches around. Random forests is actually kind of like bagging, but on the width, not the length. And usually it's implemented with both of them. So you take some sample of the instances, and then within them you take some sample of the features, so you end up with kind of like a little square of your data, and then you fit the tree on that little one, and then you do this again and again and again. This is a really great technique for data mining, because if you run your data set through this, if all of your features are equally useless, because you're doing this random sampling, you should expect that you will see your features crop up in the trees with about the same frequency. So if you just count how many times the feature was selected by your tree, and some of them are more popular than others, then that might tip you off to pursuing that feature. So you're inspired to do something with that. Now, if we're going to allow things to vote together, why stop at just trees? Why not allow a neural network to vote next to a tree, to vote next to a perceptron, to vote next to Cassie's opinion, to vote next to your opinion all together and have all these opinions vote? I can change the weights on how much each vote counts. Of course, Cassie's vote gets 95% of the weight and so forth. That is called an ensemble. What ensembles are really great at is covering one another's faults, if you will. So think about it like this. If you wanted to do your decision making by one awesome, benevolent tyrant who is really, really good and on the whole better than everyone else in your organization at decision making, that would be fine unless there's an Achilles heel, a fatal flaw. On the whole, really good, but there's a blind spot, and if that blind spot is hit, that is critical failure. Well then, maybe you want to have a backup decision maker who is not that much worse at all the other parts, but covers this critical failure. Pretty good at that part and has a different flaw. Well, then we can have them balance one another out, and hopefully, where they are both decent, there's not that much of a performance degradation, so on the whole, this feels like a better system. The flip side, though, is when you start composing all these various methods together, the engineering and maintenance and upkeep and reliability issues become a nightmare. So a famous example is the Netflix prize. It was $1 million prize that Netflix gave for making a cool recommendation algorithm. And the solution there was a crazy big ensemble model. And of course, Netflix nobly paid up because that did win the competition, gave the best performance. Or they didn't implement that thing because that was not going to work sanely in production, just too much going on. All right, what is naive Bayes? What are Bayesian methods in general? They summarize to this: when in doubt, use Bayes' rule. Now, what on earth is Bayes' rule? It is a piece of math which, if you're not careful, you may fall in love with, and then it finds its way into all kinds of places in your life. Maybe you've tattooed it on yourself, or maybe you're making art, light fixtures, like this is an actual light fixture, in the form of Bayes' rule. And so, not in the spirit of equationsing, but in the spirit of art appreciation, let's make sure we know how to pronounce this formula. Now, there's nothing controversial about this formula. If you've heard of classical statistics versus Bayesian statistics as a controversial thing, that's for the statistical testing. That's very philosophically heavy. For machine learning, though, there's no philosophy here. This is borrow whatever math you can find lying wherever, and if it works, and doesn't matter. And actually, if all we're using is this formula, there's no controversy at all. This is a mathematical formula with a proof it works. So how do we read it? Well, whenever there's P with brackets, that's pronounced probability of. And A and B here are just events. Events like the coin comes up heads or falls on the floor or whatever. Events like your roommate forgot to wash the dishes, events. And this vertical bar that you see over here and here is pronounced conditional on, or given that, or in a world where. So let's practice conditional probabilities real quick. We'll pronounce things like the probability that we have a cat given this evidence is equal to blah, blah, blah. So what does this boil down to computationally? It's all about counting things. In fact, we're going through this quick little demo just to show you the simplicity of the operations involved. Super simple. Look at this. Probability of cat. How do we get that? How many pictures? 8. How many of them are cats? 4. 50%. How about probability of lots of green pixels in a world where cat? Well, very simple. We said in a world where cat, so why are we bothering with all the other ones? We only care about the cat ones. And then the formula is simple again. It's the straightforward thing. How many total? 4. How many have lots of green? 2. And there's our answer. Very easy to make these manipulations. So what are we doing? Dividing, ignoring, and counting. Those are very easy for a computer to do as well, and that's going to be the point. Now, naive Bayes tends to be baby's first spam classifier. That's the favorite example in machine learning courses, when you make the first spam classifier. And it's naive in the sense that it says my features have nothing to do with any of my other features. The presence of the word free has nothing to do with the presence of the word shipping. Now that's a little naive. We know that there might be some relationship between those words, and we know that if we were trying to model the universe carefully, if that were our goal, this would probably be a bad fit. However, we're trying to get the thing to work, and it might just work even if it's naive. So maybe we'll just try it anyway and see how it performs, where it's making these clearly ludicrous assumptions fine. So what's great about this thing is that it is going to use these elementary operations. And the way that these are all composed in a formula, I have a little link down there for you in the slides. Really, an undergraduate on their first day of a probability course learns all the components that you can do to put this formula together. So if an undergraduate student can do that on the first day with no background at all, it's not anything too deep. It's just composing what we had before and using some simple, straightforward manipulations, which you can find in the link. Same principle though. Counting, multiplying, dividing, ignoring. That's it, nothing else. And finally, when it's done, you interpret the results as, given all this evidence that you've put in, that treats all the evidence as completely independent from, all the bits of evidence completely independent from one another. What's the probability that I have a cat versus a not cat? And then you can either output the label that is most likely, or you can jump for joy that you're dealing with probability outputs, because now instead of just simply getting the flat label, you can say, hey thing, how sure are you? If you're saying some number that's too close to 50, maybe you don't know what you're talking about, and maybe I prefer not to listen to you, maybe I prefer to send this to some other process, maybe have a human look at it and make the judgment call. Whereas if the number is very close to 100% or 0, then I can go with what the system is saying. So, naive Bayes, when are you going to try it first? If you have category labels, and if you have category features, like text, for example. Now, having category features is no sweat. It's very easy to turn your continuous features into categorical ones. You have measured all kinds of things about my torso, length and width and whatever. Well, you can turn that into small, medium, large with no problem. Going from the category in the opposite direction, that's the hard one. So you can always turn your features into categories. When there are many features, this is a great idea. This handles a lot of features. And with text, the way that data actually tends to be encoded is you have all the possible words that one could meet in an email, and you are asking present or absent, or how many times present, how many times absent. So you have a bunch of zeros. We saw in this email no times the word hippopotamus and no times the word tiger, and one time free and one time shipping. And so we have in that row counts of that sort. There's lots of features. This can handle that situation. And it's also great when you need your code to be simple. The operations are super simple. Now there's a naive version, this counts thing. There's also a less naive Bayes. And that one involves crazy cool things like likelihood function, priors. Warning here, this is harder, but it is so cool. And if you're not careful, you will really fall in love with things. And then, like me, you might sink several years of your life into this. So watch out, maybe don't flirt with it too much if you don't want to fall for it. What's next? Regression. We've already seen regression. It's putting lines through stuff. It's about finding lines that are as close as possible to your data, like our smoothies example. And in statistics, regression refers to fitting models of this form. What is this saying to us if we imagine a spreadsheet? All the features of the columns of the spreadsheet. So what are we doing? We're finding something to multiply the column by. Every column gets its own thing to be multiplied by. And then once we've done those multiplications, we add it up, and that's the prediction. So that kind of form. And this has been around for a really, really long time. Why did it take 200 years for us to roll around to this machine learning business if this has been known for a long time? Well, the way you use the algorithm is different. What they were going for is fitting the algorithm and describing their universe, and there were notions of statistical testing around that algorithm. What we are doing is taking that piece of math, after we have split our data, trying it out to see if it makes a recipe that looks worthwhile when we apply that recipe to a second data set. This entire machine learning thing is the result of enough data so that we can afford to split it into multiple pieces and then apply a lot of different stuff to the first piece, check if it works in the next piece, and then have a final safety check in the last piece. Machine learning is an attitude that is around splitting data, and when Gauss was starting out with this, there wasn't a lot of data to go around. When are you going to try this linear regression approach? If the output is a number, a dosage, a dollar amount, something like that, calorie count. And if the value of the feature is more meaningful than just a threshold. And to explain this, let me tell you another little story about developing this course. In the early days, I didn't have these slides, the try it if slides. And I remember presenting this in Zurich, and we have some lovely Googlers in Zurich who are really kind and want to make sure that my flight home is as entertaining as possible. So I got some emails from them that went as follows. Hey Cassie, we see you like long movies. So have you heard of this 6-hour movie? And have you heard of this 5-hour long movie? Very kind, but it's a fundamental misunderstanding of what the decision tree model before was saying. That model doesn't say the longer the movie, the more I'm going to like it. That model says, if the movie is above 127 minutes, recommend it. Otherwise, don't. There's nothing about the value of the feature being more meaningful than the threshold. So if they'd really understood that message, I should have gotten some people recommending me movies that were 128 minutes also. Or, 2.5 hours, not straight to the 5 hours. That kind of reasoning of every additional minute adds an additional bit of goodness, that is reasoning that is consistent with this sort of model. This kind of model is the one that says longer is better. For every additional gram of carbohydrates we add to the mix, we get more calories. It's not just like there's a threshold. If we're above 40 grams of carbohydrates, it's infinity calories already, and we should all panic. So this one, it has the structure of adding a little more, gives you a higher prediction. Now, the simple linear regression thing does not transform any data for you. It just takes those columns, finds something to multiply them by, and off we go. But there are other flavors of regression, more interesting, complicated ones. Here are some popular ones you may run into. Kernel regression, you already have a sense of what that might involve now that you know what kernels are. The one we'll look at is logistic regression. Logistic regression is one of the most popular approaches to binary classification. And we really love that here at Google because it is very nicely scalable. So binary classification here, at enormous scale, we like this kind of approach and we like neural networks also. So let's have a look. We're going to apply this to an utterly made-up example involving, can knowing the hours that a student has studied help us guess whether they are going to pass or fail an exam? Let's see our data. On the x-axis, we have the number of hours they've studied from 0 to 40. In blue, the ones are passes, the reds are fails. And as you're looking at this, you're like, of course hours of study has nothing to do with passing and failing. Of course. Or are you looking at this and thinking, yeah, there's something to it? I'm seeing that it does look like there's a little more failing on the low end of the study spectrum and a little more passing on the high end. So let's see if we can make a model. We're supposed to be in a putting lines through stuff section, aren't we? So let's put a line through it. Now, we would love to interpret this as a probability. We've seen already in that previous section that it's nice to get probabilities as output. But let's read. If I study for 2 hours, I have what? A negative probability of passing? That doesn't even make any sense. Probabilities can't be negative or more than 100%. So if I insist on getting a result between 0 and 100, I'd better try something else. So here's what we're going to do. Logistic regression. And I'm not going to show you what's happening there behind the scenes, details. I'm going to show you essentially how you should think about this, and especially at scale. What you're going to do is you're going to do something like a predicted probability in the sample probability of passing at each hour. And then you're going to do a little bit of converting those individual things to a different scale entirely. So you push them through a different function, and I've actually grayed out that function. It's the logit function. You don't have to even worry about what that function is. The point is simply this. When you have done that transformation, does it look like a shape that we are familiar with. It looks an awful lot like a line now, doesn't it? And so now in this converted space, our studied versus this logit, whatever on earth it is, we can fit a line model to it. Great. So we can use this model to predict this logit thing. Was that what we asked for? No, we didn't want a logit. So let's undo the damage. Let's take this model and convert it back to our original coordinate space. So it's like flip it, fit, and reverse it. And when we pass this thing, this line, through another function, ta-da! That looks a little more through it, right? This lovely S-shaped curve. These S-shaped curves, they are called... What is a psychoanalyst's favorite mathematical function? Sigmoid Freud. It's too late in the day for this, isn't it? So these are called sigmoid or logistic functions. And when you see these things in the context of data science pursuits, typically that sigmoid serves the function of forcing your output to live between where you have said it must live. Probabilities have to stay between 0 and 1. Okay, this is a way to force it to stay there. But another lovely thing that you get from the sigmoid curve is something that you might remember if you have ever taken an economics class. I have an undergraduate degree in economics, so I still remember the nightmare. So who's taken an economics class? Anyone? I see a few hands. So do you remember really early on there was a law of something? Diminishing marginal returns. Exactly. This is a way of algorithmically, mathematically putting diminishing returns into your model. So let's read what it says here. If I study for 20 hours, pass-fail for me is touch and go, right close to 50%. But let's say that I study an extra 10 hours over that. Look, my probability is pretty close to 100% of passing. I'm pretty sure I'm going to pass. So if I put another 10 hours in over that, am I going to be again that much more likely to pass? No, I'm already passing. Or, if you want to put it a different way, at 20 hours, it's touch and go. If I reduce by 10 hours, I'm failing, so I may as well not study. Standard undergraduate logic. So diminishing returns is encoded nicely in this model. So you get to peg your output where you want it, you get diminishing returns from your sigmoid functions. And this is more like a model of probabilities. And again, to classify new instances, either we can simply assign whichever label is more likely. So if it outputs for me 0.55, then I will call it a pass. Or I can say 0.55 means you don't know what you're talking about model. Let's call that the I'm not sure zone and actually ask a human for their opinion. So logistic regression is a great tool for binary classification, and it works well at scale too, including at Google scale. We use logistic regression a lot around here. Now, it can also work not only for binary labels, there's a version that works for multi-class classification, and that is multinomial logistic regression. So it's not only pass, fail, or cat, not cat, you can also use it for cat, dog, bear, elephant, giraffe. So this one, the binary one, works for binary labels. You can also do multiclass. And it's a good choice when you have that sense that diminishing marginal returns is part of what you're dealing with. And it gives you probabilities out, which is very nice. And probabilities are pretty useful for ranking stuff. Like if you want to serve the user the song that they are most likely to listen to next. So for each song, you predict the probability that they're going to interact with it. And then you can order it by the probability results. That's one simple way to do some ranking. The last section is neural networks or deep learning. I make it sound like there's a choose your own adventure element, one or the other. They are actually pretty much synonyms. Deep learning refers to neural networks with more than one layer, or deep neural networks, and deep neural networks were named when there wasn't much computing power to go around, and so we could barely dream of having maybe 2 layers. We stick with 1, but like maybe one day we can achieve 2. We shouldn't even hope about 3. Today, they've all got many. They've all got more than 2, the real ones, the production ones. They might have thousands. So they're all deep. All neural network stuff is deep learning. Feel free to use this as synonyms. All right, so we're going to dive into this. And a small disclaimer. We shouldn't even hope about 3. Today, they've all got many. They've all got more than 2, the real ones, the production ones. They might have thousands. So they're all deep. All neural network stuff is deep learning. Feel free to use this as synonyms. All right, so we're going to dive into this. And a small disclaimer. At the end of our less than half an hour section on this topic, your understanding of them will not have improved at all. Hopefully, if I do my job though, you will understand why that is and you'll be okay with it. Now, feedback I hear from many semester-long courses on neural networks, pretty much the same. The student spends an entire semester and also doesn't understand them any better. So for the low price of less than 30 minutes, you will get the same improvement in understanding as you might get from an entire semester. So shall we dive in? What are neural networks? Not that. That. Layers upon layers of mathematical transformations. Not anything magical. Just a lot of operations stacked together. And let's see an example, and I don't want you to take this example too seriously. This is just an analogy that's going to get our thinking started. So let's have a look. In case you didn't realize that it's a really bad idea to let me into the kitchen, we are back with a cooking analogy. So we're going to have some features, and they will be of plant, animal, or artificial origin, and they're going to vary for each individual instance. So think of this as the column headings in your spreadsheet. So your spreadsheet is sort of turned this ways, in my example. And our first instance has, for its plant, some broccoli. You know how much I like those sardines, so that's our animal ingredient. And for artificial, we have mint-flavored candy canes, because I submit to you that there is nothing natural in these things. And then what do we have? We have an output layer that is going to output something like tasty or not tasty, as our label coming out. And inside we have some hidden layers, which are thus named because they are hidden for your own good. Because if you look into the hidden layers, the abyss stares into you. So good advice to leave them hidden, but we're not going to take that advice today. We're actually going to look inside them and see some of the units in these hidden layers, also known, if you prefer the more futuristic sounding jargon, as neurons. And the role of the neuron will be played by a blender. So what are we going to do? We're going to take our individual ingredients here, but we're not going to take the whole ingredient all in one go. This can of sardines is much too precious. We're instead going to take some weight, some amount of each ingredient, and we will put them all into our blender, and we will blend them together. And I know what you're thinking at this point. You are dying to taste it. Indeed. And think of the taste test as the point where you're going to decide whether to allow this unholy mix to move forward or to not use what's there at all. This taste test is kind of like the activation function in neural networks. We take the thing that we've blended up and we do some kind of transformation to it, in this case using our taste buds and asking ourselves, is it good enough to move forward or not? So think of that little taste test as a little twist on the plot, adding a little bit of non-linearity, and I'll tell you why we do that shortly. But as a taste test, we taste it, apparently it's yummy, and it gets to move forward in its entirety. Now I'm tired of writing the word weight, so I'm going to indicate the weight with the thickness of the line. So far, so good. Everyone has blended stuff, yeah? In different weights of ingredients, yeah? Good. Next, we have another unit, or blender. And we're going to take other weights of these same ingredients, blend them up, taste it, that doesn't go forward, and then we'll have another blender. We taste that, it's delicious, and there's more in the next row. We blend up these various mixes in various amounts. We taste all of them. Some of these go forward, we blend those up in various amounts, we taste that, and there's our result. Whew. Now, all of you have been in the presence of a blender. Maybe even 7 blenders, all at once, maybe in a store. You've all done blending. So no part of this is complicated, intellectually speaking. But if I ask you to express to me what on earth is in this vat, especially since now you have to express the taste test procedure as part of that recipe, you realize that your head is spinning a little bit. See, if we didn't have the taste test, then you could just say, well, actually, how much of each of these ingredients did we use? I mean, you could just collapse the recipe down to, but why have all these different blenders? You could just collapse that down to effectively one blender. And then it's not a very interesting recipe. But with the taste testing, now it's something more complicated and convoluted. You have to write the whole thing out. And if I ask you to explain it to me, that is why you don't understand neural networks. Not because the individual bits are difficult, but because there is so much going on. They're building out these complicated recipes out of simple components. Let's see what it looks like in a more realistic setting. We have some binary features, light switches on and off, and we are going to combine them by taking a weighted sum. Now, this input doesn't have to be binary. Just for our example, we'll use some binary data to keep it simple. So here are our column headings, and our first row just says 1, 0, 0. We take a weighted sum, so our weights are numbers. And 0 times anything is 0, so ignore that. Our weighted sum result is 2. And then we are going to send it through an activation function to add some nonlinearity so that we won't just be able to collapse all the weighted sums down into a single simple weighted sum. So let's use one that we are comfortable and familiar with. How about sigmoid Freud? So we'll use a sigmoid activation function. So all we do is we find the 2, we put it in, we get 0.9. You don't have to use that activation function. You can go and find your favorite on a long list of them. The most popular one these days that the machine learning hipsters will tell you to use is ReLU, which sounds a little like an alien, I guess. But actually it's the one that I was describing with the taste test. It's just asking if the output, the weighted sum, is above a particular number, then keep that whole thing, and if it's below that number, then drop the whole thing. Actually, the hipsters probably wouldn't even go for ReLU. There's a whole variety of various activation functions. I think maybe a more hipstery thing would be the hyperbolic tangent or something else. So there's lots to choose from. What are you going to use in the end? Whatever is available in the implementation of the algorithm that you are working with. And if there are several options, what are you going to do? Try a few and see how it's going. But wait, there's more. We are going to take more weighted sums, and because we're tired of doing these calculations, we get the point already. We're going to pretend we did them, there you go, and we send them through our activation function as well. And then we do that again in the next layer. More weighted sums, more activation functions. Whew. And finally, our output, which we then turn into a 0 because it's closer to 0 than to 1. Again, you can all take weighted sums. You can all put a number through a simple function. That was not hard. But when you do this enough times and you stack enough of these operations together, if I ask you to write out the recipe that got you this final thing, well, that can make you dizzy. And if you don't believe me, to have real respect for neural networks, I would like you to play a game for homework called Do I Hate Cassie Yet? So here's how it works. For our simple neural network here, and I've even left a few things out, like bias terms and cool stuff like that, just for this simple setting. Write out the recipe in symbols, or you can fill in the values if you want. Write out the recipe that takes you from your benign binary inputs to the final output. What is the actual recipe over here? Not in terms of the operations, but in terms of mathematically with the logs and all that good stuff. Once you've written that out, add another layer with, again, 3 units in it. And see how much more writing it takes to go from this size with 2 hidden layers to 3 hidden layers. And you'll notice that your writing has more than doubled. But do we hate Cassie yet? If not, add another layer. And if you don't hate me yet after that, another layer. And another one, and if you get to 7, I'm super impressed. Because at some point you will be like, I have better things to do with my life. This is an annoying long recipe that I have no desire to read or interpret or look at. It consists of simple components, but it ends up being transformations of transformations of transformations. Very hard to read, very hard to write down. So you prefer to think simply in these individual components, but then when you're like, but what is actually going on? Very hard to see it, even though each individual little piece is simple. That is why you don't understand neural networks, or rather why the recipe involved in neural networks is so difficult to think about and read and understand. But the operations that get you there, they are not so difficult. And TensorFlow makes you program in terms of these graphs and these operations rather than that recipe altogether. Now, why all these transformations? What do they get for you? Well, let's go back to our city planning example. With our historical buildings and our modern buildings, remember that example with our support vector machines? There, it was bad enough that we had all our red things all clustered in the center and the blue things around them. But we could do that whole kernel trick where we punch through the sheet and we transform it by making the dimensions higher, and then cutting it with the plane. That worked. But how are you going to take that approach to the spiral? Where are you going to punch it for this to work? Or maybe you want to try k nearest neighbors. How many nearest neighbors, and at what point will it break down and start finding neighbors that are from the wrong spiral? Or where do you want to do the decision tree here? All of our methods aren't doing very well for this example. Now, what those transformations do is they torture the underlying space so much that, hopefully, they pull it apart so that things got separated under all these crazy transformations, and boom, you can cut it again. And what that means is that you can solve problems like that one, where your data set is a bunch of pixel values. Where are you going to put a line through those pixel values to output cat, not cat? Now, you could go and maybe do some feature engineering by hand to go and first ask, is there something like ovals for eyes and 2 of them, and look for ears, and it's going to be a bit wobbly if you have this cat burrito with no ears. Instead, you could feed in a lot of data, and because this thing is so flexible and can do all these transformations itself, it will let you take advantage of those features without you having to explicitly go and find them yourself. This isn't free, though. There is a price here. Because this is such a complex recipe, we saw with the ideal body shape of the dataset that the more there is going on in the recipe, the more complex it is, the more features it uses, or the more transformations, the more length you're going to need, the more examples it will take to make it work. So this is very expensive, both in terms of how big your datasets need to be for this to be viable, and how much computing power it takes, because you see there's a lot of stuff going on. If you don't have a lot of data, you just simply might not be able to take advantage of this really powerful algorithm. Now, another thing is, when it says it exploits complex structure, and it finds those eyes and noses and so forth, this makes it sound like they're going to do that and show you what they're doing. They're not. Just behind the scenes might take advantage of stuff like edges, shapes, triangles, ovals, but you won't know what it's doing. So it'll be up to you to make sure that you really pick your test conditions carefully. Really think about the data set. Which images are you going to use to make sure that this thing actually does work the way that you expect it to work? Check your data set to make sure that there isn't something in there that is found instead of the label that you are looking for. Like in our earlier example where all of Cat 1 had radiator and all of Cat 2 didn't have radiator in the background. Make sure there isn't something special about your data, especially when you work with methods like this that don't lend themselves nicely to interpretability. It's really, really important to do profiling of your input data, profiling of your outputs, and think about what's going on there. Please do check, don't trust blindly. Now, what is there before we begin with this method? From the architecture, the settings that you set up how many layers are we going to use? Is it 1, 2, 3,000, whatever. You also choose how many units are in each layer, and it doesn't have to be the same number of units in each one. And you are going to choose the activation function that you'll use. So that's all there before you begin. From each data point, you get the actual values. So if this is a row in your spreadsheet, these are the column headings, and the first row has 1, 0, and 0 in it. And then as this flows through your network, the values inside the hidden layers are also determined by that particular example. And so as your network evolves and changes and learns, because it will learn from each individual data point in the simplest implementation, then you might have the same input values for 2 data points, but because the network has changed in between them, you might have different hidden layer activations. So that's all from the individual instances. So what is the part that we're learning? This is supposed to be machine learning, deep learning. What's the bit that's being learned? What do I hear from you? The weights, that mess. And I haven't even shown you everything here. I've left off the notion of bias units, which are going to add another 3 to these. I just want to keep it simple. But even with this oversimplified setting, what have we got? We've got 9 and 3, I can't count, 21 weights to deal with. For our calories example, we also had 3 features, carbs, proteins, and fats, and that was bad enough. We had 4 parameters to tinker with, and we were like, no way, just get on with it, optimization algorithm. We don't want to have to do this by hand. Look at this, 21 of them. Now imagine doing that by hand. Just take a moment. In comes a data point, and then which one are you going to change, in what order? In comes a data point. You'll be comparing the output that you want with the output that you got. You wanted a 1, it gave you a 0. Okay, which weight are we going to change? In what order? Turns out that optimizing those weights, before we die of boredom, is actually a challenge, and doing this by hand is just not going to work. So we're stuck unless we have an optimization algorithm that can do it quickly. And that is what the backpropagation algorithm is all about. For your purpose, backpropagation is the reason that you get solutions here, in this lifetime, rather than in the old age of the universe. You don't need to know much about it as practitioners because it's already implemented in those packages for you. You don't need to go reinvent the wheel. So even though it is part of day 1 of every neural networks course ever, if you're finding it tedious, you can just ignore that because it's already implemented. Just think of it as the reason that you don't have to wait forever for the results. I remember a fun moment where my friend who has a PhD in machine learning, who is a researcher, was saying, oh yeah, I have to go teach backpropagation tomorrow, so I can't go drinking because I have to go relearn it. Turns out you could be a career machine learning researcher and have entirely forgotten it, but somehow it's part of the hazing every time. So if you take a course and you're like, I'm not getting it and it seems annoying, do I have to fail out of the course or can I just ignore this one and hope it goes away? If you're going for how to be an applied person, you can probably get away without worrying about it too much. And let's see what's happening. We take an instance and we send it through the network just as we sent those numbers through earlier to get a label out on the other side, and we call that forward propagation. And then when we look at the label, we compare it with what the true answer was, and we see a mismatch. And of course, our first response is, whom do we blame? Well, to figure out where we should start making adjustments, we essentially propagate the effects, echo, influence of that error back through the network to find where and how much we should make the adjustments. That's what that backpropagation algorithm is doing for you. And if you do end up looking into it and you really want to know what it is mathematically, remember calculus? Remember the chain rule? Do you like the chain rule? I hope you do. After this, you'll like it out of Stockholm Syndrome. Backpropagation is just the chain rule a lot. And then the adjustment is made. And now you take your next instance, forward propagate it through, get the label, get the mismatch, back and forth, back and forth, back and forth, like sewing with a needle. And as those weights adjust, the solution becomes more and more of a good, sensible recipe for you. That's the simplest implementation. Now there are more interesting ones where you can train on many instances at once. Now you'll of course need to start with an initial selection of weights. So here's what not to do. Setting them all to 0. Anything times 0, you already know the answer. The punchline will be everything will be 0, no learning will happen. The next worst thing that you can do is set them all to the same number. Because fundamentally what this is doing is asking, well, whom do I blame? So you're looking for the most heinous looking culprit, and if they all look the same, then there's no one to blame. And then all of a sudden, no more learning happens, and you have a problem. And that's a kind of noob gotcha that happens also, either setting it yourself that way, or having it just accidentally end up learning itself into symmetry, and then there's no one to blame, and then all of a sudden learning stops, and you're like, what happened? And you go to your senior machine learning sensei, and they're like, oh, don't worry about it, just whack the TV one time, just restart it, and see if it's okay. And you're like, what is this black magic? This makes no sense. What, I just whack it and it works? Well, whack it with another selection of random weights, and hopefully you don't end up with that bad symmetric situation, and off we go. So symmetry is not your friend here, and if you end up in a situation with too much symmetry, then you might see that learning got stuck and isn't happening. Another reason it may stop behaving itself, stop learning, is maybe somewhere in there you're doing a lot of multiplication over a lot of layers, and you're multiplying fractions with fractions, and fractions multiplied with fractions, multiplied with fractions, multiplied with fractions become very small numbers, and eventually your computer can't tell the difference between them, and problems. Now, when it comes to this weights thing, the way to approach it is pick random starting weights. Yes, they are all wrong, but one of them is more wrong than the others, and then off we go. And I've got a footnote for you on some advice on how to set the weights. Okay, so the pros and cons of neural networks. The pros are that these complex transformations have so much flexibility that if everything else has failed, these still might succeed. They are best at fitting. So what's the con? What's best at fitting is also best at overfitting, exactly. And not just that. Remember the limbo, the overfitting limbo that you can get stuck in? Well, to work with these things takes more engineering effort and more computing resources. And so now you are riding this limbo merry-go-round, but you are riding it slowly, very slowly, and that is a painful existence. So you don't want to start with these if you have no reason to suspect that everything else is useless. You only want to be playing this game if you're pretty sure all the simplest stuff isn't going to work out for you. Now, how do we pick the architecture in practice? There's all kinds of advice out there on the internet, things like for input units, it's going to be your number of features, for output units, the number of label classes. For the hidden layers, start small. Why start small with the hidden layers? Overfitting. Even here, even within this class of algorithms, fewer hidden layers is a simpler algorithm than more hidden layers. And if you don't believe me, do that homework exercise of Do I Hate Cassie Yet? And see just how much more complex the recipe gets as you add each layer. And hidden units, there's all kinds of crazy cool different architecture options. Some simple ones would be same number of units in every layer, so like a pipe, or like a triangle, a funnel, where you start big and you get fewer and fewer as you get to the solution. But there's many others. Why even listen to me when you can play with it yourself? You're like, I don't want to play with it myself because you just told me it's so much effort to try coding it up. We have a fun thing called TensorFlow Playground. You can click on that link, and then you go be the architect. And without writing a single line of code, you can go and see how different architectures affect the solution. So you can say, I want ++, 4 hidden layers, and I want to put 8 neurons in the first one, and I want to put 2 in the second one, and 3 in the third one, and so forth. And you're like, what activation function do I want? I want the hipster one, or I want the standard one, or whatever else. You take that from the drop-down, and you see how that affects your results on your output. And you'll see that there are going to be different scores for training and for testing. And you'll notice that you tend to do better, less loss, in the training than in the testing. Now, at the end of this section, neural networks might feel like a black box to you. And I hope that now you're okay with that. Now you understand why. There's a lot going on. Lots and lots and lots of operations. And so it's okay, don't worry about it. Don't try to read the recipe that comes out, especially if you have 1,000 layers and in each one there's 1,000 units. I mean, that's the sort of scale we're talking about with the big applications. Reading that recipe is going to make no sense at all to you. That's okay. Remember, at the end of the day, proof of the pudding is in the eating. So take the outputs. The output is the same as any other output. Doesn't matter what model made it. Compare it against the value you wanted and see how you're performing. So neural networks, try it first if. Yeah, there is a try it first section here. There are good reasons for this to be the first thing you try. Those good reasons are that you know everything else is not going to work because other people have already tried similar applications to yours and they've figured out that it's useless to try to attack it with a line or a tree or whatever else. I wouldn't try something else for images. If I'm doing image classification, I just go right to neural networks. I learn from the mistakes of others. Speech recognition, language translation is the same. Or if you have a lot of domain expertise and you know that the relationships are really complicated that you're dealing with, well, then you might want to go straight to here. So it's a good idea if your application is something similar to what other people do, to ask, hey, for data kind of like this, which algorithms tend to work out, and then you start with the simplest among those. Then, I'm kind of loath to say this, if you have a lot of data and you don't care how much computing costs, maybe in that situation you might also go right for it. But it is an expensive way to be lazy. Usually a little bit of analytics goes quite a long way to saving money and getting you decent solutions that are simple. All right, so thank you, that's it. You have survived the day and with 30 minutes to spare, so 30 more minutes of alibi. And no one knows that you're goofing off, so enjoy. Thank you so much for being here, and I'm here for questions.